Reality is a word humans use with confidence, yet rarely define with precision. We speak of reality as if it is solid, fixed, and complete, but in truth, it is a narrow window shaped by biology, physics, and limitation. To understand what might exist beyond the edge of reality, we must first understand what we mean by reality itself and why we instinctively believe it has boundaries. At its most basic level, reality is everything that exists independent of belief. It is the sum total of space, time, matter, energy, and the laws that govern them. Yet no human has ever experienced reality in its entirety. What we perceive is filtered through senses, evolved for survival, not for truth. Our eyes see only a thin slice of the electromagnetic spectrum. Our ears capture a narrow range of vibrations. Even our sense of time flows in one direction, locking us into a specific perspective from the very beginning. Human reality has been incomplete. Early humans believed reality ended at the horizon. Beyond the edge of the land was an ocean. Beyond the ocean, a void, monsters, or nothing at all. This pattern repeats throughout history. Every era places an edge where understanding fails. When the Earth was believed flat, the edge was literal. When astronomy advanced, the edge moved to the stars. When galaxies were discovered, the edge moved again. Reality never expanded, only our map of it did. This reveals an important truth. What we call the edge of reality is not necessarily an edge in existence, but an edge in knowledge. It is the point where observation breaks down, where measurement fails, and where prediction becomes speculation. Humans are uncomfortable with such edges. We instinctively want reality to be complete, enclosed, and explainable. A boundary gives comfort. Infinity does not. Modern science defines reality through measurable quantities. Space has dimensions. Time has duration. Particles have mass and charge. Forces obey equations. But even within this framework, cracks appear. Quantum physics shows that particles do not behave like solid objects until observed. Relativity shows that space and time are flexible, shaped by mass and motion. Reality is not the rigid structure it once seemed. It is dynamic, contextual, and deeply strange. This strangeness raises a fundamental question. If reality behaves differently at different scales, then what exactly are its limits? Does reality end where our equations stop working? Or does it continue in forms that are inaccessible to us? The idea of an edge emerges precisely because our tools have limits. Telescopes can only see so far. Experiments can only reach certain energies. Mathematics can only describe what it can formalize. Beyond that lies uncertainty, not necessarily nothing. The observable universe provides a powerful example. There is a maximum distance from which light has had time to reach us since the beginning of cosmic expansion. Beyond that distance, galaxies exist, but they are invisible to us, not because they are unreal, but because information from them cannot arrive. For an observer on Earth, reality appears to end at this horizon, but the universe does not end there. The edge is observational, not physical. This distinction matters. An edge of perception is not an edge of existence. Yet humans often confuse the two. Throughout history, whatever lay beyond observation was labeled unreal, mythical, or impossible. Atoms were once invisible and therefore hypothetical. Galaxies beyond the Milky Way were once unthinkable. Black holes were dismissed as mathematical absurdities. In each case, reality extended beyond belief long before evidence arrived. So why do humans persist in imagining an ultimate edge? Part of the reason is cognitive. The human brain evolved to operate within finite environments. We understand beginnings and endings. We understand borders and containers. Infinity overwhelms intuition. A reality without edges feels unstable, meaningless, or terrifying. Placing a boundary allows the mind to rest. Another reason is philosophical. If reality has an edge, then it can be defined completely. It can be measured, catalogued, and mastered. Without an edge, reality becomes open-ended, forever incomplete. This challenges not only science, but identity. If reality is boundless, then human understanding is permanently limited. Not temporally, but fundamentally. Religious and mythological traditions often addressed this discomfort by placing something beyond the edge, heavens beyond the sky, underworlds beneath the earth, divine realms outside physical space. These were not random inventions. They were cognitive solutions to the problem of excess reality. When the known world felt too small to explain existence, something greater was placed beyond it. Science did not eliminate this impulse. It refined it. Instead of gods and spirits, we now speak of dimensions, multiverses, and abstract mathematical structures. The language changed, but the motivation remained. We sense that what we experience is not all there is. Reality feels too deep, too consistent, too structured to end where our instruments stop. Even the word reality implies contrast. If something is real, something else is not. Illusion, dream, hallucination, simulation. Yet these distinctions blur under scrutiny. Dreams occur within the brain, which is part of physical reality. Simulations run on hardware composed of atoms and energy. Hallucinations follow neurological laws. The boundary between real and unreal becomes less clear. Perhaps reality is not a single layer, but a stack of interacting layers, some accessible, others hidden. This layered view changes the meaning of an edge. Instead of a wall, the edge becomes a transition. Beyond familiar reality may lie forms governed by different rules. Not supernatural, but natural in ways we do not yet understand. Just as microbes existed before microscopes, entire structures of reality may exist beyond current detection. Physics already hints at this. Forces that seem separate may unify at higher energies. Dimensions beyond the visible may influence gravity. Space-time itself may be emergent rather than fundamental. If this is true, then what we call reality is not the foundation of existence, but a surface phenomenon. The edge of reality would then be like the surface of an ocean, beneath which deeper structures operate unseen. There is also the question of whether reality is observer-dependent. Our measurements shape outcomes. Our reference frames affect time and space. If reality depends partly on observation, then different observers may inhabit different realities, overlapping but not identical. In such a universe, edges would not be universal. Each observer would carry their own horizon. This possibility is unsettling. It suggests that reality is not a single shared stage, but a network of perspectives constrained by information flow. What exists beyond one observer's reality may exist fully within another's. The edge becomes relative, not absolute. Yet, even if edges are relative, the question remains, is there an ultimate boundary, a final limit beyond which nothing exists? Some theories suggest reality may be infinite, without boundary in space or time. Others suggest a closed structure, finite but unbounded, like the surface of a sphere. In such a case, there is no edge to reach. Travel far enough in one direction and you return to where you started. Both possibilities challenge intuition. An infinite reality denies closure. A finite but edgeless reality denies direction. In neither case does the familiar idea of an edge survive. The very question may be flawed. Asking what exists beyond the edge of reality may be like asking what lies north of the North Pole. The concept breaks down, and yet humans continue to ask, because even if the question is flawed, the intuition behind it is not. We sense that what we experience is incomplete, that there are layers, depths, and scales beyond daily awareness. This intuition has driven exploration, science, and philosophy for thousands of years. It has been wrong in detail, but right in direction. The edge of reality, then, may not be a place. It may be a process. The continual expansion of understanding into regions once thought unreachable. Each time we cross an old edge, a new one appears further out. Not because reality ends there, but because knowledge always lags behind existence. In this sense, the edge of reality is permanent, not because reality is limited, but because understanding is. There will always be questions that cannot yet be answered, phenomena that cannot yet be measured, structures that cannot yet be imagined. The universe does not hide these out of malice. It simply operates on scales that dwarf human capability. This leads to a humbling conclusion. Reality is not built for us. It does not conform to human intuition or preference. It exists as it is, vast, layered, and indifferent. The idea of an edge reflects our position within it, not its structure. We stand inside a small illuminated circle, surrounded by darkness, mistaking the boundary of light for the boundary of existence. As this documentary unfolds, we will move step by step toward that boundary, not to cross it, but to understand what it represents. Each outline will push further into physics, cosmology, philosophy, and speculation, not to claim certainty, but to map possibility. Because beyond the edge of reality, whether literal or metaphorical, lies the deepest question humans can ask. Not what exists out there, but how much of existence we are capable of understanding. The observable universe is not the entire universe. It is only the portion of existence that has revealed itself to us through light, radiation, and measurable signals. This distinction is critical because when people speak about the edge of the universe or the edge of reality, they are almost always referring to the boundary of observation, not a physical wall or an ending of space itself. To understand this boundary, we must begin with light. Light is the fastest messenger in the universe. Nothing carrying information can travel faster than it. Every star we see, every galaxy we photograph, every cosmic event we detect reaches us only because light or other radiation has had time to arrive. If light from an object has not reached Earth yet, that object is effectively invisible. It exists, but it does not exist to us. The universe is about 13.8 billion years old. This number immediately imposes a limit. Since light travels at a finite speed, we cannot see anything farther than the distance light has been able to travel since the beginning of cosmic expansion. This creates a sphere around us, centered on our position, defining the observable universe. Its radius is roughly 46 billion light-years, larger than the universe's age might suggest due to the expansion of space itself. This boundary is often misunderstood. It is not a physical edge. There is no curtain, no barrier, no final wall of matter. Instead, it is a horizon, similar to the horizon on Earth. When you stand on a flat plane, the horizon appears to be a boundary, but it moves as you move. The land does not end there, your perception does. The cosmic horizon behaves the same way. If intelligent observers exist in distant galaxies, their observable universe would be centered on them, not on us. They would see regions of space we can never see, and we would see regions they can never see. Reality overlaps, but observation does not. This alone reshapes the idea of an edge of reality. It suggests that reality does not have a single, universal boundary. Instead, every observer carries their own edge, defined by time, distance, and the speed of information. Beyond that edge is not nothing. It is simply unobservable from that location. However, this limitation is not merely practical, it is fundamental. No improvement in technology can overcome it. Even a perfect telescope cannot see beyond the cosmic horizon because there is no signal to detect. Space itself is expanding, and in some regions it expands faster than light can traverse. Galaxies beyond a certain distance are not just far away, they are being carried away by the expansion of space so rapidly that their light will never reach us. This introduces a profound idea. Parts of the universe are not just currently invisible, they are permanently inaccessible. No future civilization, no matter how advanced, will ever observe them. They are causally disconnected from us forever. From a human perspective, this raises uncomfortable questions. If something can never be observed, measured, or interacted with, in what sense is it real to us? Physics answers clearly. It is real, regardless of observation. Existence does not depend on accessibility. Reality is larger than what can be known. This forces a distinction between reality and empirical reality. Empirical reality is the subset of existence we can observe and test. Reality itself may be vastly larger. The observable universe is not the universe. It is a sample, limited by time and physics. Cosmic background radiation provides a striking example. When we look deep into space, we are also looking back in time. The most distant light we can see comes from a period about 380,000 years after the beginning of the universe, when atoms first formed and space became transparent. Beyond that point, the universe was opaque. Light could not travel freely. Information from earlier times is hidden behind a wall of plasma. This wall is not an edge of existence. It is an edge of visibility. The universe existed before that moment, but we cannot see it directly. Our understanding of earlier times relies on theory, inference, and indirect evidence. Again, reality extends beyond observation. This pattern repeats at every scale. There are energies too high to reach with current accelerators, distances too small to probe directly, times too brief to measure. Each limitation creates a boundary, and each boundary tempts us to mistake ignorance for absence. Human perception compounds this problem. Our senses evolved to navigate a world of meters, seconds, and moderate speeds. The universe operates across extremes of scale that the brain did not evolve to intuitively grasp. Billions of years feel abstract. Light years feel meaningless. Quantum uncertainty feels absurd. As a result, the true size and complexity of reality is psychologically flattened. Because of this, the observable universe often feels like the whole universe. It is already unimaginably vast. Billions of galaxies, each with billions of stars. What more could there possibly be? The mind resists adding more layers beyond this. Yet inflation theory suggests exactly that. The region we observe may be a tiny bubble within a much larger structure. During the earliest moments of cosmic history, space may have expanded at an enormous rate, creating regions far beyond our horizon. These regions would be real, structured, and governed by physical laws, yet completely unreachable. If this is correct, then the observable universe is not even representative. It is a local patch, shaped by chance initial conditions. Beyond it, the universe could look very similar, or radically different. The laws of physics themselves might vary. Constants could shift. Dimensions could behave differently. This possibility destabilizes the idea of a single, uniform reality. Instead, reality becomes contextual. What is true here may not be true everywhere. What we consider fundamental laws may be local rules, not universal ones. This does not mean science collapses. It means its domain is clarified. Science describes what can be observed and tested. It does not claim to exhaust existence. When science reaches the edge of observation, it does not say nothing exists beyond. It says we do not know. However, popular culture often fills this uncertainty with imagery: walls of stars, cosmic voids, empty blackness. These images mislead. Beyond the observable universe is not darkness or emptiness. It is more universe, structured, dynamic, and full of events, simply disconnected from us. The emotional impact of this idea is significant. Humans often imagine themselves at the center of reality, not necessarily spatially, but epistemologically. What we can know feels like what exists. The observable universe challenges this intuition. It places humanity inside a much larger whole, with access to only a fraction of it. This has philosophical consequences. Meaning, purpose, and significance must be reconsidered in a reality where most of existence is forever beyond reach. Yet, it also offers a strange comfort. Reality is not constrained by human limitation. It does not depend on our awareness. It continues regardless. The edge of the observable universe is therefore not an ending, but a reminder that reality is not tailored to human perspective, that knowledge is local, that understanding is provisional. As we push our instruments to greater precision, the observable universe expands in detail, not in size. We see finer structures, earlier times, subtler signals, but the horizon remains. It is built into the fabric of space-time. This means that the ultimate edge of observation is not a temporary challenge to be solved, it is a permanent feature of existence. Reality is fundamentally larger than what any observer can access. In this sense, the observable universe is both astonishing and humbling. It reveals an immense cosmos, yet simultaneously conceals an even greater one. The more we learn, the clearer it becomes that what we see is not all there is. The edge of reality, viewed through the lens of observation, is not a cliff but a veil. Beyond it lies continuation, not termination. The universe does not end where our vision fades. It simply continues without us. As we move forward in this documentary, we will go beyond this observational boundary conceptually, not by seeing farther, but by thinking deeper, exploring theories that attempt to describe what lies beyond the observable, and confronting the possibility that reality itself has no edge at all, only limits to knowing it. The speed of light is not just a number, it is a structural limit built into reality itself. Everything we know about distance, causality, and time is shaped by this single constraint. When we talk about the edge of reality, in scientific terms, we are often talking about the consequences of this limit, because it determines what can influence what can be known, and what must remain forever beyond reach. Light travels at roughly 300,000 kilometers per second. This speed is constant, regardless of the motion of the observer or the source. This fact, discovered through relativity, rewrote humanity's understanding of space and time. Before this, speed was relative and unlimited in principle. Afterward, reality gained a maximum rate of information transfer. Nothing carrying cause and effect can outrun light. This has immediate implications. When we look at distant objects in space, we are not seeing them as they are now, we are seeing them as they were when their light began its journey. A star 1,000 light-years away is seen 1,000 years in the past. A galaxy 10 billion light-years away is seen as it was 10 billion years ago. Observation becomes a form of time travel. As distances increase, this time delay grows so large that it creates a boundary. There comes a point where light from certain regions has not had enough time to reach us since the universe began expanding. Those regions lie beyond our observational reach. They are outside our causal past. This boundary is known as the cosmic horizon, but its deeper meaning is causal. It marks the limit of cause and effect. Events beyond this horizon cannot affect us, and we cannot affect them. No signal, no matter how advanced the technology, can cross this boundary if the expansion of space outpaces light itself. This leads to a subtle but profound shift in how we think about existence. Reality is no longer just about what exists somewhere, it is about what can be causally connected. Something may exist in a perfectly real, physical sense, yet have no possible interaction with us. From our perspective, it is unreachable in principle, not just in practice. This challenges everyday intuition. In daily life, distance is an obstacle, but not a fundamental barrier. You may be far from someone, but in principle, you can reach them, given enough time and speed. The universe breaks this intuition. There are distances that no amount of time can overcome. Space itself expands, stretching the gap faster than light can close it. Because of this, the universe is not just large, it is partitioned. It is divided into regions that can never exchange information. Each region evolves independently after a certain point. This creates a patchwork reality, where what happens here has no bearing on what happens elsewhere beyond the horizon. This raises an unsettling idea. If parts of the universe are forever causally disconnected, then reality is fragmented in a fundamental way. There is no single, unified cosmic story that includes everything influencing everything else. Instead, there are many isolated narratives, each unfolding within its own causal bubble. From a human standpoint, our entire cosmic history is confined to one such bubble. Every star that influenced Earth, every galaxy that shaped our local group, every fluctuation that seeded our structure lies within this causal domain. Beyond it lies a vast unknown that will never touch us. Yet this unknown is not static. It evolves, changes, and obeys physical laws. It simply does so without any relationship to us. Existence does not require interaction to persist. It does not require observation. It does not require meaning. This forces us to separate two ideas that are often conflated: existence and relevance. Something can exist without being relevant to us. The speed of light enforces this separation. It draws a hard line between what can matter to us and what cannot. The concept of an edge of reality often arises from confusing relevance with existence. When something cannot influence us, it feels unreal. But physics does not support this intuition. The universe is under no obligation to be accessible. This limit also reshapes time itself. Because information travels at a finite speed, there is no universal present moment. Different observers have different slices of now. Events that are simultaneous for one observer are not simultaneous for another. Time becomes local, not global. This destroys the idea of a single cosmic now stretching across the universe. There is no moment in which the entire universe exists together in a shared present. Reality is temporally fragmented, just as it is spatially fragmented. When people ask what exists beyond the edge of reality, they often imagine a spatial boundary, but the deeper boundary is temporal and causal. It is the limit of shared history. Beyond that limit, events are not just far away, they are outside our timeline. This leads to a radical conclusion. The universe does not have a single history. It has many overlapping but incomplete histories, each centered on an observer's causal past. Reality is not a block experienced uniformly by all. It is a network of intersecting light cones. Our light cone defines our reality. It includes everything that could have influenced us and everything we could influence. Outside it lies a realm that exists but is disconnected. This is not science fiction. It is a direct consequence of relativity. Once this is understood, the idea of crossing the edge of reality becomes meaningless. There is no path that leads from inside a light cone to outside it. No amount of energy can change this. Even hypothetical faster-than-light travel would not merely move objects. It would shatter causality itself. This is why physicists treat the speed of light not as a technological limitation, but as a foundational rule. Breaking it would unravel the logical structure of cause and effect. Paradoxes would emerge. Timelines would collapse. So if faster-than-light travel is impossible, then the causal structure of reality is fixed. The horizon is permanent. The edge is built into space-time. This permanence has consequences for the ultimate fate of the universe. As expansion continues, more and more galaxies cross our horizon. Their light stretches, reddens, and eventually fades. They do not disappear physically, they disappear causally. They slip out of our reality. Far in the future, distant galaxies will no longer be observable at all. Future astronomers may see only a small island universe, unaware of the vast cosmos that once was visible. Reality will appear smaller, not because it has shrunk, but because causality has narrowed. This introduces a tragic element to cosmology. Knowledge is time-sensitive. There is a window during which certain truths are accessible. Miss that window, and those truths vanish forever behind the horizon. In this sense, the edge of reality is dynamic. It moves as the universe evolves. Regions that are part of our reality today will not be part of it tomorrow. Not because they cease to exist, but because they cease to matter to us causally. This reinforces a humbling lesson. Reality is not arranged for comprehension. Understanding depends on timing, location, and perspective. Our current era is unusually rich in information. We exist at a time when the universe is old enough to have structure, but young enough to still be observable. The speed of light is the silent architect of this situation. It defines not only what we can see, but what can ever be known. It enforces humility by ensuring that no observer can access the whole. So when we imagine what lies beyond the edge of reality, we must abandon images of walls and voids. Beyond the edge lies more reality, unfolding beyond any possible interaction with us. Not empty, not frozen, not meaningless, simply separate. This separation is not a flaw. It is a feature of a universe governed by consistent laws. Without a finite speed of information, reality would collapse into contradiction. With it, reality gains structure, order, and depth. The edge created by light speed is therefore not an enemy of knowledge. It is the reason knowledge is coherent at all. It shapes the universe into a place where causes precede effects, where histories make sense, and where reality, though incomplete to any observer, remains internally consistent. As we move forward, the next step is to confront an even deeper question. If reality is limited by causal horizons, does it have a shape at all? Is the universe finite, infinite, or something that defies both categories? Because once the speed of light defines how reality is partitioned, the next mystery is how big that reality truly is. The question of whether the universe is finite or infinite sits at the heart of human curiosity. It is one of the oldest questions ever asked, long before modern science existed, and yet it remains unresolved even today. When people ask what exists beyond the edge of reality, they are often unknowingly asking this very question: does reality end somewhere, or does it continue without limit? To ask whether the universe is finite is to ask whether there is a total amount of space, matter, and time. To ask whether it is infinite is to ask whether reality has no bounds at all. Both possibilities challenge intuition in different ways, and both have deep implications for how we understand existence. A finite universe suggests closure. It implies that reality is a complete object, something that could, at least in principle, be fully described. An infinite universe, by contrast, suggests that reality can never be exhausted, catalogued, or fully known. No matter how much we learn, there will always be more beyond. Historically, humans favored finiteness. Ancient cosmologies imagined domes, spheres, and layered heavens. Even when the universe expanded in scale, it often retained a boundary. Infinity was associated with chaos, divinity, or abstraction, not physical reality. Modern science disrupted this preference. When astronomers discovered that galaxies extend in all directions, the universe ceased to look like a contained structure. It began to resemble something open-ended. Yet openness alone does not guarantee infinity. Something can be vast and still finite. To understand this distinction, imagine the surface of a sphere. It has a finite area, but no edge. You can travel forever without encountering a boundary, yet the total surface is limited. Cosmologists consider similar possibilities for space itself. The universe may be finite in volume, but unbounded, meaning there is no edge to cross. If this is true, then the idea of an edge of reality becomes misleading. There would be no location where reality stops. Instead, space would curve back on itself in ways that are difficult to visualize. Reality would be self-contained but without borders. On the other hand, the universe could be infinite. Space could extend endlessly in all directions, containing infinitely many galaxies, stars, and regions. In such a universe, there is no total count of anything, no largest distance, no final structure. This idea is deeply unsettling. An infinite universe implies that every physically possible configuration occurs somewhere, given enough space. There may be regions identical to our own, copies of Earth, even copies of individual lives, not because of design, but because of sheer scale. Many resist this implication emotionally, but mathematics does not share human discomfort. The equations of cosmology allow infinite solutions as naturally as finite ones. The universe shows no obvious sign of an edge, no observable curvature that would demand finiteness. Current data is consistent with both possibilities. This uncertainty is not due to ignorance alone. It may be fundamentally undecidable. If the universe is much larger than the observable region, then its global structure may be forever hidden. We can measure local geometry, but global topology may lie beyond observation. This again blurs the idea of an edge. If we cannot determine whether reality is finite or infinite, then the edge may not be something that can ever be reached, even in theory. It becomes a question without an empirical answer. Yet the philosophical consequences remain. In a finite universe, reality has a total content. Even if unreachable, it is conceptually complete. In an infinite universe, reality is inherently incomplete from any perspective. No observer can ever claim to understand more than an infinitesimal fraction. Infinity also reshapes the meaning of rarity and significance. In a finite universe, events can be unique. In an infinite one, uniqueness becomes fragile. Given infinite trials, even the most unlikely events occur endlessly. This raises existential questions. If infinite versions of similar worlds exist, what does individuality mean? What does history mean? Does meaning dilute when repetition becomes inevitable? Some physicists argue that such questions are misplaced. Infinity may be a mathematical idealization, not a physical reality. Others argue the opposite, that rejecting infinity is an emotional response, not a scientific one. There is also a third possibility. The universe may be finite in some dimensions and infinite in others, or infinite in extent but finite in information, or structured in ways that do not fit classical categories at all. Reality may not conform to the binary choice humans prefer. Quantum gravity theories suggest space-time itself may be discrete at the smallest scales. If space and time are made of indivisible units, then infinity becomes more complicated. An infinite universe would require infinitely many such units. A finite one would require a maximum count. Yet, even discreteness does not eliminate infinity. An infinite grid is still infinite. The deeper issue is whether the laws of physics permit endless extension or enforce closure. Cosmic inflation complicates this further. Inflation suggests that space can grow faster than any signal can travel, potentially without limit. If inflation never completely stops everywhere, then new regions of space are constantly being created. Reality becomes not just infinite in size, but infinite in growth. In such a scenario, asking about the edge of reality becomes almost meaningless. Reality is not a static container. It is a process. Space itself is generated over time. There is no outer boundary, because expansion does not proceed into anything. It is not space expanding into emptiness. It is space expanding by redefining distances internally. This challenges common imagery. People imagine the universe expanding into a void. But expansion does not require an outside. It is the stretching of relationships within space. Asking what lies beyond expanding space assumes there is a background arena, but physics provides no evidence for such an arena. If space is all there is, then beyond space is not another place. It is an absence of spatial meaning. The question loses coherence. This does not mean the question is foolish. It means human language struggles to describe realities that violate everyday experience. Terms like beyond and edge come from spatial intuition. When applied to space-time itself, they may mislead. Yet humans persist because the intuition of an outside is powerful. We are used to containers. Rooms have walls, maps have borders, even ideas have limits. Infinity resists containment. This resistance produces a psychological tension. Part of us wants reality to be finite, orderly, and bounded. Another part senses that any boundary would require explanation. If reality ends, why there? What enforces the ending? What lies on the other side? A finite universe with an edge demands something beyond the edge, even if only as an abstract condition. An infinite universe avoids this problem by denying edges entirely, but at the cost of overwhelming scale. In this sense, infinity may be simpler. It removes the need for external explanation. Reality simply is, without boundary, no outside, no beyond. But simplicity does not guarantee truth. The universe does not care what feels elegant or comfortable. It follows rules we are still uncovering. Observationally, current measurements suggest space is very close to geometrically flat. This leans slightly toward infinite models, but does not prove them. A universe can be finite and still appear flat locally, just as the Earth appears flat to someone standing on a field. The deeper issue is that even if the universe is finite, its size may be so vast that it functions as infinite for all practical purposes. If the total extent is trillions of times larger than the observable region, then no experiment could ever distinguish it from true infinity. This leads to a strange conclusion. Whether the universe is finite or infinite may not matter operationally. Reality may behave as if it has no edge, regardless of its true structure. And yet, the human mind cannot let go of the question, because behind it lies something deeper than geometry. It lies a desire to know whether existence is complete or open-ended, whether reality is a finished story or an endless one. If reality is finite, then it is conceivable, at least abstractly, to imagine a total description. If reality is infinite, then incompleteness is permanent. No final theory can capture everything. There will always be more. This distinction affects how we think about knowledge itself. A finite reality invites the hope of final understanding. An infinite reality demands humility forever. As we stand now, science offers no final answer. Both possibilities remain open, and perhaps that is fitting. The question of finiteness or infinity may itself be part of the edge of reality, a place where human inquiry reaches its limit. What matters is not whether reality ends somewhere, but what its structure tells us about our place within it. A finite universe still dwarfs us. An infinite universe erases any claim to centrality entirely. Either way, the idea of an edge dissolves. Not because nothing lies beyond, but because beyond may not be a meaningful concept at all. In the next stage of this exploration, we move away from geometry and toward concept. Even if the universe has no physical edge, humans still speak of one. Why? What does the idea of an edge really mean in cosmology? And why does it persist, even when physics suggests it may not exist? The idea of an edge is deeply human. It comes from everyday experience, from walls, borders, horizons, and endings. When we apply this idea to the universe, we are not necessarily describing reality as it is, but translating the unknown into familiar language. In modern cosmology, The concept of an edge is less about a physical boundary and more about the limits of description, measurement, and meaning. Cosmologists rarely speak of an edge in a literal sense. Instead, they speak of horizons, limits, and breakdowns. These are not places you could travel to and touch. They are conditions under which current theories stop providing reliable answers. The edge of reality, in this context, is where explanation itself becomes uncertain. This shift is important. It reframes the question from where does the universe end to where does understanding end. The two are often confused, but they are not the same. Reality may continue smoothly while our models fail abruptly. One example is the singularity. Inside black holes and at the beginning of the universe, equations predict infinite densities and curvatures. These infinities are not believed to be physically real. They are signs that the theory has been pushed beyond its domain of validity. The singularity marks an edge of theory, not necessarily an edge of existence. This pattern appears repeatedly. Classical mechanics breaks down at atomic scales. General relativity breaks down at quantum scales. Quantum field theory struggles with gravity. Each time an edge appears, and each time deeper theories extend reality beyond it. This history teaches caution. Edges in physics often signal incomplete understanding rather than fundamental limits. What seems impossible under one framework becomes natural under another. However, not all edges are theoretical artifacts. Some limits may be intrinsic. The speed of light, for example, is not merely a feature of a theory. It is woven into the structure of space-time itself. Similarly, quantum uncertainty appears not as a technical flaw, but as a fundamental property of nature. Cosmology sits at the intersection of these two kinds of limits. Some boundaries may dissolve with better theories. Others may persist, no matter how advanced understanding becomes. The cosmic horizon is one such candidate. It is not expected to vanish with better instruments or deeper theories. It arises from the expansion of space and the finite speed of information. It is a structural feature, not a temporary obstacle. Yet even this horizon is not an edge in the everyday sense. It does not mark a place where something different happens. The laws of physics do not change at the horizon. Nothing dramatic occurs when a galaxy crosses it. It simply becomes unreachable. This makes the edge of reality invisible. There is no signpost marking where knowledge ends. The universe looks the same everywhere we can see. The edge is inferred, not observed. This invisibility contributes to misunderstanding. Popular imagination fills the gap with dramatic imagery. Walls of light, sudden emptiness, cosmic cliffs. In reality, there is no such spectacle. The universe does not announce its limits. Another source of confusion is language itself. Words like beyond, outside, and edge imply spatial relationships. But when applied to the universe as a whole, these words may have no clear meaning. If space includes all locations, then outside space is not a place. It is an absence of spatial definition. This creates a conceptual trap. The mind insists on imagining something beyond the universe because grammar allows it. But physics does not guarantee that such imagination corresponds to anything real. In modern cosmology, edges often appear as limits of predictability. There are regions of parameter space where small changes in initial conditions lead to vastly different outcomes. Chaotic systems amplify uncertainty. Beyond a certain point, prediction becomes meaningless even if the underlying laws are known. This kind of edge is epistemic rather than physical. Reality continues deterministically or probabilistically, but our ability to track it collapses. Weather systems offer a familiar example. The atmosphere obeys physical laws, yet long-term prediction is impossible. The early universe may have similar properties. Tiny quantum fluctuations magnified by inflation determine the large-scale structure we observe today. Beyond a certain point, the specific details are unknowable, not because reality is undefined, but because information has been erased or diluted. This introduces another kind of edge, the edge of recoverable history. Even if the universe is deterministic, its past may not be reconstructible beyond a certain time. Information is lost to horizons, entropy, and quantum effects. Black holes represent an extreme case. When matter falls in, information appears to disappear from the outside universe. Whether it is truly lost or encoded in subtle correlations remains an open question. Either way, the event horizon marks a boundary beyond which information cannot return. This makes black holes a local analogy for cosmic edges. They demonstrate how reality can continue internally while becoming inaccessible externally. Inside the horizon, physics proceeds. Outside, influence is cut off. These examples suggest that edges in cosmology are less about endings and more about separations. Separations between regions of influence, between scales of description, between what can be known and what cannot. This has philosophical implications. If reality includes regions forever beyond knowledge, then a complete description of existence may be impossible in principle, not just practically, but logically. Any theory we construct may describe only a portion of what exists. Some thinkers embrace this as a feature rather than a flaw. They argue that reality does not owe us completeness. Understanding may always be partial, and that partiality does not diminish truth. It simply defines its scope. Others resist this conclusion. They seek theories that eliminate edges, unifying all phenomena under a single framework. The dream of a final theory persists, a set of equations that describes everything that exists. Whether such a theory is possible remains unknown. Even if discovered, it may not eliminate edges of observation or computation. Knowing the laws does not grant access to all consequences of those laws. There is also the question of scale. Reality may be structured hierarchically, with emergent layers. Each layer has its own effective laws. Edges appear when moving between layers. What makes sense at one level becomes meaningless at another. This is seen in condensed matter physics, biology, and even economics. Macroscopic behavior emerges from microscopic rules, but cannot be easily reduced to them. The universe itself may operate similarly, with space-time and gravity emerging from deeper, non-spatial structures. If so, then the edge of reality may lie not in space, but beneath it, beneath space-time itself, beyond geometry, beyond duration, a domain where familiar concepts dissolve. This possibility is explored in quantum gravity research, where space-time is not fundamental. If space-time emerges from entanglement or information, then asking what lies beyond space-time is not like asking what lies beyond a wall. It is like asking what lies beneath a shadow. In this view, the edge of reality is a conceptual boundary, not a physical one. It marks where language, intuition, and mathematics begin to fail simultaneously. Yet even here, the word edge persists, because humans need markers. They need to know where understanding fades. edges provide orientation, even when they are abstract. The danger lies in reifying these edges, turning them into imagined places rather than acknowledging them as limits of description. When this happens, speculation can drift away from science and into fantasy. But careful speculation has value. It pushes theories to their limits, revealing where assumptions break. Asking about the edge of reality forces cosmology to confront its foundations. It asks what space is, what time is, what existence means when stripped of human perspective. It reveals that reality may not be a thing with boundaries, but a process with constraints. As this exploration continues, the next step is to move beyond abstract limits and examine specific proposals. If there is no simple edge, what do modern theories suggest exists beyond the observable universe? Not as metaphor, but as physical possibility. When cosmologists speak about what lies beyond the observable universe, they are not speculating wildly. They are extending well-tested theories to regions that cannot be directly observed. This distinction matters. What exists beyond our cosmic horizon is not fantasy. It is the natural continuation of known physics into domains cut off by distance and time. The simplest possibility is also the most conservative. Beyond the observable universe lies more universe that looks broadly like what we see here. More galaxies, more stars, more cosmic structure arranged according to the same physical laws. The same particles, the same forces, the same constants. From this perspective, the observable universe is not special. It is a typical region within a much larger whole. This idea follows directly from the cosmological principle, which states that on large scales, the universe is homogeneous and isotropic. In plain terms, it means the universe looks roughly the same everywhere when viewed at sufficiently large scales. There is no preferred center, no special direction, no unique location. If this principle holds beyond what we can see, then the universe does not suddenly change character at the horizon. There is no edge event, no transition. The horizon is simply the limit of our information, not a boundary in space. This alone answers part of the question. Beyond the edge of reality, as defined by observation, there is still reality operating normally. Galaxies form, stars burn, black holes grow. Cosmic expansion continues. Physics does not pause simply because we cannot watch. However, this conservative view may not be the whole story. The early universe underwent a period of rapid expansion known as inflation. Inflation was not just expansion, it was exponential expansion. Tiny regions of space were stretched to enormous scales in fractions of a second. One consequence of inflation is that regions of space that were once in causal contact were driven far apart. The observable universe today may represent only a small fraction of the region that existed before inflation ended. Beyond our horizon may lie regions that share a common origin with us, but evolved independently for most of cosmic history. Inflation also introduces the possibility that different regions of the universe ended inflation at different times. In some regions, inflation may have stopped earlier. In others, it may still be ongoing. This leads to a picture of the universe that is far more complex than a single expanding space. In this picture, our observable universe is like a bubble within a vast inflating background. Beyond our bubble, other bubbles may exist. Each bubble is a region where inflation has ended and conventional physics dominates. Between them lies inflating space that continues to expand at an extraordinary rate. This is not speculative fiction. It emerges naturally from many inflationary models, and it radically alters the meaning of beyond. Beyond the observable universe may not just be more of the same. It may be a fundamentally different environment. Inside our bubble, physical constants appear fixed. The speed of light, the strength of gravity, the masses of particles all have specific values, but inflationary theory allows for the possibility that these values could vary between different regions. If this is true, then beyond our observable universe, there may be regions where physics itself is different. Chemistry might not work the same way. Stars might not form. Stable matter might not exist. Reality would still exist, but in forms incompatible with life as we know it. This possibility forces a shift in perspective. The laws of physics we observe may not be universal. They may be local conditions, shaped by how and where inflation ended. What we call fundamental may be environmental. From our vantage point, this is deeply unsettling. It means that some of the deepest questions in physics may not have unique answers. Why does gravity have this strength? Why do particles have these masses? The answer may be not because it must be so, but because it happened to be so here. Beyond the observable universe, different answers may apply. Another possibility is that space beyond our horizon is structured differently on the largest scales. Even if local physics is the same, the global geometry of space may vary. There may be large-scale patterns, anisotropies, or topological features far beyond what we can measure. Space could loop back on itself. It could contain vast repeating structures. It could include regions connected in ways that do not fit simple three-dimensional intuition. From within our observable region, these features would be undetectable. We would see only a small patch that appears smooth and uniform. The larger structure would remain hidden. There is also the question of time. Beyond our horizon lies not only distant space, but distant past and future. Regions we cannot see now may become visible in principle, given infinite time, but cosmic expansion may prevent this. Some regions are not just far away, they are receding so fast that they will never become observable, even as the universe ages indefinitely. For all practical purposes, they are permanently beyond reality as experienced by us. Yet they continue to exist and evolve. Stars will live and die. Galaxies will collide. Black holes will evaporate. Entire cosmic histories will unfold without any connection to ours. This idea challenges a deeply ingrained assumption. Humans often assume that reality is defined by shared history. That to be real is to be part of a common story. Beyond the observable universe, this assumption fails. Reality fragments into countless independent stories. Another implication concerns probability. Many cosmological predictions rely on assuming typicality. We assume our region is not special. But if the universe beyond our horizon contains vastly more volume than the region we see, then most of reality lies elsewhere. What we observe may be statistically unrepresentative. Rare conditions may dominate locally while being insignificant globally. This complicates interpretation. Data from our observable universe may not reflect the broader cosmos. This issue becomes critical when discussing fine-tuning. The apparent precision of physical constants that allow complex structures has led some to argue for deeper explanations. Beyond the observable universe, there may be countless regions where constants differ and complexity never arises. In this view, our existence does not require special design. It requires only that some regions permit observers. we necessarily find ourselves in such a region, because no observers exist elsewhere to ask the question. This line of reasoning is controversial, but it arises directly from considering what exists beyond our observational edge. It shows how extending physics beyond observation reshapes not only cosmology, but philosophy. There is also a more radical possibility. Beyond the observable universe may lie regions not connected by space in any simple way. Some theories suggest that space-time itself may be a patchwork of domains connected through quantum processes. Entanglement, wormhole-like structures, or higher dimensional connections could link regions in ways that bypass ordinary distance. Such connections would not allow travel or communication in the usual sense, but they would imply that the universe is not a simple, continuous expanse. In this case, beyond the observable universe might not be far away. It might be adjacent in a higher dimensional sense, separated not by distance, but by structure. From our perspective, such regions would be completely hidden. No signal could reach us. No experiment could detect them directly. Yet their existence could influence fundamental physics indirectly through subtle effects on space-time or constants. This possibility blurs the boundary between cosmology and metaphysics, but it remains grounded in attempts to unify quantum mechanics and gravity. What all these scenarios share is a rejection of the idea that reality stops where observation stops. Beyond the observable universe lies continuation. Whether simple or complex, uniform or varied, accessible or not, reality does not terminate at our horizon. This has emotional consequences. Humans often imagine themselves at the center of existence, not spatially, but existentially. The idea that vast regions of reality exist entirely without reference to us undermines this intuition. Yet it also reinforces a profound idea. Existence is larger than meaning. The universe does not exist to be witnessed. It exists. This realization can feel alienating, but it can also be liberating. It frees reality from human projection. It allows the cosmos to be vast without justification. In this light, the observable universe is not a prison. It is a window onto a much larger structure that we infer but cannot see. What lies beyond that window may resemble what we know, or it may be radically different. Physics allows for both. Observation alone cannot decide. This uncertainty is not a weakness of science. It is a recognition of scope. Science describes what can be tested. When it extends beyond that domain, it does so cautiously, guided by theory rather than imagination. As we continue, the next step is to examine one of the most far-reaching consequences of these ideas. If reality extends beyond our horizon in varied forms, could there be multiple universes? Not metaphorically, but physically. And if so, what would that mean for the idea of reality itself? Inflation theory is one of the most powerful ideas in modern cosmology, not because it explains what we see today, but because it explains why the universe looks the way it does at all. It addresses problems that would otherwise seem mysterious, and in doing so, it pushes the concept of reality far beyond the observable universe. To understand inflation, we must return to the earliest moments of cosmic history. According to standard cosmology, the universe began in an extremely hot, dense state and has been expanding ever since. However, this simple picture leaves several puzzles unanswered. Why is the universe so large and uniform? Why does space appear nearly flat? Why do distant regions that have never been in contact look almost identical? Inflation was proposed as an answer. It suggests that shortly after the universe began, space underwent a brief but extraordinary period of expansion. During this phase, space itself expanded exponentially, doubling in size again and again in fractions of a second. This was not matter moving through space. It was space stretching everywhere at once. The effect of this expansion was dramatic. Regions that were once tiny and causally connected were blown up to enormous scales. Quantum fluctuations, originally microscopic, were stretched to cosmic sizes, becoming the seeds of galaxies and large-scale structure. Inflation explains why the universe appears smooth and uniform. It also explains why small irregularities exist. Without inflation, the universe would look radically different. But inflation also carries a deeper implication. If space can expand this rapidly once, there is no fundamental reason it could not do so again or continue doing so elsewhere. Many models of inflation predict that it does not end everywhere at the same time. In these models, inflation ends locally, creating regions like our observable universe where conventional physics takes over. But beyond these regions, inflation continues. Space keeps expanding at an enormous rate, spawning new regions endlessly. This scenario is known as eternal inflation. It implies that the universe is not a single expanding entity, but a vast, ever-growing structure containing countless regions where inflation has ended. Each of these regions is effectively its own universe. Our observable universe would be one such region, embedded in a much larger inflating background. Beyond our cosmic horizon lies not just more space, but a fundamentally different phase of space-time. In this picture, the observable universe is a bubble. Inside the bubble, expansion is relatively slow and structure forms. Outside the bubble, inflation continues, preventing structure from forming at all. The boundary between these regions is not a wall, but a transition between different physical regimes. This reframes the question of what lies beyond the edge of reality. Beyond our observable universe lies inflating space that will never become observable. It is expanding too fast for light from our region to ever reach it, or for light from it to ever reach us. These regions are not merely distant, they are causally disconnected in a permanent way. No event in our universe can influence them, and no event in them can influence us. Yet they are still part of physical reality. They obey laws, evolve in time, and contain energy. Their existence is inferred from the same theoretical framework that explains the structure of our universe. One of the most unsettling aspects of eternal inflation is its scale. If inflation never fully stops, then the total volume of inflating space grows without bound. New bubble universes form endlessly. Reality becomes not just vast, but effectively infinite in extent and diversity. This means that almost everything that can happen will happen somewhere, given enough time and space. Not just once, but endlessly. Reality becomes a generator of possibilities. Within this framework, our universe is not special in size or location. It is special only in that it permits complexity and observers. Countless other regions may exist where inflation ended differently, producing conditions hostile to structure. This leads to a profound shift in how cosmologists think about fundamental laws. What we observe as constants of nature may not be universal constants at all. They may be local outcomes of how inflation ended in our region. Different bubbles could have different values for particle masses, force strengths, or even the number of dimensions. Physics itself becomes environmental. This idea is deeply controversial, but it arises naturally from inflationary theory. Combined with modern particle physics, It does not require invoking metaphysics or speculation beyond established frameworks. It emerges when known theories are pushed to their logical conclusions. The idea that physical laws vary across regions challenges the traditional goal of physics. For centuries, physicists sought unique explanations, a single set of laws governing everything. Eternal inflation suggests that some features of reality may not have unique explanations. Instead of asking why the constants have their particular values, the answer may be that they vary across reality, and we observe the values compatible with our existence. This does not mean explanation ends, it shifts the focus. Physics explains the distribution of possibilities rather than selecting a single outcome. Beyond the observable universe, then, lies a landscape of realities, some similar to ours, many radically different, most likely barren and simple, unable to form stable matter or complex structures. From our perspective, these regions are forever hidden. No observation can confirm their existence directly. Their reality is inferred, not observed. This raises a philosophical challenge. Can something be considered real if it can never be observed? Even in principle, physics answers yes, as long as its existence follows from well-supported theories. After all, we accept the existence of the universe before recombination, even though we cannot see it directly. We accept the existence of black hole interiors, even though we cannot observe them. Reality is not limited to what can be seen. Inflationary regions beyond our horizon are similar. They are part of a theoretical structure that successfully explains observed phenomena. Rejecting them would require rejecting the framework that explains what we see. Yet this acceptance comes with discomfort. It implies that reality is vastly larger and more complex than anything accessible to us. It implies that our universe is one outcome among countless others. This undermines the intuitive idea that reality is singular and complete. Instead, reality becomes plural and generative. The edge of reality, in this view, is not an end. It is a boundary between phases of existence. Inside our bubble, time flows in a familiar way. Outside, inflation dominates, stretching space so rapidly that time itself behaves differently. Crossing this boundary is not possible. It is not a matter of travel or energy, it is a matter of cosmic history. Our region cooled and structured, others did not. This makes the edge asymmetrical. We can imagine what lies beyond by extrapolating theory, but we can never experience it. It is not just far away, it is inaccessible by definition. This raises questions about meaning and relevance. If most of reality is forever beyond us, does it matter? From a physical standpoint, yes. From a human standpoint, it challenges perspective. Human culture often equates importance with accessibility. What we can interact with feels real and significant. Inflationary cosmology breaks this association. It says existence does not require relevance. This realization can feel unsettling. It places humanity in a small, fragile region of a vast and indifferent reality. But it also provides context. Our universe is not isolated or arbitrary. It is part of a much larger structure governed by consistent principles. Even if we can never observe beyond our bubble, understanding that it exists reshapes our conception of reality. It expands the mental map of existence. In this sense, the edge of reality becomes a conceptual frontier, a place where physics meets inference, where observation gives way to extrapolation. Some critics argue that eternal inflation is unscientific, because it makes predictions that cannot be tested directly. Supporters respond that science has always dealt with unobservable entities as long as they arise from testable theories. The debate remains open, but the idea has already changed cosmology. It has reframed the universe not as a single object, but as a process, a continual unfolding of space and possibility. If inflation is correct, then beyond the observable universe lies an endlessly growing expanse of inflating space, punctuated by islands of structure like our own. Reality has no outer edge. It has phases, transitions, and domains. This means that the question, what exists beyond the edge of reality, has an unexpected answer. Not emptiness, not nothing, but more creation, more space, more potential universes. The edge, then, is not where reality ends. It is where our particular story begins to diverge from countless others. A boundary not of existence, but of narrative. As we move forward, the next step is to explore one of the most striking consequences of this picture. If inflation creates many regions, could some of them be fundamentally similar to ours? Could reality repeat itself? Could the universe, on the largest scales, be infinite and repetitive? The idea of a repeating universe emerges naturally once infinity enters the conversation. If space extends without limit and the laws of physics remain broadly consistent, then repetition is not just possible, it becomes unavoidable. Beyond the edge of our observable reality, the universe may not merely continue, it may repeat itself in ways that challenge the meaning of uniqueness, identity, and history. To understand this idea, we must separate emotional intuition from mathematical consequence. Humans experience repetition as rare and meaningful. Patterns repeat, but exact duplication feels extraordinary. In an infinite universe, this intuition fails. Infinity changes probability itself. If the universe is infinite in spatial extent and contains a finite number of possible configurations of matter within any given volume, then those configurations must repeat. This is not speculation. It is a direct implication of combinatorics. Given infinite trials and finite outcomes, repetition is guaranteed. Our observable universe contains an enormous amount of information, but it is not infinite. Particles have discrete states. Energy levels are quantized. Physical laws constrain how matter can arrange itself. Even if the number of possible configurations is unimaginably large, it remains finite. In an infinite universe, those configurations recur. Somewhere beyond our horizon, there would exist regions arranged identically to our own observable universe, not approximately exactly. The same galaxies, the same stars, the same planets, the same histories, unfolding in the same order. This conclusion feels absurd, even disturbing, but it follows logically. If certain assumptions hold, the discomfort comes from scale, not logic. Infinity is not intuitive. Some physicists argue that the universe is infinite and statistically homogeneous. If so, then repetitions are not optional. They are inevitable. The universe becomes a cosmic tiling of similar regions, each separated by vast distances beyond any possible interaction. These regions would not be copies in the usual sense. They would not be created by duplication. They would arise independently through the same physical processes. Chance, operating across infinite space, produces the same outcomes again and again. This idea reframes what exists beyond the edge of reality. Beyond our observational horizon may lie regions so similar that the difference between here and there becomes meaningless. Identity dissolves at cosmic scales. Yet this repetition does not imply synchronization. These regions are causally disconnected. They do not influence one another. They do not share a timeline. They simply exist in parallel, unfolding according to the same rules. This raises profound philosophical questions. If there are infinitely many regions identical to ours, then every possible outcome of events occurs somewhere. Every choice branches not metaphorically, but spatially. History becomes not a single path, but a distribution of outcomes. This should not be confused with many worlds' interpretations of quantum mechanics, which posit branching universes at every quantum event. The repeating universe idea requires no branching. It arises from spatial infinity alone. In this view, the universe does not split. It repeats. Some find this idea unsettling because it seems to undermine meaning. If everything that can happen does happen somewhere, what significance does any single event have? If identical versions of ourselves exist elsewhere, what does individuality mean? These concerns are understandable, but they arise from projecting human-scale values onto cosmic-scale structures. Meaning does not require uniqueness at the level of the entire universe. It requires coherence within a local narrative. Your experiences are meaningful because they are yours, embedded in a causal history that matters to you and those around you. The existence of distant duplicates does not alter that history. It does not interact with it. It does not diminish it. From a physical standpoint, identical regions elsewhere are no more relevant than fictional worlds. They exist, but they do not matter causally. This distinction between existence and relevance becomes critical. Infinite repetition does not collapse reality into redundancy. It expands it into multiplicity. However, not all cosmologists accept this conclusion. The repeating universe depends on several assumptions. One is that space is truly infinite. Another is that physical laws and constants are uniform across that infinity. A third is that the number of possible configurations within a finite region is finite. If any of these assumptions fail, repetition may not occur. For example, if physical laws vary across regions, then identical repetition becomes less likely. If the universe contains infinite information density, repetition may be avoided. If space is finite but unbounded, repetition may still occur, but in different forms. Inflation complicates this further. In eternal inflation scenarios, regions may not only differ in initial conditions, but in fundamental constants. This creates diversity rather than repetition. Reality becomes a landscape rather than a tiling. Yet, even in such landscapes, repetition can occur locally. Within regions where laws are similar, structures may recur. There is also a deeper issue. Repetition challenges the idea of randomness. If everything repeats infinitely, then randomness becomes a local phenomenon, not a global one. Outcomes are random within regions, but inevitable across infinity. This does not invalidate probability. It reframes it. Probability describes frequency within a finite domain, not uniqueness across an infinite one. From this perspective, probability is not about whether something happens, but how often it happens relative to other possibilities. This leads to a strange but consistent picture. In an infinite universe, everything physically allowed happens infinitely many times, but most of it remains forever disconnected. The edge of reality, then, is not a wall. It is a distance beyond which repetition becomes statistically inevitable. Yet this distance is incomprehensibly large. Estimates suggest that identical regions would be separated by distances vastly exceeding the observable universe, far beyond any horizon, far beyond any conceivable travel. These duplicates are not neighbors. They are mathematical consequences of infinity, not practical realities. There is also the question of time. Repetition in space does not imply repetition in time. The universe may not cycle through the same states globally. Entropy increases, histories diverge. Repetition occurs across space, not along a single timeline. This preserves the arrow of time locally, even if spatial duplication exists globally. Some have proposed even more radical ideas. If the universe is infinite in both space and time, then histories may repeat not just spatially, but temporally. After unimaginable durations, configurations could recur. This idea borders on speculation, but it highlights how infinity destabilizes intuition. Once finiteness is abandoned, repetition becomes difficult to avoid. However, cosmology remains cautious. Infinity is a strong claim. Current observations cannot confirm or deny it. Space may be finite, but extremely large. The universe may be infinite, but structured in ways that prevent exact repetition. The key point is not whether repetition occurs, but what its possibility reveals. It reveals that the universe beyond our observable reality may be governed by statistical inevitability rather than narrative uniqueness. This challenges human-centered views of existence. We prefer stories with beginnings, middles, and ends. Infinity offers distributions instead. Yet even within this vastness, local meaning persists. Causality, memory, and identity operate within regions. Repetition elsewhere does not interfere. In fact, the existence of repetition may be the price of consistency. A universe governed by simple, uniform laws extended across infinite space cannot avoid producing the same outcomes repeatedly. If this feels uncomfortable, it may reflect a mismatch between human intuition and cosmic scale, not a flaw in the idea itself. The repeating universe also reframes the edge of reality as a statistical boundary. Beyond a certain scale, novelty does not increase. Variation gives way to redundancy. Reality becomes self-similar, not because it is simple, but because it is vast. This is not visible from within any single region. From our perspective, the universe appears unique. Only by extrapolating beyond observation does repetition emerge. This again highlights the difference between observation and inference. What exists beyond the edge of reality is not directly experienced, it is deduced. And this deduction remains tentative. Cosmology is not finished. Future theories may alter this picture. Space may be finite. Laws may vary. Infinity may be replaced by something more subtle. But the repeating universe idea serves as a powerful reminder. Reality, when extended beyond human scale, behaves in ways that challenge narrative thinking. It suggests that the universe is not a story written once, but a pattern woven endlessly. If this is true, then beyond our observable reality lies not mystery in the sense of the unknown, but mystery in the sense of excess. Too much existence for any single perspective to contain. The edge of reality, in this context, is the point where uniqueness gives way to inevitability. As we continue, the next question deepens further. If space can repeat, could reality itself branch into parallel versions with different laws? Not just repetition of the same, but coexistence of the different. This leads us directly into the concept of the multiverse. and the possibility that reality is not one, but many. The idea of the multiverse represents one of the most radical extensions of modern cosmology. It goes beyond the claim that the universe is large or infinite. It suggests that reality itself may be plural. Not one universe with distant regions, but many universes existing simultaneously, each with its own properties, laws, and histories. To understand why physicists take this idea seriously, it is important to clarify what is meant by multiverse. It is not a single theory. It is a category of consequences that emerge from several independent lines of research. Inflation, quantum mechanics, and fundamental physics all point, in different ways, toward the possibility that reality contains more than one universe. One route to the multiverse comes directly from inflation. As discussed earlier, eternal inflation suggests that space continues expanding in some regions while inflation ends in others. Each region where inflation ends becomes a universe like ours. These universes are embedded in a larger inflating background and are causally disconnected from one another. In this picture, universes are not separated by ordinary space. They are separated by cosmic history. Each universe forms when inflation locally stops, cooling and allowing particles, forces, and structures to emerge. Beyond its boundary lies inflating space that prevents any interaction. These universes are sometimes called bubble universes. They are not created in a single moment. They form continuously as inflation proceeds. Reality becomes a constantly branching structure, producing universes the way stars produce light. Another route to the multiverse arises from quantum mechanics. At the smallest scales, physical systems do not have single outcomes. They exist in superpositions of possibilities. When measured, one outcome is observed, but the theory itself does not specify why that outcome occurs rather than another. One interpretation of this process suggests that all possible outcomes occur, but in separate branches of reality. Instead of probabilities collapsing into a single result, the universe splits into multiple versions, each realizing a different outcome. This idea is known as the many worlds interpretation. It does not require new equations. It takes the mathematics of quantum mechanics at face value. The price is ontological. Reality becomes enormously larger than what we experience. In this framework, the edge of reality is not spatial, it is quantum. Every interaction that has multiple possible outcomes leads to branching. Reality becomes a constantly diverging tree of histories. These branches do not interact. Once separated, they evolve independently. Each branch contains observers who perceive a single, consistent history. From within any branch, reality appears singular and complete. This is crucial. The multiverse does not feel like a multiverse from the inside. It feels like one world. A third route to the multiverse comes from attempts to unify fundamental forces. Theories that aim to describe physics at the deepest level often predict many possible vacuum states. Each vacuum corresponds to a different set of physical laws. In this view, the laws of physics are not unique. They are solutions within a vast space of possibilities. Different regions of reality may settle into different solutions. This is sometimes called the landscape. It suggests that reality contains an enormous number of possible universes, each defined by different constants, dimensions, and particle properties. Inflation provides a mechanism to populate this landscape. As inflation proceeds, different regions fall into different vacuum states, creating universes with different physics. This connects the multiverse to the problem of fine-tuning. The physical constants in our universe appear delicately balanced. Small changes would prevent stars, chemistry, or life. In a single universe framework, this fine-tuning demands explanation. In a multiverse framework, it becomes selection. Most universes are lifeless. A small fraction permit complexity. Observers inevitably find themselves in those regions. This does not prove the multiverse, but it shows why the idea has explanatory power. It turns a mystery into a statistical outcome. Critics argue that this is not explanation, but evasion. They argue that invoking unseen universes to explain observed parameters stretches science beyond its limits. Supporters respond that science has always inferred unseen structures when theories demand them. Atoms were once unseen, fields were once abstract, curved space-time was once unimaginable. Reality has repeatedly turned out to be larger than direct experience. The key question is not whether the multiverse feels strange, it is whether it follows logically from well-supported theories. At present, the answer remains uncertain. Some aspects of multiverse theory may be testable indirectly. Others may remain forever beyond observation. This raises a difficult issue. If something cannot be observed, even in principle, can it be considered part of science? Opinions differ. Some argue that testability is essential. Others argue that coherence, consistency, and explanatory power also matter. The multiverse sits at this boundary. It is not pure speculation, but it is not directly confirmable either. Yet, even as a hypothesis, it profoundly reshapes the concept of reality. Reality becomes not a single structure, but an ensemble, not a finished object, but a space of possibilities. This forces a re-evaluation of what it means to ask what exists. Existence may not be binary. Something may exist in some universes but not others. Laws may be local rather than universal. This challenges deeply rooted assumptions. Humans tend to think of reality as one world, one history, one set of rules. The multiverse breaks this unity. But unity may be a projection of perspective rather than a feature of existence. From within any universe, reality appears unified. From outside, it may not be. This again highlights the role of observers. Observation does not define reality, but it defines experienced reality. Each observer inhabits a tiny slice of the multiverse and experiences it as complete. The edge of reality, then, is not an outer boundary. It is the limit of a particular branch or bubble. Beyond it lie other realities, equally real but inaccessible. This inaccessibility is not due to distance or energy. It is structural. Universes in the multiverse do not share space-time. There is no path connecting them. This is why the multiverse does not violate conservation laws or causality within a universe. Each universe evolves according to its own internal rules. Yet, the idea raises unsettling questions. If many universes exist, what determines which one we inhabit is identity tied to a specific branch. Do other versions of ourselves exist elsewhere? These questions blur the line between physics and philosophy, but they are not meaningless. They reflect the implications of taking theories seriously. Some worry that the multiverse undermines the idea of scientific prediction. If everything happens somewhere, what does prediction mean? The answer is subtle. Predictions become statistical. They describe distributions of outcomes rather than single events. This shift already occurs in quantum mechanics and cosmology. The multiverse extends it. There is also a psychological resistance. Humans seek closure. The multiverse offers none. There is no final universe, no ultimate version. Reality becomes open-ended. Yet openness may be closer to truth than closure. The universe has repeatedly defied attempts to box it into simple forms. What lies beyond the edge of reality in the multiverse view is not emptiness or void, it is more reality. Different reality. Reality that does not intersect with ours, but exists alongside it. This does not diminish our universe. It contextualizes it. Our universe becomes one chapter in a much larger book. And like any chapter, it is meaningful within its own narrative, regardless of how many others exist. The multiverse does not say that nothing matters. It says that mattering is local, meaning arises within universes, not across the ensemble. This idea may feel cold, but it is also liberating. It frees reality from needing a single justification. Existence does not need to converge to one outcome to be real. The edge of reality, then, is not a wall. It is a boundary of participation. Beyond it lie universes we do not inhabit, histories we do not experience, laws we do not obey. And yet, through theory, we can glimpse their possibility. As we move forward, the next question becomes even more concrete. If multiple universes exist, could they ever interact? Could there be collisions, imprints, or traces? Or are they forever sealed off from one another? This leads us to the idea of bubble collisions and the search for evidence beyond our cosmic horizon. If the multiverse exists, the most natural next question is whether its components are completely isolated, or whether interaction between universes is possible in any form. While popular imagination often treats universes as sealed bubbles floating in nothingness, modern cosmology suggests a more subtle picture. Separation does not always mean total isolation. Under certain conditions, universes may collide, overlap, or leave traces of their encounters. This idea emerges most clearly from eternal inflation. In inflationary models, bubble universes form within a larger inflating space. Inflation ends locally, creating a bubble, while the surrounding space continues to inflate. Because inflation is ongoing, new bubbles continue to form, expanding outward at nearly the speed of light. These bubbles are not static. They grow, expand, and occupy regions of the inflating background. Given enough time, collisions between bubbles become possible, not inevitable, but allowed. A bubble collision is not like two objects colliding in ordinary space. It is a collision between regions of space-time itself. When two bubble universes meet, the interaction reshapes their internal structure. Energy is released along the collision boundary. Space-time geometry is distorted. Physical conditions inside each universe may be altered. From inside one of these universes, such a collision would not look like an external invasion. There would be no foreign objects entering from outside. Instead, the collision would appear as a large-scale disturbance imprinted into the fabric of space-time. This is a critical point. If universes collide, the evidence would not appear as something obviously alien. It would appear as anomalies in the early universe, subtle patterns in radiation, deviations from perfect uniformity. This is why cosmologists have considered the possibility that traces of bubble collisions might be detectable. The most promising place to look is the cosmic microwave background, the faint afterglow of the early universe. The cosmic microwave background is remarkably uniform, but not perfectly so. It contains tiny fluctuations in temperature and density. These fluctuations seeded the formation of galaxies and clusters. They are well explained by inflation and quantum fluctuations. However, if our universe experienced a collision with another bubble during its early history, it could leave a distinctive imprint. This imprint might appear as a circular pattern, an asymmetry, or an unusual correlation in the microwave background. Searches for such patterns have been conducted. Scientists have looked for circular temperature anomalies, unusual cold spots, and deviations from statistical isotropy. So far, no conclusive evidence has been found. This absence of evidence does not rule out bubble collisions. It may simply mean that collisions are rare, or that their signatures are subtle, or that our universe formed in a relatively quiet region of the inflating background. It may also mean that collisions occurred too early or too weakly to leave detectable traces. Inflation smooths out disturbances rapidly. A collision signature could be erased before it becomes observable. There is another possibility. Collisions may occur in ways that do not affect observable physics. If two bubbles have very different properties, the collision boundary may be unstable or quickly disappear. This uncertainty highlights an important feature of multiverse ideas. They often predict phenomena that are in principle observable, but extremely difficult to detect. The edge of reality becomes experimentally elusive, not conceptually vague. Even without direct evidence, studying bubble collisions is valuable. It forces cosmology to define what interaction between universes would even mean. It pushes theory to its limits. The notion of bubble interaction also challenges the idea that universes are completely separate. If they can collide, then they are not fully isolated. They are part of a larger structure that allows interaction under specific conditions. This larger structure is not ordinary space. It is the inflating background itself. Universes are embedded within it, like regions of a phase transition in a larger medium. This analogy matters. In condensed matter physics, phase transitions occur within a material. Different phases coexist, interact, and sometimes collide. Inflationary cosmology suggests space-time itself may behave similarly. In this view, universes are not absolute entities. They are emergent regions within a deeper framework. Their boundaries are not walls, but interfaces. This reframes the edge of reality yet again. The edge of our universe is not the edge of existence. It is the boundary of a particular phase of space-time. Beyond it lies not nothing, but a different regime with different properties. Inflating space may not allow atoms, stars, or observers, but it is still physical. It still has energy, dynamics, and structure. The idea of interaction also raises the possibility of indirect influence. Even if universes cannot exchange matter or information in the usual sense, their formation may not be independent. The inflating background sets conditions. The rate of inflation, the nature of the vacuum, and the underlying field dynamics influence how bubbles form. Universes may share statistical properties, even if they never interact directly. This suggests a kind of meta-reality, a level of description above individual universes, governing their creation and distribution from within any universe. This meta-level is invisible. This invisibility does not make it unreal. It simply makes it inaccessible to direct observation. Some theorists have speculated about more exotic forms of interaction, quantum entanglement between universes, higher dimensional connections, wormhole-like links. These ideas remain speculative. They stretch current theory and lack experimental support. But they illustrate how the question of what lies beyond reality leads naturally to deeper layers of structure. One must be careful here. Speculation without constraint easily becomes fiction. The strength of cosmology lies in its discipline. Theories are judged by consistency, mathematical coherence, and connection to observation. Bubble collision research respects this discipline. It does not claim evidence where none exists. It explores what would follow if inflationary models are correct. This distinction matters. The edge of reality is not a free space for imagination. It is a region where theory is stretched, not abandoned. There is also a philosophical implication. If universes can collide, then the concept of a universe as a self-contained totality breaks down. Universes become events rather than absolutes. This challenges language. Words like universe and reality imply totality. But in multiverse scenarios, totality shifts to a higher level. What we call a universe becomes a local structure within something larger. This mirrors historical shifts. The solar system was once thought to be the universe, then the galaxy, then the observable universe. Each time, what was thought to be total became local. The multiverse may represent the next such shift. If so, then the edge of reality is not a single boundary, but a series of horizons. Each horizon marks the limit of a framework. Beyond it lies a deeper structure that reframes what came before. Bubble collisions would be the first empirical hints of such a deeper structure. They would provide evidence that our universe is not isolated. The lack of evidence so far keeps this idea speculative. But speculation grounded in theory is how science progresses. It is also worth noting that absence of collision evidence may be meaningful. It could suggest that our universe formed in a region of inflating space with low bubble density, or that inflation ended in a way that suppresses collisions. This would still be information about the larger structure. The search for bubble collisions also illustrates a broader theme. The edge of reality is not something we will cross physically. It is something we probe indirectly through subtle patterns and constraints. This requires patience and humility. It requires accepting that some aspects of reality may remain forever inferred rather than observed. Yet inference is not weakness. It is how much of science operates. We infer the existence of dark matter, dark energy, and the interior of stars. Reality often reveals itself through effects rather than direct contact. Bubble collisions, if they occurred, would be effects of interactions beyond our universe. Even if they never occurred, the theoretical possibility reshapes how we think about cosmic isolation. Our universe may be alone in practice, but not alone in principle. This distinction is crucial. Practical isolation does not imply ontological isolation. The edge of reality, then, is not a border enforced by existence, it is a border enforced by structure. Structure determines what can interact, what can influence, what can be known. Beyond that structure lies more reality, governed by the same underlying rules but arranged differently. As we move forward, the next question becomes even more abstract. If universes can exist as separate regions, what is the role of dimensions? Could there be dimensions beyond the ones we experience, providing new directions for reality to extend? This leads directly into the idea of extra dimensions and higher dimensional space. The idea of extra dimensions does not come from imagination or philosophy. It comes from mathematics. When physicists attempt to describe reality at its deepest level, the equations often demand more dimensions than the 3 of space and 1 of time that we experience. These additional dimensions are not added for creativity. They appear because the math stops working without them. To understand why extra dimensions matter, we must first clarify what a dimension is. A dimension is a direction in which movement or change is possible in everyday life. Space has 3 such directions: left-right, forward-backward, up-down. Time adds another, allowing change from past to future. These dimensions feel complete because human experience is limited to them. Yet experience is not a reliable guide to fundamental structure. Humans once experienced the Earth as flat and stationary. Deeper understanding revealed curvature and motion hidden from perception. Extra dimensions may be similar, present everywhere, yet inaccessible. The earliest serious attempt to introduce extra dimensions into physics came from attempts to unify forces. Gravity behaves differently from other forces. It is far weaker, yet acts over vast distances. Physicists sought a framework where gravity and electromagnetism could be described together. When an extra spatial dimension was added mathematically, something remarkable happened. Gravity and electromagnetism emerged from the same structure. What appeared as separate forces in 4 dimensions became aspects of geometry in higher dimensions. This result was not poetic. It was precise. Equations simplified. Patterns emerged. The idea suggested that forces might not be fundamental. They might be shadows of higher dimensional geometry. This insight did not immediately transform physics. The extra dimension had to be hidden to match observation. It could not be large or obvious. It had to be compact, curled up so tightly that it escaped detection. This introduced a crucial idea. Dimensions do not need to be large to be real. They can be microscopic, folded into every point of space. Imagine a long cable viewed from a distance. It appears one-dimensional, a simple line. Up close, it reveals thickness and circular structure. An ant walking on the cable experiences more dimensions than a human observer far away. In this analogy, humans are distant observers of reality. We perceive only large dimensions. Smaller dimensions may exist, but remain invisible because we cannot access the scales at which they unfold. Modern theories build heavily on this idea. Attempts to unify all forces consistently almost always require extra dimensions. Not 1 or 2, but many. These dimensions provide the mathematical room needed to accommodate complex interactions. This does not mean physicists believe in extra dimensions lightly. It means the alternatives fail. Without additional dimensions, the equations become inconsistent or incomplete. This places extra dimensions in a strange position. They are not observed, yet they are implied by the most successful attempts to describe reality at its deepest level.
If extra dimensions exist, then reality is not confined to the space-time we experience. What we call the universe would be a slice of a higher dimensional structure.
Beyond our familiar reality would not be emptiness, but additional directions of existence. This reframes the question of the edge of reality dramatically. The edge may not be far away in space. It may be right here, folded into every point, hidden by scale and structure. This idea challenges intuition. Humans instinctively imagine beyond as distant. Extra dimensions suggest beyond can be adjacent, yet inaccessible. Why would these dimensions be hidden? One explanation is energy. Accessing smaller dimensions may require energies far beyond what we can achieve. Particles moving through these dimensions would manifest as extremely massive states in our 4-dimensional world. This means that extra dimensions could influence physics subtly without being directly visible. Gravity, for example, may leak into extra dimensions, weakening its apparent strength in our space. This could explain why gravity is so much weaker than other forces. If gravity spreads into higher dimensions, while other forces are confined, then our experience of gravity would be diluted. This idea has been explored seriously as a solution to long-standing puzzles. This confinement leads to another concept. Our universe may be a lower dimensional surface embedded in higher dimensional space. Matter and forces may be restricted to this surface, while gravity alone explores the full structure. In this picture, we are not inhabitants of all dimensions. We are confined to a subset. Reality extends beyond us, but we are pinned to a slice of it. This makes the edge of reality a boundary of access rather than existence. Beyond our accessible dimensions lie regions we cannot enter, not because they are far, but because the laws of physics restrict us. Such restrictions are not arbitrary. They emerge from the dynamics of fields and forces. Particles may be bound to certain dimensions due to how they interact with underlying structures. This is not unlike how electrons are bound to atoms. The rest of space exists, but electrons cannot occupy just any location. Their allowed states are constrained. Extra dimensions may be real, but inaccessible in the same way, not forbidden by logic, but by dynamics. This idea has radical implications. If higher dimensions exist, then reality is vastly richer than the visible universe. Events may occur beyond our dimensions that have indirect effects here. For example, collisions or vibrations in higher dimensions could influence the behavior of gravity. The expansion of the universe might be affected by geometry beyond space-time. Dark energy might reflect dynamics occurring in unseen dimensions. These ideas remain speculative, but they are not arbitrary. They arise from attempts to explain observed phenomena that resist simpler explanations. Extra dimensions also blur the distinction between inside and outside. If higher dimensions permeate our space, then beyond reality is not a separate region. It is an extension woven through what we already inhabit. This challenges the language of edges entirely. There is no boundary to cross. There is only depth to access. From this perspective, the universe may resemble a projection, a lower dimensional image cast by a higher dimensional structure. What we see is consistent and complete within its domain, but incomplete relative to the whole. This idea resonates with earlier themes. The observable universe is not the entire universe. Space-time may not be the entire reality. At each level, what appears fundamental may turn out to be emergent. Extra dimensions also offer a new way to think about unification. Forces that appear distinct in 4 dimensions may unify naturally in higher dimensions. Particles may be modes of vibration or geometry rather than fundamental points. This shifts the meaning of what exists. Existence becomes geometric rather than material. Reality becomes structure rather than substance. Such abstraction is uncomfortable. Humans prefer tangible entities, but physics has repeatedly shown that abstraction reveals deeper truth. Fields replaced particles. Space-time replaced absolute space and time. Extra dimensions may be the next step, yet caution is necessary. Mathematical consistency alone does not guarantee physical reality. Many mathematically consistent structures exist that do not describe our universe. The challenge is to find observable consequences, subtle deviations in gravity, missing energy signatures, effects at extremely small scales. So far, no conclusive evidence has been found. This absence does not falsify extra dimensions. It constrains their size and properties. They must be small, hidden, or structured in ways that evade detection. This again highlights a pattern. The deeper layers of reality become harder to access, not because they are unreal, but because they operate at scales or in directions removed from experience. If extra dimensions exist, then the edge of reality is not a frontier of space, it is a frontier of dimensionality. Beyond our familiar reality lies a multidimensional structure that contains it. We are not at the center of existence, we are embedded within it. This has philosophical consequences. It suggests that reality is layered, that what we perceive is a cross-section, that deeper truths may be orthogonal to experience. It also reframes questions about origin and destiny. The beginning of our universe may correspond to a transition or configuration in higher dimensions. Its end may be influenced by dynamics beyond space-time. This does not imply purpose or design. It implies structure. Structure does not require intention. It requires consistency. Extra dimensions offer a way for reality to be both finite in experience and infinite in structure. Our accessible universe may be limited, while the full reality is vast beyond comprehension. This possibility satisfies a recurring tension. The universe feels both complete and incomplete. Extra dimensions allow both to be true. Yet, until evidence appears, this remains a hypothesis, a powerful one, grounded in theory but unconfirmed. Still, its implications cannot be ignored. If reality includes more dimensions than we experience, then asking what exists beyond the edge of reality becomes misguided. Reality does not end. It extends in directions we cannot sense. The edge is not a wall, it is a limit of access. As we continue, the next step is to examine a specific framework that makes extensive use of extra dimensions and has reshaped modern theoretical physics. A framework where reality is built not from particles alone, but from extended objects existing in higher dimensional space. This leads directly into string theory and the hidden architecture of existence. String theory emerges not as a single idea, but as a response to failure. When physicists attempted to combine quantum mechanics with gravity using conventional methods, the mathematics broke down. Infinities appeared that could not be removed. Predictions became meaningless. Something fundamental was missing. String theory was proposed as a solution to this breakdown. Its central claim is deceptively simple. The fundamental constituents of reality are not point-like particles, but tiny, vibrating strings. Everything we observe arises from different vibrational modes of these strings. This change from points to strings has profound consequences. Point particles interact at exact locations, leading to infinite quantities when gravity is involved. Strings, having length, smear interactions over space, softening infinities and restoring consistency. This alone would be significant. But string theory does more. When the equations are written down carefully, they refuse to work unless the universe has extra dimensions, not optionally, necessarily. In most versions of string theory, space-time must have 10 or 11 dimensions for the mathematics to be consistent. 4 are familiar, the others are hidden. This requirement is not imposed by aesthetic preference. It is demanded by internal logic. Without extra dimensions, the theory collapses. This places string theory in a unique position. It does not merely allow extra dimensions, it predicts them. If string theory is correct, then the reality we experience is not the full reality. It is a lower dimensional slice of a higher dimensional structure. What we perceive as particles are vibrations of strings moving through dimensions we cannot see. These extra dimensions are not vast like ordinary space. They are compact, curled up at scales far smaller than atoms. Every point in space contains them. They shape the behavior of strings and therefore determine the properties of particles. This leads to a remarkable conclusion. The properties of matter may be geometric, particle masses, charges, and interaction strengths could be determined by the shape and topology of hidden dimensions. Reality, at its deepest level, would be architecture rather than substance. This reframes the question of what exists beyond the edge of reality. Beyond space-time may lie structure that defines space-time itself. Space and time would not be fundamental, they would be emergent. String theory suggests that what we call space-time arises from deeper entities interacting in higher dimensions. Gravity, in this view, is not a force in the usual sense. It is a manifestation of geometry and vibration. This idea aligns with earlier insights from relativity, where gravity is curvature of space-time rather than a force acting within it. String theory extends this idea further. Space-time itself may be secondary. This has dramatic implications for the concept of an edge. If space-time is emergent, then asking what lies beyond space-time is like asking what lies beyond a shadow. The shadow is not the full object. It is a projection. Beyond our experienced reality would lie the underlying structure casting the projection. String theory also introduces new kinds of objects beyond strings. Membranes, higher dimensional surfaces, and extended entities appear naturally in the theory. These objects can have various dimensions existing within the higher dimensional space. This suggests that reality is populated not just by particles, but by extended structures interacting across dimensions. Some of these structures could be large relative to the hidden dimensions, shaping the universe in subtle ways. Others could be microscopic, influencing physics only at extreme energies. This complexity makes string theory difficult to test. Its predictions often occur at scales far beyond current experimental reach. This has led to criticism. A theory that cannot be tested risks drifting into metaphysics. Yet string theory continues to attract serious attention because it unifies gravity and quantum mechanics in a consistent framework. No other known theory has achieved this convincingly. String theory also connects seemingly unrelated ideas. Black holes, entropy, information, and geometry become aspects of the same underlying structure. Insights from string theory have deepened understanding even in areas not directly related to its original goals. This suggests that even if string theory is not the final description of reality, it may be pointing in the right direction. One of the most striking consequences of string theory is the sheer number of possible solutions it allows. Different shapes of hidden dimensions produce different physical laws. The number of possible configurations is enormous. This leads to the idea of a landscape of solutions. Each solution corresponds to a different universe with different physical constants and properties. This landscape connects directly to multiverse ideas. String theory does not predict a single universe. It predicts many possible universes. Inflation provides a mechanism to realize them physically. In this combined picture, reality consists of a vast landscape of possible universes, each realized somewhere through inflationary processes. Our universe is one realization among many. This is a dramatic departure from traditional physics. Instead of explaining why the universe has certain properties uniquely, physics explains why many possibilities exist. The explanation for why we observe our particular universe becomes statistical rather than deterministic. This shift is deeply unsettling to some. It challenges the idea that science should provide unique answers. Others argue that it reflects reality more honestly. String theory also reshapes the concept of what exists beyond the edge of reality by introducing the idea of duality. In some cases, two very different-looking theories describe the same physics. A universe with gravity in one description can be equivalent to a universe without gravity in another description. A higher dimensional theory can be equivalent to a lower dimensional one. This suggests that dimensionality itself may not be fundamental. Reality may admit multiple equivalent descriptions, none of which is privileged. This undermines the idea of an absolute edge. If reality can be described in different ways, then boundaries depend on description, not existence. One particularly striking example is the idea that information about a volume of space can be encoded on its boundary. This implies that the interior is not independent of the surface. Reality behaves like a projection. In such a framework, asking what lies beyond the edge becomes ambiguous. The edge may contain all the information needed to describe what appears beyond it. This does not mean beyond does not exist. It means that existence may be relational rather than absolute. String theory therefore challenges the basic categories humans use: inside and outside, fundamental and emergent, simple and complex. It suggests that reality is layered, interconnected, and context-dependent. Yet string theory remains incomplete. It lacks a single definitive formulation. Many versions exist, many questions remain unanswered. This incompleteness mirrors the theme of this documentary. Reality itself may not be neatly packaged. Understanding may always be provisional. String theory also highlights the limits of human intuition. The mathematics is abstract, high-dimensional, and far removed from sensory experience. Understanding it requires abandoning everyday concepts. This makes communication difficult. Metaphors break down. Language strains. Yet, this difficulty does not imply meaninglessness. It implies depth. String theory proposes that the universe we experience is a surface phenomenon. Beneath it lies a richer structure that generates it. If this is correct, then beyond the edge of reality lies not emptiness, but foundation. The edge would not be a boundary between something and nothing. It would be a boundary between description levels. We would be inhabitants of an emergent layer, perceiving reality as fundamental when it is not. This realization is humbling. It suggests that even our most basic intuitions may be contingent. It also offers a strange comfort. If reality is deeper than it appears, then mystery is not a failure of understanding, it is an invitation. String theory does not claim to have reached the bottom. It claims that the bottom may be deeper than we thought. This aligns with the recurring pattern of science. Each time we think we have reached the foundation, a deeper layer emerges. The edge of reality recedes. As we move forward, the next step is to examine an even more concrete idea that arises from higher dimensional theories. The idea that our universe may be a surface within a higher dimensional space. Not metaphorically, but physically. This leads directly into the concept of brains and the possibility that reality itself is layered like a stack of worlds. The concept of brains takes the idea of extra dimensions and gives it physical structure. Instead of imagining dimensions as abstract directions alone, brain theory suggests that reality itself may be layered. Entire universes could exist as surfaces embedded within higher dimensional space, coexisting without direct awareness of one another. A brain is a multidimensional object. Its dimensionality can vary. Some brains may be one-dimensional, like strings. Others may be two-dimensional surfaces or higher dimensional volumes. Our universe, according to some models, could be a three-dimensional brain embedded in a higher dimensional space. In this picture, everything we observe, matter, light, forces except gravity, is confined to the brain. Particles are bound to it. Interactions occur within it. From our perspective, this confinement is invisible. It simply appears as the natural structure of reality. Gravity behaves differently. It is not confined in the same way. It can propagate into the higher dimensional space beyond the brain. This provides a potential explanation for one of the deepest puzzles in physics: why gravity is so weak compared to other forces. If gravity spreads into extra dimensions while other forces remain trapped on the brain, then its apparent weakness is an illusion. It is not intrinsically weak. It is diluted across a larger space. This idea has been explored seriously because it connects abstract theory to observable phenomena. Deviations in gravitational behavior at small scales could reveal the presence of extra dimensions and brains. So far, experiments have not detected such deviations, but the constraints help refine models. Brains must be arranged in ways that hide their effects at accessible energies. Brains also introduce a new way to think about what exists beyond the edge of reality. Beyond our universe may lie other brains. Entire worlds existing parallel to ours, separated not by distance in space, but by position in higher dimensions. These parallel brains could be extremely close in a higher dimensional sense, yet completely invisible to us. No light can cross the separation. No particles can travel between brains. The separation is not spatial in the ordinary sense. This creates a striking possibility. Reality may be crowded with worlds, stacked like pages in a book, each unaware of the others. This idea differs from the multiverse of inflation. Here, universes are not separated by cosmic expansion. They coexist within the same higher dimensional structure. Their separation is geometric, not temporal. Interaction between brains is usually suppressed, but not necessarily impossible. Under certain conditions, brains could influence one another through gravity or other subtle effects. Some models suggest that collisions between brains could occur. Such a collision would be catastrophic. It could release enormous energy and radically reshape space-time. One speculative idea proposes that the Big Bang itself was the result of a brain collision. Two higher dimensional surfaces collided, injecting energy into our brain and triggering expansion. This idea is not widely accepted, but it illustrates how brain theory reframes cosmic origins. The beginning of our universe may not be an absolute beginning. It may be an event within a larger structure. If so, then what exists beyond the edge of reality includes not only other universes, but the space in which universes reside, a higher dimensional arena where brains move, interact, and evolve. This arena is sometimes called the bulk. The bulk is not empty. It contains geometry, energy, and possibly fields that govern the behavior of brains. From our perspective, the bulk is completely hidden. We cannot see it. We cannot travel into it. Yet it may determine fundamental properties of our universe. This again shifts the meaning of beyond. beyond reality is not outside existence, it is outside accessibility. Brain models also allow for asymmetric realities. One brain may have different physical laws from another. Particle content, force strengths, and dimensionality could vary. This makes reality highly plural, not just many universes, but many kinds of universes. Yet, these universes would not be arranged in a simple hierarchy. None is more real than another. Each is complete within its own domain. This undermines the notion of a privileged universe. Our reality would not be central or fundamental. It would be one layer among many. This idea resonates with earlier shifts in human understanding. Earth was not the center of the solar system. The solar system was not the center of the galaxy. The galaxy was not the center of the universe. Brain theory suggests the universe itself may not be central. This is a recurring theme. Each expansion of understanding displaces human centrality. Brains also complicate the idea of dimensionality. Dimensions may not be uniform across reality. Some may be accessible in one universe and inaccessible in another. This raises questions about what it means to exist in a dimension. Dimensional access becomes a property of a universe, not a universal feature. It also raises questions about causality. Events on one brain may influence another indirectly through the bulk. Such influence would be subtle and difficult to detect, but not forbidden by theory. This opens the door to speculative ideas about hidden influences. Unexplained phenomena in our universe could, in principle, be effects of structures beyond our brain. Most physicists approach such ideas with caution. Extraordinary claims require extraordinary evidence. Brain theory provides a framework, not confirmation. Yet the framework itself is valuable. It expands the conceptual space of cosmology. It shows how reality could be structured in ways far beyond everyday intuition. Brains also force a reconsideration of boundaries. The edge of our universe would not be a place where space ends. It would be a boundary of confinement. Beyond that boundary, space continues. But we are not part of it. This is similar to how fish experience water. The water does not end at the surface. The fish's world ends there. From this perspective, humans may inhabit a cosmic aquarium. Beyond our perceived reality lies a larger environment we cannot enter. This analogy is imperfect, but it captures the asymmetry. The larger structure exists regardless of our awareness. Brain theory also suggests that reality is stratified. There may be multiple levels of description, each valid within its domain. What we call fundamental may be emergent from a deeper layer. What we call beyond may be closer than we think. This again undermines the idea of a final edge. Reality may not terminate, it may simply change character. The edge of reality becomes a change in rules rather than a cessation of existence. This view is consistent with much of modern physics. Laws change with scale. Phases change with conditions. Boundaries mark transitions, not endings. Brains provide a way to formalize this idea cosmologically. They also reintroduce an ancient intuition in a new form. The idea of layered worlds has appeared in mythology and philosophy across cultures. Brain theory strips away myth and replaces it with mathematics. This does not validate myth. It shows that human intuition sometimes anticipates structure, even when details are wrong. The challenge now is evidence. How could brains be detected? Possible signals include deviations in gravity at small distances, missing energy in particle collisions, or cosmological signatures imprinted in the early universe. So far, none have been observed conclusively. But absence of evidence is not evidence of absence. Brain theory remains a candidate framework, not a confirmed description. Yet its implications are profound. If brains exist, then what lies beyond the edge of reality is not abstract speculation, it is physical structure beyond our confinement. We would be inhabitants of a surface, unaware of the space in which it floats. This realization reshapes humility. We are not just small in size. We may be small in dimensional access. The universe we experience may be only a slice of what exists, and beyond that slice lies a reality we can infer but not enter. As this exploration continues, the next step is to confront an even deeper question. If our universe may be embedded within something larger, could the entire universe itself be contained within something else? Not just dimensions beyond, but a hierarchy of containment. This leads us to ask whether our universe could exist inside a larger structure entirely, and what that would mean for the idea of reality. The idea that our universe could exist inside something larger pushes cosmology to its conceptual limits. It asks not merely what lies beyond the observable universe, or beyond space-time, but whether the entire cosmos we inhabit is itself a contained structure, not metaphorically, but physically. If true, this would mean that what we call reality is a subsystem of a deeper reality. This idea initially feels absurd because humans instinctively treat the universe as the ultimate container. By definition, the universe is everything. To suggest that it exists inside something else appears to misuse language, yet history shows that such intuition has failed before. The Earth was once everything, then the sky, then the galaxy. Each time, what was thought to be total turned out to be local. Physics does not forbid containment. It forbids only certain kinds of containment. Space cannot be embedded inside space in the same way objects are embedded within rooms. But space-time could be embedded in a higher dimensional structure. Geometry allows this. From this perspective, our universe would not be floating inside another universe like an object in a box. It would be a region, a configuration, or a phase within a larger framework. Containment would be structural, not spatial in the everyday sense. One way to think about this is through analogy. Consider a whirlpool in a river. The whirlpool has structure, boundaries, and internal dynamics. It can be studied as a distinct system. Yet it exists entirely within the river. It is not separate from the river. It is a pattern within it. Our universe could be similar. A stable pattern within a larger reality. Space-time, particles, and forces would be features of that pattern, not the whole. This idea appears in several theoretical contexts. In some models of quantum gravity, space-time emerges from more fundamental degrees of freedom. These degrees of freedom do not live in space-time. Space-time is something they generate collectively. If this is correct, then the universe is not fundamental. It is emergent. What exists beyond it is not another place. It is the substrate from which it arises. This substrate may not resemble anything familiar. It may not have space, time, or matter as we understand them. It may be informational, mathematical, or relational in nature. This challenges the idea of an edge entirely. If space-time itself is emergent, then there is no meaningful sense in which space-time has an outside. Asking what is outside space-time is like asking what is outside a pattern. The pattern exists within something else, but that something else is not a place. This view aligns with developments in quantum information theory, where space-time geometry appears linked to patterns of entanglement. Distances, connectivity, and even dimensionality may arise from how information is correlated. In such models, the universe is not a container of information, it is an expression of information. This reframes the question of existence. What exists fundamentally may not be objects, but relationships, not things, but connections. If reality is relational at its core, then containment becomes a matter of structure rather than location. The universe could be one relational structure among many. Another approach to this idea comes from black hole physics. Studies suggest that information about what falls into a black hole is not lost, but encoded in subtle correlations on its boundary. This implies that a lower dimensional surface can encode a higher dimensional volume. This raises a striking possibility. Our universe itself could be encoded on a boundary of a higher dimensional structure. What we experience as volume may be a projection of something more fundamental. In this view, the universe is not inside something else in the ordinary sense. It is derived from something else. This possibility undermines the notion of a final layer. If space-time emerges from something deeper, then that deeper layer may itself emerge from something else. Reality becomes hierarchical. This hierarchy does not necessarily extend infinitely. It may terminate at a fundamental level, but from our perspective, there may be several layers between experience and foundation. Each layer would have its own effective laws, concepts, and limitations. What seems fundamental at one level becomes emergent at the next. This pattern is familiar in science. Temperature emerges from particle motion. Solidity emerges from electromagnetic interactions. Life emerges from chemistry. None of these are illusions. They are real at their level. Space-time itself may be similar. Real, but not fundamental. If this is true, then the edge of reality is not something we approach by traveling farther. It is something we approach by probing deeper, by understanding how familiar structures arise. This has implications for cosmology. The beginning of the universe may not be the beginning of existence. It may be a transition, a reconfiguration, a phase change within a deeper system. The Big Bang, in this view, is not a creation event. It is a boundary in description. Our equations break down there not because nothing existed, but because space-time itself ceased to be a useful concept. What existed before the Big Bang may not be describable in spatial or temporal terms, not because it is mystical, but because those concepts did not apply. This again challenges human intuition. We think in time and space because we live within them. Imagining existence without them is difficult. Yet difficulty does not imply impossibility. Mathematics routinely describes structures that defy visualization. If the universe exists inside something larger, then our sense of totality is an illusion born of perspective. We experience all that we can interact with and mistake that for all that exists. This has philosophical consequences. It suggests that ultimate reality may be permanently beyond full comprehension, not because of technological limits, but because our cognitive tools are adapted to emergent layers, not foundations. Yet, this does not render inquiry meaningless. Understanding emergent layers has immense value. We do not need to understand quarks to build bridges. We do not need to understand quantum gravity to understand stars. Knowledge is layered, like reality itself. The idea of containment also reshapes existential questions. Meaning does not require fundamentality. A novel written on paper is meaningful, even though the paper is not the story. Our universe can be meaningful even if it is not ultimate. This counters a common fear that if reality is larger than our universe, then our existence is diminished. In fact, it is contextualized, not negated. A painting is not less meaningful because it hangs in a gallery rather than floating in void. If anything, being part of a larger structure can enrich understanding. It connects local experience to a broader framework. However, this view also demands humility. It suggests that even the universe itself may not be the final word, that our most basic assumptions may one day be reframed. This humility has always accompanied scientific progress. Certainty shrinks as understanding deepens. The idea that our universe could exist inside something else is not a claim of fact. It is a logical possibility emerging from serious attempts to understand reality at its deepest level. It is neither proven nor dismissed. It remains a frontier idea, but its implications are consistent with a recurring theme. Every time we have assumed we reached the ultimate layer, we discovered another beneath it. This suggests a pattern. Reality may not have a single edge, it may have many transitions. What we call beyond may simply be another layer of description, governed by different rules. In this light, the question, what exists beyond the edge of reality, transforms. The answer may be not another place, but another way of existing. And if that is true, then the edge of reality is not something to cross, it is something to reinterpret. As we move forward, the next step is to examine a dimension that does not fit neatly into space or containment at all time. If reality has layers and hierarchies, what does time mean within them? Could time itself be bounded? Could there be a beyond time? This leads us to one of the deepest questions in physics and philosophy. What exists beyond time itself? Time feels fundamental because we live inside it. Every thought, every memory, every observation unfolds along its flow. We cannot step outside it. We cannot stop it. We cannot move backward through it. Because of this, time feels like the deepest layer of reality. Yet modern physics increasingly suggests that time may not be fundamental at all. It may be emergent, directional only in certain contexts, and possibly absent at the deepest level of existence. To ask what exists beyond time is therefore not a poetic question, it is a serious, scientific, and philosophical one. If time has limits, then reality may extend into domains where time, as we understand it, does not apply. In classical physics, time is absolute. It flows uniformly, independently of what happens in space. This view is intuitive and closely matches human experience. Events happen in sequence. Causes precede effects. The past is fixed, the future is open. This view was shattered by relativity. Time is not universal. It depends on motion and gravity. Clocks tick at different rates depending on speed and gravitational potential. There is no single cosmic clock ticking for the entire universe. This alone suggests that time is not a simple background parameter. It is intertwined with space, forming space-time. Geometry determines how time flows. Yet even space-time may not be fundamental. Attempts to unify relativity with quantum mechanics often run into a problem. Time behaves very differently in each framework. In quantum mechanics, time is external. It is not something that fluctuates or becomes uncertain. It is a parameter against which change is measured. In general relativity, time is dynamic. It can stretch, slow, and warp. When these two frameworks are combined, the concept of time becomes unstable. Equations describing the universe at the deepest level often lack time entirely. They describe relationships between configurations, not evolution through time. This leads to a startling possibility. At the most fundamental level, the universe may not evolve in time at all. It may simply exist as a whole. Change and flow may emerge only when viewed from within certain subsystems. This idea is known as the timeless view of reality. In this view, time is not an ingredient of the universe. It is a perspective that arises when parts of the universe interact in particular ways. To understand this, consider a book. The entire story exists at once. The beginning, middle, and end coexist. Yet a reader experiences the story sequentially, page by page. The flow of time is not in the book itself, it is in the act of reading. The universe may be similar. The full structure may exist timelessly. Observers, embedded within it, experience time because of how information is processed locally. This analogy is imperfect, but it captures a key idea. Time may be emergent from correlation, memory, and causality, not fundamental existence. If this is true, then asking what exists beyond time is like asking what exists beyond the act of reading. The answer is not another moment, it is the structure that gives rise to moments. This view finds support in the study of entropy. The arrow of time, the distinction between past and future, is closely tied to entropy increase. Systems evolve from ordered to disordered states. This gives time its direction. But entropy increase depends on initial conditions. It depends on the universe starting in a highly ordered state. Physics does not require this. It simply observes it. This suggests that the arrow of time is not fundamental. It is contingent. It arises because of how the universe began, not because time itself demands it. If the universe began in a low entropy state, then time appears to flow forward. If it began differently, the arrow could be absent or reversed. This again suggests that time is not a universal feature of reality, it is a property of certain histories. This becomes especially relevant when considering the beginning of the universe. At the Big Bang, our equations suggest that time itself begins. Asking what happened before becomes problematic. Before implies time. If time began at the Big Bang, there is no before. Yet, this conclusion depends on taking space-time as fundamental. If space-time is emergent, then the Big Bang may not be the beginning of existence. It may be the boundary of applicability for time. What existed before the Big Bang may not be describable as earlier. It may be orthogonal to time entirely. This leads to the idea of a timeless phase of reality, a domain where change does not occur in the familiar sense, where there is no past or future, only structure. From such a domain, time could emerge as a derived concept when certain conditions are met, when systems become sufficiently complex, when correlations form, when memory becomes possible. This idea appears in various approaches to quantum gravity. In these approaches, the fundamental description of reality involves relationships between states rather than evolution through time. Time appears only when a subset of variables is used as a reference. One part of the system plays the role of a clock relative to another. This relational view of time means that time is not a background. It is a comparison. It exists only between systems. If this is correct, then beyond time lies not chaos or nothingness, but a deeper order without temporal labels. This has implications for the fate of the universe. If time is emergent, then its end may also be emergent. Scenarios like heat death describe what happens as entropy increases and structure dissolves. Time continues to exist, but nothing interesting happens. But in a deeper sense, the end of time may occur when correlations break down, when no subsystem can function as a clock for another, when everything becomes maximally disordered. At that point, time would not end with an explosion or collapse, it would fade, not because reality ceases, but because change loses meaning. Beyond that point, reality may still exist, but not as a sequence of events. It would exist as a static or timeless structure. This challenges the idea that existence requires time. Perhaps existence simply is. Time is how certain parts of existence experience change. This idea also reframes questions about eternity. Eternity is often imagined as infinite time, endless duration. But timeless existence is not endless time, it is the absence of time altogether. This is difficult to imagine, because imagination itself unfolds in time, yet difficulty does not imply impossibility. Mathematics routinely handles timeless structures. Equations do not evolve, they simply are. Their implications can be explored, but the structure itself is static. Reality at its deepest level may be similar. Dynamic appearance may arise from static structure. This idea also affects how we think about causality. Cause and effect are time-based concepts. If time is emergent, then causality may be emergent too. At the fundamental level, relationships may not be causal, they may simply coexist in a consistent structure. Causality emerges when time emerges. This suggests that the ultimate foundation of reality may be a causal, not random, but not ordered by before and after. This again challenges intuition. Humans rely on causality to make sense of the world. Removing it feels like removing logic itself. Yet quantum mechanics already challenges classical causality. Correlations exist that cannot be explained by local cause and effect. Deeper structures may challenge it further. Asking what exists beyond time therefore leads to a profound conclusion. Beyond time may lie the foundation of reality itself, not another era, not another timeline, but a domain where temporal concepts do not apply. This does not mean that time is illusory. Illusions do not obey precise laws. Time obeys laws extremely well. It is real within its domain. It means that time may be contextual rather than absolute. This contextuality mirrors earlier themes. Space may be emergent. Laws may be local. Universes may be plural. Time may be relational. Each step removes an assumed absolute and replaces it with a structure dependent on conditions. This pattern suggests that the edge of reality is not a place or a moment. It is the limit of applicability of certain concepts. Space works here, not there. Time works here, not there. Causality works here, not there. Beyond those limits, reality does not end. Our language does. This realization is both unsettling and liberating. Unsettling because it dissolves familiar anchors. Liberating because it allows reality to be deeper than imagination. When people ask what exists beyond the edge of reality, they often expect something exotic, another universe, another dimension, another realm. What may exist instead is something more radical: existence without time, structure without sequence, order without flow. This does not mean that time is meaningless. It means that time is a feature of our layer of reality, not the foundation. Our experiences, histories, and lives are real within time. They matter within time. Timelessness does not negate them. Just as the existence of atoms does not negate the reality of mountains, the existence of timeless structure does not negate the reality of moments. The universe may be layered. Time exists in some layers, not in others. The edge of time may therefore mark a transition between layers, not an end. This brings us to a critical point. If space and time may both be emergent, then what we call reality may be built from something even more abstract. The next step is to explore one of the most provocative ideas arising from this line of thought: the possibility that reality at its deepest level is not made of matter or energy, but of information itself. If so, then beyond space and time lies not emptiness, but code, structure, and relation. This leads us directly to the idea of informational reality and the possibility that the universe is fundamentally computational in nature. The question of what existed before the beginning of the universe is one of the most persistent and misunderstood questions in cosmology. It arises naturally from human intuition. Beginnings imply causes. Events imply prior events. Time, as we experience it, always stretches backward. So when we are told the universe had a beginning, the mind immediately asks what came before. Yet, this question may be fundamentally flawed. Not because it is foolish, but because it assumes that time existed before the universe. Modern physics increasingly suggests that this assumption may be wrong. To understand why, we must first clarify what is meant by the beginning of the universe. In standard cosmology, the universe began in a hot, dense state, often referred to as the Big Bang. This is not an explosion in space, it is an expansion of space itself. Distances between points increased rapidly from an extremely compact state. As we trace this expansion backward using known laws of physics, densities and temperatures rise. Eventually, equations predict a singularity, a point where quantities become infinite and the laws of physics break down. This singularity is often called the beginning of time. But singularities are not believed to be physical objects. They are signals that a theory has been pushed beyond its domain of validity. When equations yield infinities, it usually means something deeper is missing. The Big Bang singularity is likely not a literal beginning of existence. It is the boundary beyond which our current theories cannot reliably describe reality. This distinction is crucial. The beginning of the universe in our models may mark the beginning of space-time as we know it, not the beginning of everything. If time itself emerged at the Big Bang, then asking what happened before is like asking what is north of the North Pole. The concept ceases to apply. This does not mean nothing existed. It means existed before may not be a meaningful phrase. Yet many physicists believe that something did exist prior to the Big Bang, in a sense that does not rely on time as we understand it. Several serious proposals explore this idea. One possibility is that the universe did not begin, but transitioned. Our expanding universe may have emerged from a prior phase of reality, not earlier in time, but differently structured. In some models, the universe undergoes cycles. Expansion follows contraction. Big bangs follow big crunches. The universe rebounds rather than begins. In such models, the Big Bang is not the first event. It is a bounce, a transition from a contracting phase to an expanding one. Time may extend through this transition, but its direction may change. Entropy may reset or behave differently across cycles. These models face challenges. Entropy tends to increase, making exact cycles difficult yet modified versions remain under study. Another possibility is that the universe emerged from a quantum state at extremely small scales. Quantum effects dominate. Space-time may fluctuate wildly, losing its classical meaning. In this view, before the Big Bang there was no smooth space-time. There was a quantum regime where geometry itself was uncertain. The universe did not emerge from nothing. It emerged from a quantum structure. This structure would not be located in time. Time would arise only after the universe expanded and cooled enough for classical space-time to form. In such models, the beginning of time is not a creation event. It is a phase change. This is similar to how temperature emerges when many particles interact. Temperature does not exist for a single particle. It emerges statistically. Time may be similar. It emerges when enough degrees of freedom align in a particular way. Another class of ideas suggests that the universe is eternal into the past, but not in the way human intuition imagines. Instead of a single timeline extending infinitely backward, reality may consist of many branches, regions, or configurations without a global temporal ordering. In such a reality, our universe would be one branch where time flows in a particular direction. Other branches may exist without time or with different temporal structures. This again dissolves the idea of before as a universal concept. Some proposals suggest that the universe was born from a fluctuation, not a fluctuation in time, but a fluctuation in a timeless background. Quantum systems can exhibit transitions without external time parameters. Change can be relational rather than temporal. In this sense, the universe may not have been caused by something earlier. It may have emerged as a configuration within a larger structure. This challenges deeply held intuitions about causality. Humans expect every event to have a prior cause, but causality itself may be emergent. At the deepest level, reality may not operate by cause and effect. It may simply have constraints and relationships. What we perceive as causes may be patterns within those relationships. This idea feels unsettling because it removes the comfort of explanation by sequence, yet it may be closer to how reality actually works. Another possibility is that the universe is self-contained. Its existence does not require an external cause. It exists because it exists. This sounds circular, but physics already accepts similar principles. The laws of mathematics do not have causes. They are structures that exist timelessly. Physical reality may be anchored in similar structures. In this view, the universe is not caused, it is instantiated. This does not imply design or intention. It implies necessity. Certain structures exist because they are consistent. This idea aligns with approaches that treat reality as fundamentally mathematical. Physical existence becomes a manifestation of abstract consistency. If this is true, then asking what existed before the universe becomes a category error. The universe is not an event within time. It is a realization of a structure. Time exists within the universe, not the other way around. There is also a more modest possibility. The universe may have begun in time, but the question of before is simply unanswerable, not because it is forbidden, but because no information survives from earlier phases. Cosmic inflation, entropy increase, and horizon effects may have erased all traces of prior conditions. Even if something existed before, it left no imprint accessible to us. This would make the beginning of the universe an epistemic boundary. Beyond it, reality may exist, but knowledge cannot reach. This again highlights a recurring theme. The edge of reality often coincides with the edge of recoverable information. What existed before the beginning of the universe may be real, but unreconstructable. This is not unusual. Much of reality is like this. We cannot reconstruct the exact microstate of yesterday's air molecules. We accept this without existential discomfort. The early universe may be similar, just on a cosmic scale. Yet the question persists, because beginnings feel special. They feel explanatory. Humans want origins to anchor meaning. Physics does not share this need. It describes how systems behave, not why they exist in an ultimate sense. When physics encounters a boundary like the Big Bang, it does not declare creation. It declares incompleteness. This distinction is often lost in popular discussion. The Big Bang is described as the beginning of everything, when it is more accurately the beginning of our ability to describe the universe using known laws. This misinterpretation feeds confusion about what existed before. The honest answer from science is not nothing. It is unknown. But unknown does not mean unknowable. Theories continue to evolve. New frameworks may extend understanding beyond the Big Bang. Yet even if future theories describe a pre-Big Bang phase, the deeper question may remain: why that phase exists at all? This question may not have a scientific answer, not because science is weak, but because the question may not be well defined. Existence itself may not admit a why in the way human language expects. This is difficult to accept because humans seek narrative. Beginnings, causes, purposes. Reality may not operate narratively. It may operate structurally. The universe may exist because a certain structure exists. No earlier, no later, just existence. If this is the case, then what existed before the beginning of the universe is not an earlier thing. It is the underlying structure that allows universes to exist. This structure may be timeless, it may be mathematical, it may be informational, it may be something we do not yet have language for. What matters is that the beginning of the universe may not be the beginning of reality. It may be the beginning of our story. This perspective reframes the question of the edge of reality. The edge is not a moment where existence starts or stops. It is a boundary of description. Beyond that boundary lies something that does not fit our categories. This does not diminish the reality of the universe. It deepens it. It suggests that our universe is not arbitrary or isolated, but connected to a deeper framework. This connection may never be fully understood, but partial understanding is still understanding. Science does not require final answers to be meaningful. It progresses by extending boundaries. The question of what existed before the universe may remain open indefinitely, not because it is meaningless, but because it points toward the deepest layer of reality, and that layer may resist full articulation. As we move forward, the next step is to examine another aspect of reality that seems to dominate the universe yet remains invisible: dark matter and dark energy. If most of the universe is made of things we cannot see, then perhaps the edge of reality is not far away at all, but embedded within the cosmos itself, shaping everything without revealing itself directly. When astronomers measure the universe, they discover a paradox. Almost everything that exists is invisible. Stars, planets, gas, and dust. The entire luminous cosmos make up only a small fraction of reality. The vast majority of the universe consists of components that do not emit light, do not absorb it, and do not interact with matter in familiar ways. These components are known as dark matter and dark energy, and together they dominate cosmic behavior. This realization fundamentally alters the idea of what lies beyond the edge of reality. The edge may not be far away in space or time. It may be embedded within the universe itself, shaping everything while remaining hidden from direct perception. Dark matter was inferred, not observed. Galaxies rotate faster than visible matter alone can explain. Clusters of galaxies bend light more strongly than their luminous mass allows. Large-scale structure forms in patterns that require additional gravitational influence. Something unseen must be present. This unseen component behaves like matter. It has mass, it exerts gravity, but it does not interact electromagnetically. It does not shine, glow, or reflect. It passes through ordinary matter almost entirely unaffected. Dark matter forms vast halos around galaxies, scaffolding cosmic structure. Without it, galaxies would not form as they do. Stars would not remain bound. The universe would look radically different. Yet, despite its dominance, dark matter has never been directly detected. Decades of experiments have searched for it. Underground detectors, particle accelerators, space-based instruments. So far, no definitive signal has been found. This absence of detection does not imply non-existence. The gravitational evidence is overwhelming. It implies that dark matter interacts extremely weakly with ordinary matter. This makes dark matter a boundary phenomenon. It exists fully within our universe, yet lies beyond most forms of interaction. It is part of reality, but not part of experience. Dark energy is even more mysterious. While dark matter pulls matter together through gravity, dark energy appears to do the opposite. It drives the accelerated expansion of the universe. Observations of distant supernovae revealed that cosmic expansion is speeding up. Galaxies are not just moving apart, they are accelerating away from one another. Something is counteracting gravity on the largest scales. This something is called dark energy. It permeates all of space. Unlike matter, it does not clump. It remains uniform even as the universe expands. Dark energy dominates the energy content of the universe. It determines its fate. Whether the universe expands forever, tears itself apart, or settles into a cold, empty state depends on the nature of dark energy. Yet, dark energy is even less understood than dark matter. It may be a property of space-time itself, a vacuum energy, a manifestation of deeper physics. This raises a profound possibility. What we call empty space may not be empty at all. It may be filled with energy that shapes cosmic evolution. If so, then the edge of reality is not a boundary of objects, it is a boundary of interaction. Dark energy exists everywhere, yet interacts only through gravity. This challenges the intuitive idea that reality is made of things. Reality may be made of fields, properties, and dynamics that do not correspond to objects at all. Dark matter and dark energy together suggest that most of reality is invisible not because it is distant, but because it is subtle. This invisibility is not due to technological limitation alone. It may be intrinsic. These components may not interact in ways that allow direct detection. This, again, blurs the distinction between known and unknown. We know dark matter and dark energy exist through their effects. We do not know what they are. This is a recurring pattern in science. Effects precede understanding. Gravity was used centuries before its mechanism was understood. Atoms were inferred long before they were observed. Dark matter and dark energy may follow a similar path, or they may represent a new category entirely. Some physicists have proposed that dark matter and dark energy are signs that our understanding of gravity is incomplete. Perhaps gravity behaves differently at large scales. Perhaps space-time itself has additional degrees of freedom. If so, then dark components may not be components at all. They may be manifestations of deeper structure. This possibility ties dark matter and dark energy to earlier themes: extra dimensions, emergent spacetime, higher level structure. Dark matter could be matter moving through dimensions we cannot access. Dark energy could be pressure arising from geometry beyond spacetime. These ideas remain speculative, but they illustrate how invisible components push inquiry beyond familiar frameworks. Another possibility is that dark matter consists of entirely new particles, particles that interact only through gravity and perhaps weakly through other forces. If so, then reality includes an entire sector of matter that rarely interacts with ours, a hidden world overlapping our own, sharing space but not interaction. This would mean that reality is layered even within the same spacetime. Visible matter and dark matter would coexist, largely unaware of each other. This coexistence would be peaceful but profound. Galaxies would be shaped by matter we cannot see. Motion would be governed by invisible hands. Dark energy, if it is a property of vacuum, suggests that emptiness itself is active. Space would not be a passive stage, it would be a participant. This again challenges intuition. We think of nothing as absence. Physics suggests nothing may be something. This has implications for the edge of reality. Perhaps there is no sharp boundary between something and nothing. Perhaps reality transitions smoothly from matter to fields to properties. Dark matter and dark energy may represent intermediate layers, not objects, not void, but something else. Their existence also humbles human perception. Everything we see, every star and galaxy, is a minority component. Most of reality does not announce itself with light. This suggests that what we experience is not representative. It is biased toward what interacts with our senses. This bias shapes intuition. We imagine reality as luminous and solid. In truth, it may be dark and diffuse. This realization shifts the edge of reality inward. The unknown is not beyond the cosmos, it is embedded within it. Dark matter and dark energy are reminders that the universe still hides its essence. Not in distant realms, but in plain sight. Their study may reveal deeper laws, new symmetries, new dimensions, new ways of thinking about existence. Or they may reveal that some aspects of reality are permanently indirect, known only through influence. This would not diminish science. It would define its scope. Science does not require direct access to describe reality. It requires consistent explanation of effects. Dark components also influence cosmic destiny. If dark energy continues to dominate, the universe will expand faster and faster. Galaxies will drift beyond horizons. The observable universe will shrink in content. In the far future, observers may see only their local galaxy group, unaware of the wider cosmos that once existed. This would make the edge of observable reality closer over time, not because reality shrinks, but because access fades. Dark energy thus creates a moving edge, one that advances inward. This introduces a poignant idea. Knowledge itself has a window. Certain truths are accessible only at certain times in cosmic history. We happen to exist during a period when the universe is observable. This is not guaranteed. It is contingent. Dark matter and dark energy therefore shape not only structure, but epistemology. They determine what can be known and when. This deepens the meaning of the edge of reality. It is not just spatial or temporal. It is informational. Beyond certain limits, information cannot be recovered. Beyond others, it never reaches us. Dark components define these limits. As research continues, dark matter and dark energy may turn out to be keys to deeper layers of reality. They may connect to quantum gravity, extra dimensions, or emergent spacetime. Or they may introduce entirely new principles. Either way, they show that reality is not exhausted by what we see. The visible universe is a surface phenomenon. Beneath it lies a vast, unseen structure that governs everything. The edge of reality, then, is not where the universe ends. It is where light stops telling the full story. As we move forward, the next step is to explore regions where even space-time itself breaks down. Places where gravity overwhelms, geometry and reality becomes extreme black holes. If dark matter and dark energy hide reality quietly, black holes hide it violently. Understanding them may reveal whether edges of reality can exist locally, not just cosmically. Cosmic voids are among the largest structures in the universe, yet they are defined by absence rather than presence. They are vast regions of space containing very little matter, few galaxies, and minimal radiation. At first glance, they appear empty, irrelevant, and uninteresting. In reality, they may be some of the most important environments for understanding what lies beyond the familiar layers of reality. Voids occupy most of the volume of the universe. Galaxies, clusters, and filaments form a web-like structure, and between these filaments lie enormous cavities stretching hundreds of millions of light-years across. These cavities are not completely empty, but they are close to it by cosmic standards. Because voids contain so little matter, they behave differently from dense regions. Gravity is weaker, interactions are rarer, cosmic evolution proceeds more slowly. In these regions, the universe approaches its most primitive and unstructured state. This makes voids natural laboratories for probing the foundations of reality. In dense regions, complexity hides simplicity. In voids, simplicity dominates. One of the most important features of voids is that they amplify the influence of dark energy. Where matter is sparse, the repulsive effect driving cosmic expansion becomes more apparent. Voids expand faster than denser regions, growing larger over time. This accelerated expansion stretches space inside voids, making them even emptier over billions of years. Matter drains from voids into filaments, leaving behind regions increasingly dominated by dark energy. In this sense, voids are previews of the universe's future. As expansion continues, more of the cosmos will resemble today's voids. Structure will thin out. Isolation will increase. This raises an unsettling possibility. The far future of the universe may be void-like on all scales. Galaxies isolated, stars burned out, space dominated by emptiness and expansion. In such a universe, reality would still exist, but interaction would be rare. Meaning, as defined by complexity and connection, would be difficult to sustain. Voids, therefore, represent not just spatial emptiness, but a potential endpoint of cosmic evolution. Yet voids are not entirely empty. Quantum fields still exist. Dark energy still permeates space. Space-time geometry still operates. Reality does not vanish when matter disappears. This highlights an important idea. Emptiness is not nothingness. The absence of objects does not imply the absence of reality. Voids may be closer to the baseline state of the universe than dense regions. Galaxies and stars may be local deviations from a more fundamental emptiness. This reverses intuition. Instead of seeing voids as holes in reality, we may see matter as an interruption in an otherwise sparse cosmos. This perspective aligns with quantum field theory. Even the vacuum is not empty. It seethes with fluctuations, virtual particles, and energy. Fields exist everywhere, even where particles do not. Cosmic voids may therefore be places where reality is closer to its ground state, not devoid of existence, but minimally structured. This makes voids ideal places to search for subtle deviations from known physics, modifications to gravity, effects of extra dimensions, variations in dark energy behavior. In dense regions, such effects are masked by complexity. In voids, they may become detectable. Some theories predict that gravity behaves differently in low-density environments. If gravity weakens or strengthens subtly in voids, it could signal physics beyond general relativity. This again suggests that the edge of reality is not a distant frontier. It may be found in the quietest regions of the universe. Voids also raise questions about observation. Most of what we know about the universe comes from luminous objects. Stars and galaxies tell stories through light. Voids tell stories through silence. Interpreting silence is harder. Absence of signal must be inferred indirectly. This makes voids epistemologically challenging. Yet this challenge mirrors the broader theme of hidden reality. Dark matter, dark energy, extra dimensions, and emergent space-time all operate largely through absence rather than presence. Voids are the spatial manifestation of this pattern. There is also a deeper philosophical implication. Humans associate meaning with presence. Something matters because it is there. Voids challenge this association. They matter because of what they lack. This forces a redefinition of significance. Reality is not only about objects. It is about structure, distribution, and dynamics. Voids shape how matter moves. They influence galaxy formation. They affect cosmic expansion. Their emptiness has consequences. This mirrors earlier insights. What is not there can matter as much as what is. Voids also challenge the idea of an edge. One might imagine that beyond the last galaxy lies nothing. Voids show that nothing is not beyond, it is everywhere. The universe does not end in emptiness. It is mostly empty already. This suggests that the edge of reality is not a transition from something to nothing, it is a transition from complexity to simplicity. Beyond the structured universe lies a simpler state, not absence, but minimal differentiation. This simplicity may be closer to the fundamental nature of reality. If so, then understanding voids is not about understanding what is missing. It is about understanding what remains when complexity fades. This has implications for cosmology and philosophy alike. It suggests that the universe may not be built from things, but from fields and geometry, with things emerging locally. Voids represent regions where emergence is weak. They may also reveal how reality behaves without observers. Life requires structure. Voids do not support life, yet they exist and evolve regardless. This reinforces a recurring lesson. Reality does not require observers to be real. Voids also invite speculation about whether they could host exotic phenomena, rare events, unusual physics, perhaps even new kinds of structure beyond current imagination. Because voids are so large and so empty, even rare processes could occur somewhere within them. However, there is no evidence that voids harbor anything beyond known physics. Their value lies in their purity, not their exoticism. They strip the universe down to its essentials. In doing so, they help clarify what reality is without decoration. This clarity is crucial when asking about the edge of reality. To know where reality might end, one must understand what remains when almost everything is removed. Voids show that even when matter and light are scarce, reality persists. Space expands, fields fluctuate, laws operate. There is no point at which reality fades into nothingness. Instead, reality thins out. This thinning suggests that the universe does not have an edge in the traditional sense. It does not stop, it becomes simpler. Simplicity, not emptiness, may be the true asymptote of existence. This insight reframes the edge of reality as a limit of complexity rather than existence. Beyond the dense, luminous cosmos lies a realm dominated by vacuum, expansion, and minimal structure. This realm is not beyond reality. It is reality in its most stripped-down form. Voids, therefore, act as bridges between the visible universe and deeper layers of existence. They remind us that reality does not announce itself with spectacle. It persists quietly, even when almost nothing happens. As we move forward, the next step is to examine places where reality becomes extreme rather than minimal, places where gravity overwhelms structure, information seems to vanish, and space-time itself breaks down. Black holes. If voids reveal reality at its simplest, black holes reveal it at its most intense. Understanding them may show whether reality can have local edges, where known laws cease to apply. Black holes are the most extreme objects known to physics. They are not merely massive bodies. They are regions where space-time itself is pushed beyond familiar limits. Inside them, gravity becomes so intense that the normal structure of reality appears to collapse. For this reason, black holes are often described as local edges of reality, places where known laws stop working. A black hole forms when a large amount of mass is compressed into a small enough region. Gravity overwhelms all other forces. Matter collapses inward without limit, according to classical theory. At a certain point, an event horizon forms. This horizon marks a boundary that nothing can cross outward, not even light. The event horizon is not a physical surface. It is not made of matter. It is a boundary in space-time. Crossing it does not feel special locally. An object falling in would notice nothing unusual at the moment of crossing. Yet from the outside, the horizon represents an absolute limit. Once something passes the event horizon, it is causally disconnected from the rest of the universe. No signal from inside can ever reach an external observer. Information appears to vanish behind this boundary. This makes the event horizon a true one-way edge. Not an observational horizon like the cosmic horizon, but a causal barrier enforced by geometry itself. Inside the horizon, all paths lead inward. Space-time is warped so strongly that moving forward in time means moving toward the center. The future points inward. Escape is not just difficult, it is impossible. This inversion of time and space already signals that reality behaves very differently near black holes. Concepts that feel fundamental elsewhere become interchangeable or lose meaning. According to general relativity, everything inside the horizon collapses toward a singularity. At the singularity, density and curvature become infinite. Space-time ends. Equations break down. This singularity is often described as the edge of reality, not metaphorically but mathematically. Beyond it, the theory cannot describe what happens. Yet physicists do not believe singularities are real physical objects. They are signs that general relativity is incomplete. Just as the Big Bang singularity marks a limit of description, not necessarily a beginning of existence, black hole singularities likely mark a limit of theory. Something else must happen at extreme densities. Quantum effects cannot be ignored. Space-time may not remain continuous. New physics must intervene. This makes black holes laboratories for probing the deepest layers of reality. They compress matter, energy, and information to extremes unattainable elsewhere. One of the most profound puzzles associated with black holes concerns information. According to quantum mechanics, information is never destroyed. According to classical black hole theory, information that falls in is lost forever. This conflict is known as the black hole information paradox. It is not a technical issue. It strikes at the consistency of physical law. If information is truly destroyed, then quantum mechanics fails. If it is preserved, then classical black hole theory must be revised. Decades of research suggest that information is not destroyed. Black holes are not perfect erasers. Subtle correlations preserve information, even as the black hole evaporates. This evaporation occurs through a process known as Hawking radiation. Black holes are not completely black. They emit faint radiation due to quantum effects near the horizon. Over extremely long timescales, a black hole can lose mass and eventually disappear. If it disappears completely, what happens to the information that fell in? This question forces a radical conclusion. Information must be encoded somewhere. It cannot simply vanish. This has led to the idea that information is stored at the event horizon itself, not inside the volume, but on the surface. The horizon becomes a kind of informational boundary. This idea reshapes the concept of inside and outside. What appears to be a three-dimensional volume may be fully described by a two-dimensional surface. This principle has implications far beyond black holes. It suggests that reality itself may be holographic, that higher dimensional volumes can be encoded on lower dimensional boundaries. If this is true, then the edge of reality takes on a new meaning. Edges may not mark endings. They may store information. Black holes therefore challenge the notion that edges are places where reality stops. Instead, edges may be places where reality is transformed. Inside a black hole, the fate of space-time remains unknown. Some theories suggest that space-time continues in some form. Others suggest that singularities are replaced by new phases of geometry. Some speculative ideas propose that black holes could be gateways to other regions of reality. Not traversable tunnels, but transitions. Matter falling in could re-emerge elsewhere, transformed. There is no evidence for this. Such ideas remain speculative, but they illustrate how black holes force consideration of reality beyond known structure. Even without such speculation, black holes demonstrate that reality has local boundaries, where ordinary concepts fail. Time behaves strangely. Space collapses. Causality becomes one-directional. These local edges do not end existence. They reshape it. From the outside, a black hole appears simple. It can be described by only a few parameters: mass, charge, rotation. Everything else seems erased. From the inside, if inside can be meaningfully defined, reality may be complex beyond imagination. This asymmetry between outside simplicity and inside complexity suggests that our perspective matters. What appears like an end from one viewpoint may be continuation from another. This theme recurs throughout cosmology. Horizons hide rather than eliminate. Black holes also suggest that reality is more robust than it appears. Even in extreme conditions, consistency is preserved. Laws bend, but do not break completely. This resilience hints that reality does not have abrupt ends, it has transitions. The event horizon is therefore not the edge of existence. It is the edge of accessibility. This mirrors the cosmic horizon, but at a local scale. In both cases, beyond lies more reality, inaccessible by design. This leads to a sobering conclusion. Reality may contain many such inaccessible regions. Black holes, horizons, and other extreme structures partition existence into domains. We live in one domain. Others exist without reference to us. This does not imply that reality is fragmented into disconnected pieces without coherence. Deeper laws may unify these domains at a level we do not yet understand. Black holes may be windows into that level. They expose the fault lines of current theories. Understanding black holes requires reconciling gravity, quantum mechanics, and information. This reconciliation may reveal what reality is made of at its core. Until then, black holes remain the clearest examples of local edges of reality, places where the universe confronts its own limits. They show that edges do not require distance. They can exist wherever conditions become extreme. This reinforces a broader lesson. The edge of reality is not a single boundary at the outskirts of the cosmos. It is a recurring feature wherever our descriptions fail. Yet failure of description does not imply absence of existence. It implies the need for deeper understanding. Black holes, therefore, do not represent voids in reality. They represent density of reality beyond comprehension. As we move forward, the next step is to consider an even more speculative counterpart. If black holes represent entrances, could there be exits, theoretical objects known as white holes? If they exist, they would challenge our understanding of time, causality, and the direction of reality itself. White holes are among the most speculative objects in theoretical physics, yet they arise naturally from the same equations that predict black holes. If black holes are regions where matter and information fall in but cannot escape, white holes would be the opposite, regions where matter and information emerge but cannot enter. They represent not just exotic objects, but a radical challenge to how reality handles time, causality, and direction. In general relativity, the equations describing spacetime are time-symmetric. They do not inherently prefer a direction of time. For every solution that describes matter collapsing inward, there exists a mathematically valid solution where matter expands outward. Black holes correspond to one direction of this symmetry. White holes correspond to the other. A white hole would have an event horizon similar to a black hole, but reversed in function. Nothing could cross the horizon inward. Instead, matter, radiation, and energy would emerge from it, expelled into surrounding space. From the outside, a white hole would appear as a sudden, violent outpouring of energy. From the inside, if inside has meaning, it would be inaccessible. No observer could enter to investigate. This already sets white holes apart from any known object. Black holes form naturally from stellar collapse. White holes have no known formation mechanism in our universe. Nothing in observed astrophysics suggests that matter spontaneously emerges from nothing in this way. Entropy considerations strongly disfavor white holes. They would represent an extreme decrease in entropy, a reversal of the arrow of time. This is the core problem. While general relativity allows white holes mathematically, thermodynamics appears to forbid them physically. Entropy tends to increase. Black holes fit this rule perfectly. They absorb matter, increase entropy, and simplify structure. White holes would do the opposite. They would create order from chaos, violating the second law of thermodynamics. Because of this, most physicists consider white holes unphysical, mathematical artifacts rather than real objects. Yet their existence in the equations cannot be dismissed casually. Equations that describe reality do not usually produce meaningless solutions. They often point to regimes where assumptions break down or interpretations must change. This raises a subtle question. Are white holes impossible, or are they forbidden only under familiar conditions? Some theories suggest that white holes could exist briefly, at extremely small scales or early cosmic times, where conventional thermodynamic reasoning may not apply in the same way. In quantum gravity, time symmetry may be restored at the deepest level. Entropy increase may emerge only at larger scales. If so, white hole-like phenomena could occur in restricted contexts. One such context is the Big Bang itself. Some researchers have suggested that the Big Bang resembles a white hole, a boundary from which space-time and matter emerge, but into which nothing can enter. This does not mean the universe is literally a white hole, but the analogy is instructive. Both involve one-way boundaries and outward flow of energy. If the Big Bang is interpreted as a kind of white hole, then white holes would not be localized objects, but global transitions, not things in space, but beginnings of space. This reframes the idea of an exit from space-time. Rather than matter escaping from a black hole into another region, space-time itself may emerge from deeper structure. Another speculative idea links black holes and white holes directly. In some models, a black hole could transition into a white hole after extremely long timescales. Matter falling into a black hole could eventually re-emerge, not in our future, but in a different temporal orientation. This would mean that black holes are not dead ends. They are delayed transitions. Information is not destroyed, but transformed and released. In such models, the apparent permanence of black holes is an illusion created by time dilation and horizon effects from the outside. The process appears frozen. From a deeper perspective, it completes. This idea is highly speculative, but it addresses several deep problems at once. It preserves information. It avoids singularities. It restores time symmetry at a fundamental level. If such transitions exist, then black holes and white holes would be two phases of the same object viewed from different temporal perspectives. This would imply that reality does not strictly enforce one direction of time at its deepest level. The arrow of time may be emergent, not absolute. White holes also force reconsideration of causality. In ordinary physics, causes precede effects. White holes would appear to produce effects without identifiable causes within our space-time. This would violate everyday notions of explanation, yet similar violations already appear in quantum phenomena, where outcomes occur without classical causes. White holes may represent macroscopic analogues of such behavior, not random, but acausal relative to our description. This again suggests that our intuitive categories may not apply universally. Causality may be a feature of certain regimes, not a fundamental principle everywhere. If white holes existed, they would represent local edges of time itself, places where the direction of temporal flow breaks or reverses. This would have enormous implications. It would mean that the universe contains regions with different temporal orientation, not just different histories, but different arrows of time. Observers in such regions, if they could exist, would experience reality very differently. However, there is no evidence for white holes in the current universe. No observed phenomena require them for explanation. No astrophysical signatures point convincingly in their direction. This absence makes white holes a theoretical curiosity rather than an empirical proposal. Yet their conceptual value remains. They show that the equations describing reality permit far stranger possibilities than what we observe. They also show that reality may be constrained not just by equations, but by initial conditions. White holes may be allowed by laws, but excluded by how the universe began. This distinction is important. Laws describe what is possible. History determines what is realized. White holes may be possible in principle, but unrealized in our cosmic history. This again ties back to the edge of reality. Edges may exist not because laws forbid passage, but because history selects outcomes. The universe we observe may be one realization among many allowed by deeper laws. White holes may belong to unrealized possibilities. This does not make them meaningless. Understanding what is allowed but unrealized helps clarify what shapes reality. White holes also sharpen the distinction between mathematical existence and physical existence. Not everything permitted by equations exists physically. This distinction applies to many speculative ideas: extra dimensions, multiverses, exotic particles. The challenge is determining which possibilities are realized. White holes sit at the extreme end of this spectrum. They are permitted by symmetry but disfavored by thermodynamics. This tension highlights the layered nature of physical law. Some principles operate more deeply than others. Symmetry may be deeper than entropy, or vice versa. Understanding which principles are fundamental remains an open question. White holes, therefore, occupy a liminal space. They are not observed. They may not exist. Yet they expose cracks in our understanding. They force us to ask why time flows one way, why entropy increases, why the universe selects certain solutions and not others. These are not abstract questions. They determine the structure of reality. Even if white holes never exist, the fact that the equations allow them suggests that reality could have been very different. This reinforces a humbling insight. The universe we inhabit is not the only one allowed by physical law. It is one shaped by particular initial conditions and constraints. The edge of reality, then, may not be about what is possible, but about what is realized. Beyond the realized universe lies a vast space of possibilities, some familiar, some bizarre, some fundamentally incompatible with experience. White holes inhabit that space. They mark the boundary between allowed and actual. They remind us that physics does not just describe what exists, it describes what could exist. And the difference between the two is where the deepest mysteries lie. As we continue, the next step is to move away from astrophysical objects and toward a more radical idea. The possibility that reality itself is not fundamentally physical in the traditional sense, but informational. That space, time, matter, and energy emerge from information processing. If this is true, then the edge of reality may not be spatial, temporal, or dimensional, but computational. The idea that reality may be a simulation is one of the most controversial and widely misunderstood proposals of the modern era. It is often treated as science fiction or philosophical provocation. Yet at its core lies a serious question rooted in physics, computation, and information theory. If the universe is governed by discrete laws, finite information, and computable processes, then it becomes reasonable to ask whether reality itself is fundamentally informational rather than material. This idea does not begin with computers. It begins with the observation that the universe behaves in ways that resemble computation. Physical laws are precise, outcomes follow rules. States evolve according to equations. Information is conserved, transformed, and encoded across space and time. When physicists describe reality, they increasingly do so in terms of information. Black holes are described by entropy and information content. Space-time geometry appears linked to entanglement patterns. Quantum states encode probabilities rather than concrete trajectories. Matter and energy become carriers of information rather than substances in the classical sense. This shift in language is not cosmetic. It reflects a deeper insight. What exists may be defined not by what it is made of, but by how it is structured and how it changes. From this perspective, the universe resembles a vast information processing system. Particles are states, interactions are rules, evolution is computation. If this is true, then the question of what exists beyond the edge of reality becomes the question of what exists beyond the computation we inhabit. The simulation hypothesis proposes that our universe may be an artificial instantiation of such a computation, not metaphorically, but literally. Reality could be running on a substrate outside itself, governed by rules that produce the physics we observe. This idea sounds extraordinary, but its logic is simple. If conscious experience can arise from physical processes, and if those processes can be simulated, then simulated beings could experience reality indistinguishable from a base reality. In such a scenario, observers inside the simulation would perceive their environment as fundamental. The underlying computational structure would be inaccessible from within except through indirect effects. This mirrors earlier themes. Horizons, extra dimensions, and emergent space-time all describe inaccessible layers that nevertheless shape experience. Simulation adds a different kind of inaccessibility, not spatial or dimensional, but ontological. If reality is simulated, then the edge of reality is not a physical boundary, it is the limit of the simulation itself. Beyond that limit would lie the substrate on which the simulation runs, a deeper reality not governed by our physical laws. This does not require intention, intelligence, or purpose in a human sense. A simulation could arise as a byproduct of exploration, modeling, or processes incomprehensible to us. Motivation is irrelevant to the structural question. Critics often dismiss the simulation idea as unfalsifiable, yet many accepted aspects of physics are also not directly falsifiable. What matters is whether the idea is consistent with known facts and whether it generates meaningful questions. The simulation hypothesis raises concrete questions. Is information in the universe finite? Are physical quantities discrete or continuous? Are there limits to resolution? Are there computational bounds on complexity? Remarkably, physics increasingly suggests yes. Quantum mechanics implies discreteness at fundamental scales. There are smallest units of action, smallest measurable lengths, smallest time intervals, beyond which the concept of measurement loses meaning. Information density appears finite. Black holes impose limits on how much information can be stored in a region of space. The universe may have a maximum information capacity. These features resemble constraints in computational systems: finite memory, finite resolution, finite processing speed. This resemblance does not prove simulation, but it weakens the assumption that reality must be continuous and unbounded. Another clue comes from error correction. Quantum systems exhibit behaviors similar to error-correcting codes. Entanglement appears to protect information against noise. Space-time geometry may emerge from error correction structures. This is striking. Error correction is a concept from information theory, not classical physics. Its appearance suggests that the universe is designed or structured to preserve information. Preservation of information is a computational goal. Again, this does not imply intention, and natural processes can produce computationally efficient structures. Evolution does so routinely. But it strengthens the idea that information is primary. If information is primary, then matter and energy become secondary. They are expressions of information states. This redefines existence. To exist is to be instantiated as information. From this perspective, what lies beyond the edge of reality may be more information, higher-level rules, a different encoding. The simulation idea also reframes the concept of physical law. Laws may not be ultimate truths. They may be constraints imposed by the simulation environment. Constants may not be fundamental. They may be parameters. This would explain fine-tuning without invoking design. Parameters are chosen because they work within the simulation constraints. This again parallels earlier ideas about environmental laws in multiverse scenarios. Simulation is another way to generate diversity of laws. The difference is that simulation implies an external context, while multiverse scenarios do not require one. This external context raises philosophical discomfort. Humans resist the idea that reality depends on something else. It feels diminishing. Yet dependency does not imply meaninglessness. Characters in a novel are meaningful within the story, even though the book exists on paper. The analogy is imperfect, but instructive. Internal meaning does not require ultimate fundamentality. If we are simulated, our experiences are still real experiences. Pain still hurts. Joy still matters. Meaning does not evaporate because of origin. This is a crucial point. The simulation hypothesis does not trivialize existence. It relocates its foundation. Yet, the hypothesis also raises disturbing questions. Could the simulation end? Could it be modified? Could laws change? These questions mirror fears humans have always had: cosmic destruction, divine intervention, arbitrary catastrophe. Simulation simply reframes these fears in modern language. But physics already accepts that the universe could end. Vacuum, decay, heat death, Big Rip. Meaning has never required permanence. Simulation adds no new existential vulnerability. It adds a different narrative. There is also the question of detectability. Could we ever know if we are in a simulation? Most serious discussions conclude that direct proof is unlikely. A well-designed simulation would hide its substrate. Accessing it would require stepping outside the rules, which is impossible from within. However, indirect hints have been proposed. Limits on computation, discretization artifacts, anomalies in physical constants. None of these provide evidence so far. They merely show that the idea is not logically incoherent. The lack of evidence again reinforces a theme. Beyond the edge of reality may exist, but may be permanently inaccessible. This does not make it unreal, it defines our position within it. Simulation also intersects with earlier ideas of holography and emergent space-time. If reality is information, then space and time may be interfaces, not foundations. What we perceive as distance may be a measure of information separation. What we perceive as time may be a measure of computational steps. This is not metaphor. Serious research explores space-time as emergent from information processing. If so, then simulation is not an external imposition. It is a description of what reality already is. The word simulation may mislead. It implies artificiality. A better word may be instantiation. Reality may be an instantiated information structure. Whether instantiated by a computer, a mathematical structure, or something else entirely may be irrelevant. This leads to a deeper idea. The universe may exist because it can exist, because it is consistent, because it is computationally stable. This is similar to mathematical realism. Structures exist because they are self-consistent. Physical reality would then be one such structure experienced from within. This view removes the need for external agents entirely. Reality does not need a simulator. It simply exists as an information pattern. In this case, simulation is not the correct framing. Existence itself is informational. The edge of reality would then be the edge of that structure. Not spatial, not temporal, but structural. Beyond it would lie other structures, other consistent realities, not connected, not interacting. This converges with multiverse ideas, but grounded in information rather than space. It also converges with timeless views of reality. Information structures do not require time to exist. Time emerges when structures are experienced sequentially. From this perspective, asking what exists beyond the edge of reality becomes a question about what structures exist beyond the one we inhabit. This question may be unanswerable from within. Just as a character in a book cannot read the pages outside their story, yet the existence of other pages does not invalidate the story. This brings us back to meaning. Humans fear that discovering deeper layers will drain meaning from existence. History shows the opposite. Each expansion of perspective enriches meaning. Knowing that Earth orbits the Sun did not make life meaningless. Knowing that the galaxy is not central did not erase value. Knowing that the universe may be part of something larger would not either. Meaning arises locally, from relationships, memory, and experience. Foundations do not determine significance. The simulation hypothesis, at its best, is not a claim about deception. It is a claim about structure. It suggests that what we call reality may be one level in a hierarchy of descriptions. This hierarchy may not end, or it may terminate in something utterly abstract. Either way, the edge of reality recedes, and that may be the central lesson. No matter how deep we probe, reality may always extend beyond our current framework. Not because it hides from us, but because understanding is layered. The simulation idea is one more layer. It may be wrong, it may be incomplete, it may be replaced, but it serves a purpose. It forces us to detach reality from intuition, to accept that existence may not resemble experience. This acceptance is not resignation, it is intellectual maturity. The edge of reality, then, is not a place where inquiry stops. It is a place where humility begins. As we continue, the next step is to move even deeper, beyond simulation, beyond information, toward the most abstract proposal of all, that reality itself is mathematical. Not described by mathematics, but identical to it. If this is true, then existence is structure, and the universe is one expression among countless others. This leads us to the idea of mathematical universes, and the possibility that reality at its deepest level is equation rather than substance. The idea that reality is fundamentally mathematical is one of the most abstract and unsettling proposals ever seriously considered. It does not claim that mathematics describes reality. It claims that mathematics is reality. That physical existence and mathematical structure are not separate things, but the same thing viewed from different perspectives. This idea arises from a simple but persistent observation. The universe obeys mathematics with extraordinary precision. Physical laws are written as equations, and those equations work across vast scales of space and time. They are not approximate metaphors, they are exact. This raises a question that has no easy answer. Why should abstract symbols invented by human minds map so perfectly onto the behavior of the universe? Why should reality care about equations? One answer is pragmatic. Mathematics works because it was shaped to work. Humans keep the equations that succeed and discard the ones that fail. But this does not fully explain the depth of the correspondence. Mathematics often predicts phenomena before they are observed, sometimes decades in advance. This suggests that mathematics is not merely a language. It may be the underlying structure of reality itself. The mathematical universe idea proposes that every mathematically consistent structure exists physically, not metaphorically, but literally. Physical existence is just one way mathematical structures are instantiated. In this view, our universe is a particular mathematical structure with properties that allow observers to exist within it. Other mathematical structures also exist, but most do not support observers. This reframes the question of why the universe has the laws it does. The answer becomes not because they were chosen, but because this is the structure we inhabit. This is similar to the multiverse idea, but more radical. Instead of many universes with different laws, there are infinitely many mathematical structures, each corresponding to a universe. Existence becomes a matter of consistency. If a structure is mathematically self-consistent, it exists. This eliminates the need for a creator, simulator, or external cause. Nothing selects which universes exist. All consistent ones do. This idea is deeply counterintuitive because humans associate existence with physicality, objects, matter, energy. Mathematical existence feels abstract and unreal. Yet physics has repeatedly shown that what feels abstract often turns out to be fundamental. Fields replaced particles. Space-time replaced absolute space and time. Information may replace matter. Mathematics may be the final replacement. If reality is mathematical, then what we call physical properties are internal relations within a structure. Mass, charge, and motion are not substances. They are relational quantities defined by equations. Observers are not outside the structure. They are substructures within it. Self-aware patterns capable of modeling other parts of the structure. This is a crucial point. Consciousness does not float above reality, It is embedded within mathematical relations. This embedding explains why observers experience reality from the inside. They do not see equations, they experience consequences. From within a structure, existence feels physical. Solidity, duration, and causality emerge naturally from relational consistency. This explains why the universe feels real even if it is abstract at its foundation. If this view is correct, then the edge of reality is not a boundary of space or time, it is a boundary of structure. Beyond our universe lie other structures with no connection to ours. There is no space between them, no time separating them. They simply coexist abstractly. This eliminates the idea of beyond as a direction. Beyond becomes a category change. Asking what exists beyond reality becomes asking what structures exist beyond this one. The answer may be all of them. This is both liberating and unsettling. Liberating because it removes arbitrary selection, unsettling because it removes uniqueness. Our universe is not special because it was chosen. It is special because it allows observers. This shifts explanation from causation to selection, not design, but compatibility. Some criticize this idea as unfalsifiable. If all mathematical structures exist, then no observation can disprove it. This criticism is fair. The idea does not make testable predictions beyond those already made by existing physics. Yet science has always included untestable foundations. The assumption that the universe is governed by consistent laws is itself untestable. It is a working principle. The mathematical universe idea proposes a deeper working principle. Consistency equals existence. Whether this principle is true cannot be confirmed from within any single structure. Observers cannot step outside all structures to verify it. Yet its value lies in explanatory power. It explains why mathematics works. It explains fine-tuning. It explains why reality feels law-like rather than chaotic. It also explains why the universe does not need an external cause. Existence is not triggered, it is static. This idea aligns naturally with timeless views of reality. Mathematical structures do not evolve, they simply are. Time exists only within structures that contain time-like relations. Our universe contains such relations, so we experience time. Other structures may not. They may be timeless or static in ways no observer could inhabit. This suggests that existence is vast, but experience is rare. Observers require specific structures: stability, complexity, memory, causality. Most mathematical structures do not support these features. This explains why the universe we observe is highly ordered. Only ordered structures support observers. This is not a coincidence. It is a selection effect. This again reframes the edge of reality. Reality does not end where observation ends. Observation exists only where structure allows it. Beyond our reality lies an immense abstract landscape, not of places, but of possibilities. This landscape is not spatial. It does not expand. It does not evolve. It exists timelessly. This makes the word beyond misleading. There is no outside. There is coexistence without interaction. From within our universe, other structures are inaccessible not because of distance, but because of incompatibility. They do not share variables. They do not share relations. They do not share information. This makes them utterly unreachable. This may sound like metaphysics rather than physics. Yet the boundary between the two has always been porous. Physics rests on assumptions about existence that cannot be tested directly. The mathematical universe idea simply makes one such assumption explicit. It also aligns with earlier ideas explored in this documentary: multiverses, simulations, informational reality. All point toward abstraction. Mathematical reality is the extreme form of this trend. If reality is mathematical, then the question of what exists beyond the edge of reality dissolves. There is no edge. There are only different structures. Our universe does not sit at the edge of existence. It sits within a vast space of structures. This space is not a place. It is a set. This conclusion can feel cold. It strips existence of narrative. No beginning, no end, no progression. Yet narrative exists within structures that support it. Our universe is one of them. Meaning does not require global narrative. It requires local coherence. The mathematical universe idea does not deny meaning. It relocates it. Meaning arises within structures, not across them. This is consistent with human experience. Meaning arises in lives, not in the cosmos as a whole. The universe does not owe us purpose. Purpose arises within it. This idea, therefore, does not diminish humanity. It contextualizes it. We are not the center of existence. We are a pattern within one structure among many. This has always been the direction of scientific discovery. Each step removes centrality and replaces it with context. This step may be the final one, or it may be another layer, because even if reality is mathematical, one can still ask why mathematics exists. And that question may have no answer at all. Existence may be a brute fact, not caused, not chosen, simply present. This is difficult to accept because humans seek explanation, yet explanation itself may be a feature of certain structures, not a universal requirement. The mathematical universe idea invites humility. It suggests that some questions may not have answers in the way we expect. Yet it also invites awe. Existence may be far larger, deeper, and more elegant than any story could capture. The edge of reality, in this view, is not a wall. It is the limit of relevance. Beyond it lie structures that do not concern us, not because they are inferior, but because they are incompatible. This does not make our reality small. It makes it precise. Our universe is not everything. It is something, and something is enough. As we continue, the next step is to return from extreme abstraction to a question that bridges physics and philosophy directly. If reality may be mathematical or informational, what role does consciousness play? Is consciousness fundamental, or is it emergent? Could reality exist without observers, or does observation shape reality itself? This leads us to one of the deepest questions of all: whether reality depends on being observed, or whether it exists entirely independently of mind. Consciousness occupies a strange position in discussions about reality. It is the only thing we know directly, yet it is the hardest thing to explain. Every observation of the universe is filtered through conscious experience, which raises an unavoidable question. Does reality exist independently of observers, or does observation play a fundamental role in shaping what is real? This question is often misunderstood. It is not asking whether the universe disappears when no one looks at it. It is asking whether the structure of reality depends, even in part, on observation. Classical physics assumed a clear answer. Reality exists objectively and independently. Observation reveals facts, but does not create them. The universe behaves the same whether anyone is watching or not. Quantum mechanics disrupted this certainty. At microscopic scales, the act of measurement appears to influence outcomes. Particles exist in superpositions of states until measured. Observation seems to select a definite result from many possibilities. This has led to widespread confusion. Popular accounts often claim that consciousness creates reality. This is not what quantum mechanics says. It says that interaction with the measuring system causes outcomes to become definite. Whether consciousness is required for this process remains deeply debated. Some interpretations treat observers as irrelevant. Measurement is just interaction. Consciousness plays no special role. Reality evolves according to equations, regardless of who is watching. Other interpretations give observation a more central role. They suggest that reality does not fully crystallize until it is observed. In this view, the universe exists in a kind of limbo, with properties undefined until measurement occurs. This ambiguity has fueled philosophical speculation for decades, yet no experiment has conclusively shown that consciousness itself alters physical outcomes. What matters is interaction, not awareness. This suggests that reality does not depend on mind in a direct causal sense. The universe existed long before conscious observers emerged. Stars formed, galaxies evolved, and physical laws operated for billions of years without witnesses. This historical fact strongly supports the idea that reality exists independently of observation. Yet independence does not mean irrelevance. Observation still matters in another sense. While reality may exist independently, experienced reality does not. What we call reality in daily life is a constructed model. The brain interprets sensory data, fills gaps, imposes structure, and creates a coherent world. Color, solidity, continuity, these are not properties of the external world alone. They are joint products of reality and perception. This means that experienced reality is not identical to objective reality. It is an interface. This interface evolved for survival, not for truth. It highlights relevant features and ignores most of what exists. Entire layers of reality, electromagnetic fields, quantum states, dark matter, are absent from direct experience. From this perspective, the edge of reality may not be a boundary in existence, but a boundary in perception. What lies beyond the edge of perceived reality may be vast, even within the same space. This again complicates the question of whether observers shape reality. They do not shape existence, but they shape appearance. The world we experience is a filtered projection, not a full representation. This projection is remarkably stable and consistent because it reflects real structure, but it is incomplete. This incompleteness can be mistaken for absence. What we do not perceive feels unreal. Yet physics repeatedly reveals layers of reality that perception ignores. This suggests that consciousness is not a creator of reality, but a selector of relevance. It selects which aspects of reality enter experience. This selection creates the illusion that reality is smaller than it is. This illusion fuels questions about edges and beyonds. Yet there is a deeper issue. Even if reality exists independently, the laws we formulate depend on observation. Science builds models from data. Data requires observers. This introduces a subtle circularity. Reality produces observers. Observers produce descriptions of reality. This feedback loop does not imply that reality depends on observers to exist. It implies that knowledge of reality depends on observers to arise. This distinction is critical. Without observers, reality would still exist, but there would be no descriptions, no theories, no questions. In this sense, the universe is indifferent to being known. This indifference is often emotionally difficult to accept. Humans seek significance. We want the universe to care. Physics offers no such reassurance. It describes structure, not meaning. Meaning arises within conscious systems, not from the universe as a whole. This does not diminish meaning. It localizes it. Another question arises. Could consciousness itself be fundamental? Could it be a basic feature of reality rather than an emergent one? Some philosophical positions argue that consciousness cannot be reduced to physical processes. They suggest that mind is as fundamental as matter or space. These views are controversial and lack empirical support. Neuroscience has made substantial progress explaining consciousness as an emergent phenomenon arising from complex information processing in brains. Damage the brain, and consciousness changes. Alter neural activity, and experience shifts. This strongly suggests that consciousness depends on physical structure. This dependence makes it unlikely that consciousness is a fundamental ingredient of reality. Yet the hard problem remains. Why does physical processing give rise to experience at all? Why is there something it is like to be a system? This question may not have a scientific answer in the usual sense. It may be a boundary question, similar to asking why mathematics exists. Consciousness may be an emergent fact that cannot be further reduced. This again mirrors earlier themes. Reality may have layers that are irreducible. If consciousness is emergent, then it does not define reality. It is defined by reality. This supports the view that reality does not require observers, yet observers require reality. This asymmetry matters. It implies that beyond the edge of observed reality lies more existence, whether or not it is ever experienced. The universe is not a stage built for minds. Minds are actors that arise on a stage not designed for them. This realization has consequences for how we think about significance. Significance is not cosmic, it is local. Our lives matter because they matter to us and to others, not because the universe notices. This is not nihilism, it is realism. It also reframes fear. Discovering that reality is larger than experience does not erase value. It removes illusions of centrality. This removal has happened before. Humans are not at the center of the cosmos. The Earth is not the center of the solar system. Consciousness may not be the center of reality. Each realization felt threatening. None destroyed meaning. Instead, meaning adapted. The role of consciousness, then, is not to define reality, but to navigate it. Consciousness is a tool evolved to manage complexity. It creates models, predicts outcomes, and assigns value. These models are partial. They work within certain domains. Beyond those domains, they fail. This is why questions about the edge of reality feel unsettling. They push beyond the domain where intuition evolved to function. Yet, pushing beyond intuition is precisely what science does. Science does not require comfort. It requires consistency. The consistent picture that emerges is that reality exists independently of observers, but observers experience only a fraction of it. This fraction feels complete because it is sufficient for survival. Completeness is an illusion born of adequacy. This illusion dissolves under inquiry. What lies beyond the edge of perceived reality is not emptiness. It is structure beyond relevance. This does not make it unimportant, it makes it unrelated. From the universe's perspective, there is no inside or outside. There is only existence. From our perspective, there is relevance and irrelevance. The edge of reality, then, is not a universal boundary. It is a personal one. Each observer carries their own horizon of understanding, shaped by biology, culture, and tools. As tools improve, horizons expand, yet they never vanish entirely. There will always be aspects of reality beyond experience. This is not a failure. It is a feature of finite systems embedded in larger ones. Consciousness is finite. Reality may not be. This asymmetry ensures that mystery persists. And mystery is not ignorance. It is recognition of scale. The universe is not obligated to be fully intelligible to creatures within it, yet partial intelligibility is extraordinary enough. We can understand stars, atoms, fields, and laws. We can infer dimensions we cannot see and epochs we did not witness. This capacity is remarkable. It suggests that while consciousness does not define reality, it can glimpse it. Those glimpses expand what we consider real. This brings us to the next question. If consciousness does not define reality, but interacts with it, what are the limits of interaction? Are there layers of reality forever beyond any possible observation or interaction? Not just beyond current technology, but beyond principle. This leads us to the concept of hidden layers of existence, domains that may exist but can never be accessed, detected, or influenced. Understanding these limits may be the final step in understanding what the edge of reality truly means. The limits of human senses are often mistaken for limits of reality itself. What we can see, hear, and feel feels complete because experience feels complete. Yet biology places strict constraints on perception. Our senses evolved not to reveal the universe, but to keep organisms alive. As a result, vast portions of reality lie outside direct awareness. This mismatch between reality and perception is fundamental. Humans perceive a narrow band of electromagnetic radiation and call it light. Beyond this thin slice lie radio waves, infrared, ultraviolet, X-rays, and gamma rays, all equally real, all shaping the universe in ways invisible to unaided senses. The same is true for sound, pressure, temperature, and motion. We perceive only specific ranges, as beyond them, reality continues uninterrupted. This fact alone shows that reality does not conform to perception. Perception conforms to survival needs. Technology extends perception, but extension does not eliminate limits. Instruments translate signals into forms we can interpret. They do not grant direct access to all that exists. Even with the most advanced detectors, we observe indirectly. Graphs, numbers, images are representations, not reality itself. This introduces an unavoidable filter. Reality is always mediated. This mediation raises a deeper question. Are there aspects of reality that are not just difficult to detect, but fundamentally inaccessible? Layers that no observer, no matter how advanced, could ever interact with. Physics suggests the answer may be yes. Some limits arise from fundamental principles, not technological shortcomings. Horizons, conservation laws, and quantum uncertainty impose absolute boundaries. The cosmic horizon limits what can ever be observed, regardless of future technology. Regions beyond it recede faster than light can traverse space. Information from them will never reach us. This is not a temporary ignorance. It is permanent inaccessibility. Black hole horizons impose similar limits locally. Once information crosses the horizon, it cannot return in usable form. The region exists, but interaction ends. Quantum mechanics introduces another kind of limit. Uncertainty is not about measurement error. It is about what can exist simultaneously. Some properties cannot be precisely defined at the same time. This is not a limitation of instruments. It is a limitation of reality itself. These limits suggest that reality includes domains that exist but cannot be fully known, even in principle. This challenges a common assumption that with enough progress, science will eventually explain everything. Science may explain all that is explainable, but explainable may not mean all that exists. This distinction is subtle but important. There may be aspects of reality that exist but cannot be represented in any model accessible to observers within the universe. This is not mysticism. It is a consequence of being embedded within the system one is trying to understand. A system cannot fully model itself without loss of information. Any internal description is necessarily partial. This idea appears in mathematics and computation. Systems cannot fully contain complete descriptions of themselves without contradiction or incompleteness. Reality may obey similar constraints. If so, then there may be hidden layers of existence that are real but structurally inaccessible. These layers would not be hidden because they are far away. They would be hidden because interaction with them would violate consistency. For example, extra dimensions may exist, but be compactified in such a way that no particle can enter them, not because of energy limits alone, but because of boundary conditions that forbid interaction. Or there may be fields that do not couple to any known interaction. They would exist, but leave no trace. Some physicists call such possibilities dark sectors, not dark because they are mysterious, but because they do not interact with light or known forces. These sectors could be vast, entire layers of reality overlapping our own space-time, sharing location but not interaction. This again dissolves the idea that beyond means elsewhere. Beyond may mean orthogonal. This also reframes the idea of emptiness. What appears empty may be full of structure we cannot access. This possibility is not speculation without grounding. Dark matter already demonstrates that significant components of reality interact only gravitationally. Others may interact not at all. This raises an uncomfortable possibility. There may be realities within reality that are forever beyond confirmation or denial. Science traditionally distinguishes between the unknown and the unknowable. The unknowable is often dismissed as irrelevant. Yet existence does not require knowability. Something can exist even if it cannot be known. This challenges the scope of science. Science describes the accessible structure of reality. It does not necessarily describe all of reality. This is not a failure of science. It is a definition of its domain. Confusing the scope of science with the scope of existence leads to unnecessary conflict between physics and philosophy. Physics answers how questions within accessible domains. Philosophy addresses boundary questions about existence itself. Hidden layers of reality sit at this boundary. They may be real, they may matter indirectly, or they may have no influence whatsoever. The universe does not promise relevance. This idea also reshapes existential anxiety. Some fear that if reality contains unreachable layers, human knowledge is meaningless. This fear misunderstands meaning. If knowledge does not require completeness to be valuable, partial understanding is still understanding. We understand enough to build civilizations, explore space, and reflect on existence. The presence of inaccessible layers does not negate this. It contextualizes it. Hidden layers also explain why certain questions persist without resolution. Questions about ultimate origins, absolute foundations, or totality may be undecidable. Not because humans are unintelligent, but because such questions exceed what an embedded system can answer. This suggests that the edge of reality is not just a physical boundary, but a logical one. Beyond certain points, questions lose operational meaning. This does not mean they are meaningless. It means they cannot be resolved within the system. This is similar to asking what lies outside all possible maps. The question presupposes a mapping that cannot exist. This realization requires intellectual humility. The universe may not be fully transparent to itself. Yet this opacity does not imply chaos. Hidden layers may be structured, lawful, and consistent. They simply do not intersect our domain. This possibility aligns with earlier discussions of mathematical universes and informational reality. Structures may exist without relation. Existence does not require interaction. This is difficult for humans to accept because interaction defines experience. Something that cannot be interacted with feels unreal. Yet gravity waves were once non-interacting with our senses. Neutrinos pass through the Earth almost without interaction. They exist regardless of our awareness. Interaction defines detection, not existence. Hidden layers, therefore, represent reality beyond detection. This also means that the concept of edge is relative. An edge is defined by interaction limits. Beyond an interaction boundary lies more existence, not nothing. This interpretation removes drama from the idea of edges. They are not cliffs, they are horizons. Horizons do not mark endings, they mark perspective limits. As technology improves, some horizons recede, others remain fixed. The cosmic horizon will never recede. Quantum uncertainty will never vanish. Logical incompleteness will never be eliminated. These permanent limits define the ultimate edges of human inquiry. Within them lies an immense domain of knowledge. Beyond them lies existence we cannot touch. This may sound unsatisfying. Humans seek closure, yet closure has never been part of scientific reality. Every answered question reveals deeper ones. The idea of hidden layers suggests that this process may never terminate. Reality may always have more layers than any observer can uncover. This does not mean inquiry is futile. It means inquiry is endless. Endlessness is not failure, it is richness. This brings us back to the original question. What exists beyond the edge of reality? The answer is not a single thing. It is not a place or object. It is whatever lies beyond the limits of interaction, perception, and description. That may include other universes, extra dimensions, informational substrates, mathematical structures, or layers forever hidden. Some of these may influence us, others may not. The universe does not guarantee accessibility. This realization completes a pattern that has emerged throughout this exploration. The edge of reality is not a boundary of existence. It is a boundary of relation. Beyond it lies existence without relation. This is not nothing. It is simply not part of our story. And that may be the deepest insight of all. Reality does not exist for us. We exist within a small region of it. This does not diminish our place, it defines it. We are participants in a fragment of a vast structure. Understanding that fragment deeply is already an extraordinary achievement. Seeking to understand beyond it is a noble ambition. Accepting that some beyonds may remain forever beyond is wisdom. As we move forward, the next step is to confront the most fundamental question that emerges from all of this. If there are limits to observation, interaction, and description, then is there a final edge at all? Or is reality inherently unbounded, with edges appearing only relative to observers? This leads us to the question of whether reality ends or whether it simply transforms endlessly, without a final boundary. That question brings us to the next outline. Quantum reality represents the deepest layer of physics that has been experimentally confirmed, and it radically alters how existence behaves. At this scale, reality no longer resembles objects moving through space and time in predictable ways. Instead, it becomes probabilistic, relational, and deeply non-intuitive. If there is an edge of reality, quantum mechanics suggests it is not a wall, but a change in the rules of existence itself. In classical reality, objects have definite properties. A particle has a position, a speed, and a trajectory. Whether or not anyone looks at it, cause leads to effect in a clear sequence. The universe behaves like a machine. Quantum reality breaks this picture completely. At the quantum level, particles do not have definite properties until they interact. Instead of precise states, they are described by probability distributions. Position is not a point, it is a range. Motion is not a path, it is a set of possibilities. This is not ignorance. It is not that we do not know the values. The values do not exist in a definite form prior to interaction. This is one of the most unsettling discoveries in the history of science. It suggests that reality itself is not fully formed until relations occur. This does not mean consciousness creates reality. It means interaction defines reality. A quantum system exists as a superposition of possible states. When it interacts with another system, those possibilities reduce to outcomes. Reality becomes definite locally. This process is not random chaos. It is governed by precise mathematical rules. Probabilities follow strict patterns. Outcomes are constrained. Yet the outcome of any individual event is not determined in advance. This indeterminacy is fundamental. No hidden variable has been found that restores classical certainty without breaking other well-confirmed principles. This suggests that at its deepest level, reality is not deterministic in the classical sense. This challenges the idea of an edge of reality as a boundary between something and nothing. Instead, it suggests a boundary between determinism and probability. Beyond the classical world lies a domain where existence is fuzzy, relational, and contextual. This domain is not small. It underlies everything. Atoms, molecules, stars, and galaxies are all built from quantum processes. Classical reality is an approximation that emerges when quantum effects average out. This emergence hides the strangeness beneath. Quantum entanglement further complicates the picture. When particles interact, they can become entangled, meaning their properties are linked regardless of distance. Measure one, and the other responds instantly, even across vast separations. This does not allow faster-than-light communication, but it does reveal that reality is not locally separable. Parts of the universe cannot always be described independently. This non-locality challenges the idea that reality is built from independent pieces. Instead, reality appears to be holistic. Relations matter more than objects. This has profound implications for what lies beyond the edge of reality. If reality is fundamentally relational, then beyond may not mean outside, it may mean unentangled. Regions of reality may exist that share no relational structure with ours. Such regions would be completely inaccessible, not because of distance, but because there is no shared quantum correlation. This again dissolves the idea of spatial edges. Quantum mechanics also introduces limits to knowledge that are absolute. Uncertainty principles are not about technological limits. They are about what can exist simultaneously. Certain pairs of properties cannot both be precisely defined. This means that reality itself does not contain those values simultaneously. This is not ignorance, it is structure. This introduces a fundamental edge. Not an edge of space or time, but an edge of definition. Beyond certain precision, reality does not become sharper, it becomes undefined. This suggests that at the deepest level, reality is not infinitely detailed, it is granular. There may be a smallest unit of information, a smallest meaningful distinction. If so, then the idea of infinite depth may be wrong. Reality may bottom out, not in substance, but in resolution. This would mean that beyond a certain scale, asking further questions does not reveal new structure. It reveals the limits of structure. This again reframes the edge of reality. The edge may be the point where questions stop making sense. Quantum field theory adds another layer. Particles are not fundamental objects. They are excitations of underlying fields. Fields exist everywhere. Particles appear when fields vibrate in particular ways. This means that emptiness is not empty. Even the vacuum is active. Quantum fields fluctuate even in their lowest energy state. Virtual particles appear and disappear. Energy is never perfectly zero. This vacuum activity influences reality. It contributes to forces, masses, and cosmic expansion. This again suggests that what lies beyond the edge of visible reality is not nothing, but restless structure. Quantum reality also challenges the idea of individuality. Particles of the same type are truly identical, not similar, identical. This is not a limitation of measurement. It is a fundamental fact. There is no way to distinguish one electron from another. This indistinguishability suggests that individuality is emergent, not fundamental. Objects appear distinct at macroscopic scales because of complex arrangements, not because of unique essence. This undermines a deeply ingrained intuition. We think in terms of individual things. Quantum reality suggests that individuality arises from pattern, not substance. If individuality is emergent, then asking what exists beyond reality in terms of things may be misguided. Reality may not be made of things at all. It may be made of processes and relations. Quantum mechanics also raises the question of many worlds. If every quantum event branches reality into multiple outcomes, then reality itself may constantly split. In such interpretations, the edge of reality is not static, it multiplies. Every interaction creates new branches, each equally real. This picture is controversial, but it arises naturally if one takes the equations seriously. If true, then reality does not have a single edge. It has an ever-expanding tree of possibilities. This would mean that beyond our experienced reality lie countless other realities differing by quantum outcomes. These realities would be inaccessible not because of distance, but because of decoherence. Once branches separate, they do not interact. This again emphasizes that beyond may mean orthogonal, not distant. Even if many worlds is not the correct interpretation, quantum decoherence is real. It explains why classical reality emerges and why interference disappears at large scales. Decoherence creates effective boundaries. It divides reality into branches that do not interact. These boundaries are not absolute in principle, but absolute in practice. This introduces another kind of edge. Not a fundamental edge of existence, but an effective edge of interaction. Quantum reality is full of such effective edges, boundaries created by interaction patterns. These edges shift depending on context. What is accessible in one regime is inaccessible in another. This fluidity suggests that the edge of reality is not fixed. It depends on scale, interaction, and perspective. Quantum mechanics therefore dissolves the idea of a single, final edge. Instead, reality appears layered with transitions rather than endings. At some scales, classical laws apply. At others, quantum rules dominate. At still others, gravity reshapes everything. Each regime has its own effective reality. Beyond each lies another regime, not empty, but governed by different rules. This layered structure mirrors earlier discussions of emergence, extra dimensions, and informational reality. Quantum mechanics sits at the center of these ideas because it shows that reality does not behave uniformly across scales. This non-uniformity is not a failure of understanding, it is a feature of existence. The universe does not operate by one simple rule everywhere. This realization undermines the hope for a single, final theory that explains everything in one stroke. Even if such a theory exists, its consequences may manifest differently at different scales. Understanding reality may always require multiple descriptions. This is not weakness. It is richness. Quantum reality also highlights a deeper issue. Measurement outcomes depend on context. How you measure matters. This contextuality suggests that reality does not assign absolute values independent of interaction. This does not mean reality is subjective. It means that properties are relational. This aligns with relational interpretations of physics, where the fundamental elements are relations, not objects. If relations are fundamental, then existence itself may be relational. What exists may be defined by what relates to what. This dissolves the idea of isolated existence. Beyond the edge of reality, there may be no relations linking that domain to ours. Such a domain would exist, but be entirely disconnected. This again suggests that beyond is defined by disconnection, not distance. Quantum reality, therefore, provides a consistent answer to the question of what exists beyond the edge of reality. What exists is more structure, governed by different rules, often inaccessible due to relational boundaries. There is no sharp line where existence stops. There are only regimes where our concepts stop working. This conclusion recurs throughout this exploration. Edges appear whenever concepts fail. Space fails at horizons. Time fails at singularities. Causality fails at quantum scales. Individuality fails at fundamental levels. Each failure marks an edge. Beyond each edge lies not nothing, but a deeper description. Quantum mechanics shows that even the most basic concepts are contingent. This contingency suggests that reality is not built from intuitive primitives. It is built from abstract structure. This is uncomfortable, but it is also liberating. It means reality is not constrained by human intuition. It can be richer, stranger, and more subtle. The question then becomes whether there is a final layer beyond which no deeper description exists. Quantum mechanics hints that there may be limits: smallest scales, maximum information density, irreducible uncertainty. These limits may represent the deepest edge, or they may be signs of an incomplete theory. History suggests caution. Every time physics encountered a limit, a deeper framework eventually emerged. Yet there is no guarantee this will always happen. There may be a final edge where explanation ends. That edge would not be a boundary of existence, but a boundary of explanation. This distinction matters. Reality could exist beyond explanation. This possibility is not defeatist, it is realistic. Human understanding has always expanded by confronting limits. Some limits recede, others remain. Quantum mechanics may represent a class of limits that are permanent, or it may be a stepping stone. Either way, it reshapes the meaning of beyond. Beyond is not where reality ends. Beyond is where our questions must change. This brings us to the next and perhaps most important question. If reality has no single edge, but many contextual edges, then what happens at the ultimate scale? Does reality end? Or does it transform endlessly? Is there a final boundary, or only transitions? The next outline confronts this directly by asking whether reality itself can end at all, or whether existence is inherently unbounded. This is not a technical question, it is the culmination of everything explored so far, and it leads us to the final phase of this inquiry. The question of whether reality can truly end is the natural culmination of every idea explored so far. If space may be infinite or finite without boundary, if time may be emergent, if laws may be local, if reality may be layered, relational, or informational, then the idea of a final edge becomes increasingly unstable. What appears instead is a picture in which reality does not terminate, it transforms. To ask whether reality ends assumes that existence behaves like an object with a boundary, a container that holds everything and stops somewhere. This assumption comes from everyday experience. Rooms have walls. Lands have borders. Bodies have skin. These boundaries are tangible and intuitive. Cosmic reality does not seem to follow this pattern. In cosmology, space may be finite, yet unbounded. Like the surface of a sphere, it can have a finite size without edges. Traveling far enough does not lead to an end. It leads back to where one started, though in higher dimensions this looping may be more abstract. This already undermines the idea of an edge in the most literal sense. Time shows similar behavior. It may have a beginning in our description, yet that beginning may be a transition rather than a creation. Time may not end in a final moment. It may simply lose relevance as structure dissolves. In both cases, the concept of end fails. This failure is not accidental. It suggests that the idea of an absolute boundary may not apply to reality at all. Instead of edges, reality may consist of phases. Phases are regimes where certain properties dominate. Water can be solid, liquid, or gas. None of these phases represents the end of water. They represent different modes of existence under different conditions. The universe may behave similarly, dense and structured in some regions, diffuse and simple in others, timeless in some descriptions, temporal in others. Asking where reality ends may be like asking where water ends when it becomes vapor. It does not end, it changes character. This perspective reframes all apparent edges as phase boundaries. Horizons, singularities, and limits of interaction become transitions between regimes. Even the most dramatic events in cosmology can be reinterpreted this way. The Big Bang becomes a phase transition from a quantum or pre-geometric regime into classical spacetime. Black hole singularities become transitions to unknown phases where current laws no longer apply. Cosmic acceleration becomes a transition toward a vacuum-dominated phase where structure fades. None of these imply annihilation of reality. They imply reconfiguration. This view also aligns with conservation principles. Physics strongly suggests that something is conserved. Energy, information, structure, forms change. But totality persists. Even when stars die, matter remains. When particles annihilate, energy persists. When black holes evaporate, information appears to be preserved. This persistence suggests that reality is resilient. It does not collapse into nothingness. This resilience undermines narratives of ultimate endings. Heat, death, Big Rip, vacuum decay. These scenarios describe the end of certain structures, not the end of existence. A universe filled with cold, dilute particles and empty space is still a universe. A universe where time has no meaningful direction is still existence. An existence without observers is still existence. This distinction is crucial. Humans equate meaning with structure and activity. Reality does not. The universe does not owe complexity permanence. The idea that reality ends often arises from anthropocentrism. When the universe no longer supports life, we interpret that as an end. From a cosmic perspective, it is simply a different state. This does not trivialize life, it contextualizes it. Life is a phase of cosmic evolution, not its purpose. The universe existed before life and will exist after. This does not make life meaningless. It makes it rare and valuable. This reasoning also applies to consciousness, time, and causality. These may be phases rather than absolutes. If so, then beyond their disappearance lies more reality, but without those features. This is difficult to imagine because imagination itself relies on those features. Yet, imagination is not a measure of possibility. History repeatedly shows that reality exceeds imagination. Another way to approach this question is through mathematics. Mathematical structures do not end. They exist timelessly. They may be finite or infinite, but they do not terminate. If physical reality is deeply mathematical, then it may share this property. Existence would not be a process with a beginning and an end. It would be a structure that contains processes. Processes may start and stop. The structure remains. This aligns with timeless views of reality. Time is internal, not global. In such a view, the question of whether reality ends becomes meaningless. There is no global time in which an ending could occur. There is only internal change. This also aligns with information-based views. Information is not destroyed, it is transformed. Structures may simplify, correlations may fade, but existence does not vanish. This again suggests that the edge of reality is not a final boundary. It is a boundary of description. When our concepts cease to apply, we interpret that as an end. In reality, it is a transformation beyond our conceptual reach. This realization does not answer every question. It reframes them. Instead of asking where reality ends, the more meaningful question becomes how reality changes. What transitions are possible? What regimes exist? What structures emerge and dissolve? This shift from end to transformation is central. It also dissolves existential anxiety tied to cosmic endings. The universe may become cold, empty, and dark, but existence will persist in some form. This persistence does not guarantee significance, but significance does not require cosmic permanence. Significance is local. The idea that reality must end for meaning to exist is a narrative imposition, not a logical necessity. Another concern arises here. If reality does not end, does it repeat endlessly? Does it cycle? Some models suggest eternal recurrence. Others suggest endless expansion. Others suggest static, timeless existence. The common feature is continuity of existence. Even if the universe decays into a vacuum state with minimal structure, that vacuum still exists. It may fluctuate. It may transition. It may be metastable. But it is not nothing. This leads to a sobering conclusion. Nothingness may not be a physically realizable state. Physics has no place for absolute nothing. Even the vacuum has structure. Even emptiness has laws. The idea of nothingness may be a human abstraction rather than a physical possibility. If nothingness is impossible, then reality cannot end. It can only change form. This conclusion aligns with all evidence we have. Every time something appears to disappear, it transforms. Matter to energy, structure to entropy, order to disorder, never to nothing. This does not answer why existence exists. It answers how existence behaves. Why may remain inaccessible. This again reflects the limits of explanation. There may be no deeper answer to why there is something rather than nothing. Perhaps nothing was never an option. Perhaps existence is the default. This idea is unsettling because it removes the comfort of explanation by cause. Yet it may be the most honest conclusion. Existence may not need a reason. It may simply be. This does not undermine inquiry. It defines its boundary. Science explains how reality behaves. It does not explain why existence exists at all. That question may not have an answer within reality. The edge of reality, then, may not be a place where existence stops, but a place where explanation stops. Beyond that lies silence, not emptiness. Silence not because there is nothing to describe, but because description requires concepts that no longer apply. This silence is not ignorance, it is humility. The universe may not be fully intelligible. This does not diminish its beauty. It enhances it. The recognition that reality may be endless in transformation, without a final edge, invites a different attitude. Not one of conquest, but of participation. We are not explorers marching toward a final wall. We are inhabitants of a structure that changes around us. Our task is not to reach the end, but to understand the region we occupy as deeply as possible. That understanding is already profound. Atoms, stars, galaxies, fields, quantum states, and cosmic history. This is not trivial knowledge. It is extraordinary. The absence of a final edge does not mean the absence of mystery. It means mystery is permanent, and permanence of mystery is not a flaw in reality. It is a feature of finite beings embedded in infinite or unbounded structures. This brings us to the final phase of this inquiry. If reality does not end, but our ability to describe it does, then the edge of reality is a cognitive boundary. The final outlines will address what this means for human understanding, meaning, and the future of inquiry. Not as consolation, but as clarity. The universe does not promise closure. It offers depth, and depth may be the most valuable gift existence can provide. The idea that space may have no edge at all is one of the simplest answers to the question of what lies beyond the edge of reality. Yet, it is also one of the hardest for the human mind to accept. Humans instinctively imagine boundaries. Every space we encounter in daily life has an end. Rooms have walls, roads have limits. Land meets sea. This intuition breaks down completely at cosmic scales. Modern cosmology allows for the possibility that space is finite but unbounded, or infinite without edges. Both cases remove the notion of a literal boundary where reality stops. To understand this, consider a two-dimensional being living on the surface of a sphere. From its perspective, it can travel endlessly without encountering an edge. There is no boundary to fall off. Yet the surface has a finite area. It is complete without having an end. Our universe may be similar, but in higher dimensions, space could curve back on itself in ways that are difficult to visualize. Traveling far enough in a straight line could, in principle, bring you back to your starting point, not because space loops like a circle, but because geometry itself is closed. In such a universe, asking what exists beyond the edge of space is meaningless. There is no edge. There is only continuation. Even if space is infinite rather than closed, the conclusion is similar. An infinite space has no boundary by definition. It does not end. There is no outer wall. This means that the observable universe is not a container. It is a region defined by light travel time. Beyond it lies more space, not emptiness or nothingness. This distinction is crucial. The observable universe has an edge. Because light has traveled only a finite distance since the universe became transparent, that edge is not physical. It is informational. Beyond it, galaxies exist that we cannot see and will never see. Not because they do not exist, but because the structure of space-time prevents their light from reaching us. This reinforces a recurring theme. Edges in cosmology are almost always horizons, not terminations. The absence of an edge also undermines the idea of a center. An unbounded universe has no central point. Every location is equivalent. This symmetry removes privileged positions. This has happened repeatedly in science. Earth was not the center. The sun was not the center. The galaxy was not the center. The universe may not have a center at all. This lack of center is deeply unsettling for human intuition, which seeks orientation and hierarchy. Yet it is consistent with all observations so far. The absence of edges also raises a philosophical question. If space has no boundary, then the question of what lies outside space dissolves. There is no outside. This challenges the language we use. Words like beyond, outside, and edge assume containment. They may not apply to reality at large. This does not mean the question is foolish. It means the question reveals a mismatch between language and structure. Language evolved for bounded environments. It struggles with unbounded ones. This mismatch appears repeatedly when humans confront infinity. Infinity does not behave like a very large number. It obeys different rules. In an infinite universe, repetition becomes inevitable. Patterns recur. Configurations repeat. Uniqueness becomes local rather than global. This connects to earlier discussions of repeating universes, not through branching or multiple universes, but through spatial infinity alone. This again dissolves the idea of an edge. Beyond any region lies more of the same. Yet, sameness at large scales does not imply sameness at small scales. local complexity and variation remain. This preserves meaning locally, even if the universe is infinite globally. Another consequence of edgeless space is that totality becomes inaccessible. In an infinite universe, no observer can ever survey the whole. Any description is partial by necessity. This is not a flaw of observation, it is a feature of infinity. This implies that complete knowledge of reality is impossible even in principle, not because of ignorance, but because of scale. This again suggests that the edge of reality is epistemic rather than physical. The universe may be fully real everywhere, but no finite observer can access it all. This realization aligns with earlier ideas about hidden layers and permanent horizons. An infinite universe guarantees that there will always be regions beyond reach. Yet this does not diminish the value of local understanding. We do not need to know the entire ocean to understand waves. Infinite space also raises questions about probability and explanation. In an infinite universe, every physically allowed event occurs somewhere. This complicates the notion of typicality. What does it mean to say something is likely if everything happens infinitely many times? This problem appears in cosmology and requires careful statistical reasoning. Yet even here, the absence of an edge does not lead to incoherence. It requires new tools, not abandonment of understanding. Some people find the idea of infinite space disturbing. It feels excessive, wasteful, pointless. This emotional response reflects human scale bias. The universe is not obligated to be economical by human standards. Nature often operates with abundance. There are more stars than grains of sand, more galaxies than stars. Excess is the norm, not the exception. Infinite space would simply be the extreme case of this pattern. Yet space need not be infinite to lack an edge. Finite but unbounded geometries achieve the same effect. Current observations cannot distinguish conclusively between these possibilities. Space may be extremely large and flat, or subtly curved and closed. What matters for the question of the edge is that neither option produces a boundary where reality ends. This strongly suggests that the edge of reality is not spatial. Space does not end. It either loops or continues. This realization forces a shift in thinking. Instead of imagining reality as a box, we must imagine it as a manifold, a structure without edges. This shift has already occurred in mathematics and physics. Space is described by geometry, not containment. Accepting this fully is psychologically difficult. Humans want an outside. They want a beyond that is qualitatively different. Physics offers something subtler. Beyond is more of the same, governed by the same rules. This does not eliminate mystery. It relocates it. Mystery shifts from where reality ends to why it has the structure it does, why space has the geometry it has, why laws are uniform, why dimensions are what they are. These questions remain open. The absence of spatial edges also influences how we think about creation and destruction. If space has no edge, then creation is not about filling empty space. It is about transforming existing structure. The Big Bang did not create space inside a void. It transformed space itself. Similarly, cosmic endings would not destroy space. They would alter its contents or dynamics. This again reinforces the idea that reality does not terminate. It transforms. The idea of no edge also has existential implications. Humans often imagine escaping the universe, reaching an outside, or transcending reality. Physics suggests there may be no outside to reach. Transcendence, if it exists, would not be spatial. It would involve deeper understanding, not departure. This may feel limiting. It may also be grounding. It suggests that meaning must be found within reality, not beyond it. This does not diminish aspiration. It redirects it. The aspiration becomes understanding, not escape. This is consistent with the scientific enterprise. Science does not seek to leave reality. It seeks to describe it. If space has no edge, then the universe is not a stage with curtains. It is an open structure without final boundaries. This openness is not emptiness. It is continuity. This continuity aligns with the broader picture emerging throughout this exploration. Reality does not end. It extends. Edges are artifacts of perspective. Beyond the observable lies the unobservable, not the non-existent. Beyond the describable lies the indescribable, not the absent. The edge of reality is not a place. It is a limit of framing. This prepares us for the next question. If space has no edge, if reality transforms rather than ends, then how should humans think about infinity itself? Infinity is not just a mathematical concept. It may be a physical one. Yet, infinity challenges cognition more than any other idea. The next outline will examine why infinity is so difficult to grasp, how it appears in cosmology, and what it implies for the idea of an edge of reality. This is not merely abstract. It goes to the heart of how humans confront the boundlessness of existence. Infinity is one of the most unsettling ideas the human mind can encounter. It appears simple in definition, yet impossible to visualize. It resists intuition, breaks everyday logic, and produces paradoxes that feel more like tricks than truths. Yet modern cosmology suggests that infinity may not be a mere mathematical abstraction. It may be woven into the structure of reality itself. The difficulty begins with scale. Human cognition evolved to handle finite environments. Food is limited. Distance is limited. Time is limited. Even large numbers eventually run out. Infinity does not. When humans imagine infinity, they often imagine a very large number. This is a mistake. Infinity is not large. It is unending. No matter how far you go, there is always more. No matter how much you count, counting never completes. This distinction matters because many paradoxes arise from treating infinity like a number rather than a property. Mathematics shows that infinity behaves differently from anything finite. There are different sizes of infinity. Some infinities are larger than others. Sets can be infinite, yet contain subsets that are also infinite. This alone breaks intuition. How can one infinity be larger than another? Yet mathematically, this is precise and unavoidable. When infinity enters physics, the discomfort intensifies. Infinities in equations often signal breakdowns of theory. Singularities appear where quantities diverge without bound. Physicists usually interpret these as warnings, not truths. Yet, not all infinities are pathological. An infinite universe does not imply infinite density or infinite energy in any region. It implies unbounded extent. This type of infinity may be physically meaningful. Cosmology allows for several kinds of infinity. Space may be infinite in extent, time may be infinite in duration. The number of regions like our observable universe may be infinite. The number of possible configurations may be finite or infinite depending on assumptions. Each of these infinities has different implications. An infinite space removes spatial edges entirely. There is no boundary to reality. Beyond any point lies more space. This is conceptually simpler than a finite universe with boundaries. Boundaries require special conditions. Infinities do not. Yet, infinite space introduces new problems. Probability becomes difficult to define. If every event occurs infinitely many times, what does likelihood mean? This is not a philosophical curiosity. It affects how cosmologists interpret observations in an infinite universe. Rare events are guaranteed to occur somewhere. This challenges explanation by probability. Yet, this does not make science impossible. It requires careful conditioning, and probability becomes local rather than global. We ask what is likely within a given region, not across all existence. This localization preserves predictive power. Another difficulty with infinity is repetition. In an infinite universe with finite configurations, exact copies of regions must exist. This leads to unsettling conclusions about duplication and identity. Yet this discomfort arises from conflating global structure with local meaning. Your experiences are defined by causal history, not by global uniqueness. Duplication elsewhere does not alter local significance. This is a recurring lesson. Infinity challenges emotional intuition, not logical coherence. Time introduces a different kind of infinity. If time extends infinitely into the future, then every structure eventually decays. Entropy increases. Stars burn out. Complexity fades. This leads to scenarios of heat death. The universe becomes cold, dilute, and empty. Some interpret this as an end. In fact, it is a state. Infinite time does not imply infinite activity. It may imply prolonged stillness. This raises a paradox. If time is infinite, why are we not already at maximum entropy? The answer lies in initial conditions. Entropy increases from low to high. If the universe began in a low entropy state, then there is room for increase. This again points to the special nature of beginnings, not endings. Infinite past time introduces deeper difficulties. If time extended infinitely backward, why did anything ever happen? Why are we not infinitely old? Various models address this by suggesting that while time may extend infinitely, it does not do so in a uniform way. Cycles, phase transitions, and emergent time structures may break simple, infinite extension. This shows that infinity in time is more subtle than infinity in space. Infinity also appears in multiverse and mathematical universe ideas. The number of possible universes may be infinite. The number of mathematical structures may be infinite. This raises a profound question. If everything that can exist does exist, what does existence mean? This question cannot be answered intuitively. Existence loses exclusivity. Yet again, meaning is local. Existence does not require uniqueness. It requires consistency. One of the deepest human anxieties about infinity is insignificance. If reality is infinite, humans feel small and irrelevant. This emotional response is understandable but misplaced. Significance does not scale with size. A sentence in a book is not meaningless because the book has many pages. Local narratives matter within their context. The universe does not assign value by volume. Another anxiety concerns completion. Humans like closure. Infinity offers none. There is no final chapter, no ultimate boundary, no last answer. This frustrates the desire for final explanation. Yet science has never promised finality. It promises refinement. Infinity simply makes this explicit. The idea that reality may be infinite also reframes the idea of an edge. An infinite reality has no edge by definition. Asking what lies beyond infinity is meaningless. This does not mean there is nothing beyond. It means beyond does not apply. This again highlights how language fails. Words like beyond, outside, and edge assume finitude. Infinite structures require different conceptual tools. This mismatch between language and structure creates confusion. Many debates about the edge of reality are really debates about language. When people ask what is outside the universe, they imagine the universe as an object in a container. Physics suggests this image is wrong. The universe is not inside space, it is space. Asking what space is inside is like asking what geometry is inside. The question dissolves. This does not mean curiosity is misguided. It means curiosity must adapt. Infinity also raises questions about explanation. In a finite system, explanation often involves tracing causes to origins. In an infinite system, origins may not exist. Structures may have no beginning. This challenges causal thinking. Yet explanation does not require beginnings. It requires relationships. Mathematics explains infinite sets without origins. Physics may do the same. Another subtle issue with infinity is measurement. No infinite quantity can be measured. Observation is finite by nature. This means that if reality is infinite, it can never be fully known. This, again, reinforces the idea that the edge of reality is epistemic, not ontological. Reality may be boundless, knowledge is not. This asymmetry is unavoidable. Humans often conflate what cannot be known with what does not exist. Infinity teaches the opposite lesson. What cannot be known fully may still exist fully. This is uncomfortable because it limits mastery. Yet acceptance of limits is maturity. Infinity also complicates the idea of laws. If reality is infinite, laws must apply everywhere or vary across regions. If laws vary, then infinity contains diversity. If laws are uniform, infinity contains repetition. Both possibilities are strange. Yet strangeness is not incoherence. Physics has already accepted many strange truths. Non-intuitive does not mean false. Infinity also intersects with computation. Infinite structures cannot be simulated fully. This suggests that no finite system can model an infinite reality completely. Again, this is not failure, it is constraint. Models are tools, not mirrors. The edge of reality, in an infinite context, is the edge of modeling capacity. Beyond that lies more reality, not more knowledge. This distinction is essential. Another concern is paradox. Infinity generates paradoxes like Hilbert's Hotel, where an infinite hotel can be full yet still accommodate more guests. These paradoxes feel absurd, but they are mathematically consistent. They reveal how intuition breaks down. Reality may behave in ways that feel paradoxical to finite minds. This does not mean reality is contradictory. It means our intuitions are inadequate. This inadequacy has appeared before. Relativity contradicted intuition. Quantum mechanics contradicted intuition. Both are correct. Infinity may be the next such challenge. If reality includes infinity, then human thought must accept permanent discomfort. This discomfort is not a flaw. It is evidence of progress. Each time science advanced beyond intuition, understanding deepened. Accepting infinity may be the next step. This acceptance also reframes humility. Humans are not meant to grasp infinity intuitively. We can understand it formally, relationally, indirectly. This is enough. The desire to visualize infinity may be misguided. Some truths cannot be visualized. They can only be described. This is already true for higher dimensions and quantum states. Infinity may join them. This means that the edge of reality is not something we will ever picture. It is something we infer. Inference is a powerful tool. Much of physics operates by inference. We infer dark matter, black holes, and early universe conditions without direct observation. Infinite reality may be inferred in the same way. This inference may never be confirmed or denied definitively. Yet, that does not make it arbitrary. It must be consistent with observation. So far, an infinite or unbounded universe remains consistent with all data. This is significant. It suggests that reality does not privilege finitude. Human environments are finite. Cosmic reality may not be. This mismatch is a source of existential tension. Humans seek meaning in bounded narratives. Reality may not provide them. Yet, bounded narratives can exist within unbounded reality. Life is finite. Stories end. Relationships have arcs. These arcs matter regardless of the infinity surrounding them. This again emphasizes local meaning. Infinite reality does not erase finite value. It contextualizes it. Another implication of infinity is inevitability. In an infinite universe, even extremely unlikely events occur. This challenges notions of uniqueness and miracle. Yet again, occurrence does not equal relevance. What matters is what occurs here, not everywhere. Infinity expands possibility, not necessity. This is often misunderstood. Some fear that infinity implies determinism. Everything happens, so nothing is chosen. This is false. Local choice and global inevitability can coexist. Choices matter locally, even if outcomes exist elsewhere. This coexistence is difficult to reconcile emotionally, but it is logically consistent. Infinity, therefore, does not negate agency. It reframes it. Agency operates within domains. Domains exist within larger structures. This hierarchical view is consistent across scales. Atoms exist within molecules. Molecules within cells. Cells within organisms. Organisms within ecosystems. Each level has its own agency and constraints. Infinite reality may be the largest level. It does not erase smaller levels. It contains them. This containment without edges is the key insight. The universe may be like an open-ended structure with no outer boundary. Edges appear only when descriptions change. This brings us back to the central theme. The edge of reality is not where existence stops. It is where human concepts stop applying. Infinity makes this explicit. There is no final wall, no ultimate beyond. There is continuation beyond every boundary we imagine. This does not mean reality is chaotic. It may be structured, lawful, and coherent throughout. Lawfulness does not require finitude. It requires consistency. Infinity is compatible with consistency. This is perhaps the most important lesson. The human mind equates control with boundaries. Reality does not. Accepting infinity requires letting go of the need for containment. This is difficult, yet science has repeatedly demanded such letting go. The Earth is not the center. The Sun is not special. The galaxy is not unique. Infinite reality is the next removal of privilege. This does not diminish humanity. It places humanity in context, a context that is vast, deep, and ongoing. This context does not ask us to understand everything. It asks us to understand what we can. That is enough. The idea of infinity, therefore, transforms the question of what lies beyond the edge of reality. The answer becomes simple and profound. There is no edge. There is only more. More space, more time, more structure, more possibility. And with that realization, the question itself evolves. If reality has no edge, then the meaningful task is not to seek beyond, but to understand within, to map the structures we inhabit, to recognize the limits of our models, to accept that some aspects of existence will remain forever outside comprehension. This acceptance is not surrender, it is clarity. As we continue to the next outline, the focus shifts from infinity itself to the limits it imposes on knowledge. If reality may be infinite and unbounded, then what are the ultimate limits of what can ever be known? This leads directly to the concept of cosmic censorship, horizons of knowledge, and the possibility that some truths are permanently hidden, not by distance, but by principle. That exploration follows next. The idea that some truths may be permanently hidden is deeply uncomfortable for human understanding. It conflicts with the belief that knowledge advances toward completeness, that every mystery is only temporary. Yet modern physics increasingly suggests that there may be fundamental limits to what can ever be known, not limits of technology, but limits of principle. This idea is often discussed under the concept of cosmic censorship and epistemic horizons. The universe may actively conceal certain aspects of itself, not through intention, but through structure. In general relativity, cosmic censorship refers to the idea that singularities are hidden behind horizons. Naked singularities, where space-time breakdown would be visible to observers, appear to be forbidden or extremely rare. Instead, singularities are cloaked by event horizons, preventing their influence from propagating outward. This is not merely a technical detail. It suggests that the universe protects observers from the most extreme breakdowns of physical law. Where equations fail, access fails as well. This introduces a profound principle. Some regions of reality may exist, but their details can never be observed. Black holes are the clearest example. Their interiors exist according to theory, yet no information from inside can be recovered directly. Even if information is preserved in subtle ways, the detailed internal state remains inaccessible. This means that parts of reality are real but unknowable. This is not ignorance that can be cured. It is a structural limit. Cosmic horizons impose similar constraints on large scales. Regions beyond the observable universe exist, but their state will never be measured. No future technology can change this. Expansion enforces permanent separation. This turns the universe into a patchwork of knowable and unknowable domains. Quantum mechanics introduces additional censorship. Uncertainty principles forbid simultaneous knowledge of certain properties. This is not a limitation of measurement devices. It is a limitation of what reality allows to be simultaneously defined. Entanglement introduces another subtle boundary. While correlations exist, extracting full information about a system destroys the correlations that encode it. Knowing everything is incompatible with preserving structure. This suggests that complete knowledge may be impossible even locally. there is also a computational aspect to censorship. Some physical processes may be computationally irreducible. Predicting their outcome requires simulating every step. No shortcut exists. This means that even if laws are known, outcomes may remain unpredictable in practice and in principle. This is not randomness. It is complexity beyond compression. This type of irreducibility suggests that reality may generate facts faster than they can be known. Knowledge lags existence. This, again, challenges the idea that the universe is fully transparent. Another form of censorship arises from logical limits. Systems embedded within themselves cannot produce complete descriptions of themselves without contradiction or incompleteness. This is not speculation, it is a proven feature of formal systems. If the universe is describable as a formal system, then any description produced within it must be incomplete. Some truths must remain undecidable. This does not mean meaningless. It means unprovable from within. This idea connects physics to deep results in logic and mathematics. It suggests that limits of knowledge are not accidental, they are necessary. This reframes the edge of reality as an edge of provability. Some aspects of existence may be real but undecidable. This is unsettling because it undermines the hope of total explanation. Yet it may be unavoidable. The universe may not be designed to be fully known by parts of itself. This does not imply hostility or intention. It implies structure. Reality may simply be too large, too complex, or too self-referential to be fully transparent. This is consistent with everything observed so far. Every increase in knowledge has revealed deeper layers, not final closure. Edges recede, but never vanish. This suggests a principle of perpetual horizon. For any observer, there will always be truths just beyond reach, not because of ignorance, but because of structure. This does not make inquiry futile. It defines its scope. Science aims not at omniscience, but at coherence within accessible domains. Within those domains, understanding can be extraordinarily deep. We understand stellar evolution, atomic structure, cosmic history, and quantum behavior. These are not trivial achievements. Yet even as understanding grows, horizons remain. This balance between knowledge and ignorance is not failure. It is equilibrium. The universe may be such that total comprehension is impossible, but partial comprehension is stable. This stability allows civilizations, science, and meaning to exist. Total transparency might actually be destructive. If everything were immediately knowable, complexity might collapse. Uncertainty allows novelty. Censorship allows structure. This idea turns the notion of hidden truth from a defect into a feature. The universe may preserve its own consistency by limiting access to its most extreme regimes. This does not imply design. It implies constraint. Constraints are fundamental to structure. Without constraints, nothing stable exists. This perspective also tempers speculation about ultimate answers. Questions like why there is something rather than nothing may be permanently unanswerable, not because they are forbidden, but because they lack operational meaning within reality. This does not make them illegitimate. It places them at the boundary of inquiry. Philosophy can explore them. Physics cannot resolve them. Confusing these domains leads to frustration. Accepting their distinction leads to clarity. Cosmic censorship, therefore, extends beyond black holes. It becomes a metaphor for the structure of reality itself. Some truths are hidden because revealing them would require stepping outside the system. No observer can do that. This again emphasizes that the edge of reality is not a place. It is a boundary of access. Beyond it lies existence without observability. This existence is not empty. It is simply unrelated to us. This conclusion aligns with earlier discussions of hidden layers, infinite space, and relational reality. All point toward the same pattern. Reality exceeds observation. This excess is not temporary. It is permanent. This permanence does not undermine science. It defines it. Science operates within the accessible region of reality. Within that region, laws are discoverable, patterns are explainable, and predictions are possible. Beyond it, speculation may occur, but certainty cannot. This division is healthy. It prevents overreach. It protects coherence. This also reframes humility. Humility is not weakness. It is alignment with structure. The universe does not yield all its secrets to parts of itself. Expecting it to do so is anthropocentric. Accepting limits is mature. This acceptance also reshapes how we think about the edge of reality. The edge is not where existence ends. It is where knowledge ends. And knowledge may always end somewhere. This does not diminish curiosity. It focuses it. It encourages exploration within limits rather than obsession with unreachable absolutes. This focus has driven scientific progress effectively for centuries. Accepting cosmic censorship does not close doors. It clarifies which doors exist. The idea that some truths are unreachable may feel unsatisfying. Yet consider the alternative. A fully transparent universe with no mystery would be static. Nothing new could be learned. No exploration would be meaningful. Mystery sustains inquiry. Limits sustain progress. This is not consolation. It is structure. The universe appears to be built this way. Edges of knowledge are not accidents. They are intrinsic. This realization prepares us for the next question. If some truths are permanently hidden, could advanced civilizations know more than us? Could they pierce deeper layers of reality? Or are all observers bound by the same limits? This question shifts the focus from cosmic structure to intelligence. The next outline will explore whether advanced civilizations could access deeper truths about reality's edge, or whether even the most advanced intelligence would encounter the same fundamental boundaries. That exploration follows next. The question of whether advanced civilizations might understand reality more deeply than we do is both natural and revealing. It reflects a belief that intelligence, technology, and time can eventually overcome any barrier. Yet, the deeper this inquiry goes, the clearer it becomes that some limits may be universal. Not limits of sophistication, but limits of structure. It is easy to imagine civilizations millions or billions of years older than humanity. Such civilizations would possess technologies far beyond our own. They might manipulate energy on stellar scales, engineer space-time locally, or compute with efficiencies that dwarf anything we can conceive. With such capabilities, it seems reasonable to assume they would know far more about the universe. And they would understand physical laws with greater precision. They would map cosmic structure in far greater detail. They might exploit phenomena that we barely understand today. Yet the key question is not whether they would know more, it is whether they would encounter the same fundamental edges. The evidence suggests that they would. No matter how advanced a civilization becomes, it remains embedded within reality. It cannot step outside the universe to view it from an external vantage point. It must operate within the same space-time, the same causal structure, and the same fundamental constraints. Cosmic horizons would still exist. Regions receding faster than light would remain inaccessible. No amount of intelligence can retrieve information that never arrives. Black hole interiors would remain hidden. Even if information is preserved in subtle ways, the internal structure would not become directly observable. Quantum uncertainty would still apply. No measurement strategy, however refined, can violate uncertainty relations without contradicting the framework that makes measurement possible at all. Logical limits would remain. No system can fully describe itself without incompleteness. No observer embedded in reality can construct a complete, contradiction-free account of all that exists. These are not technological problems. They are structural. This suggests that advanced civilizations may encounter the same ultimate boundaries that we do, even if they approach them more closely. However, this does not mean all observers are equal. Advanced civilizations could push practical limits far beyond ours. They could extract information from regimes currently inaccessible. They could probe quantum gravity effects, manipulate space-time curvature, and test theories that remain speculative for us. Their picture of reality would be richer, more unified, and less fragmented. Yet richness does not eliminate boundaries. It sharpens them. The more deeply one understands reality, the clearer the limits become. This has already occurred in human science. Early physics assumed that complete determinism was possible. Deeper understanding revealed fundamental uncertainty. Early cosmology assumed that the entire universe might be observable. Deeper understanding revealed horizons. Progress did not remove limits. It exposed them. An advanced civilization would likely experience the same pattern. This raises an important distinction between ignorance and unknowability. Ignorance is a temporary lack of information. Unknowability is a permanent feature of structure. Advanced civilizations eliminate ignorance. They cannot eliminate unknowability. This distinction matters when imagining godlike intelligence. Even a civilization that controls galaxies would not be omniscient. Omniscience would require access to all information in reality. Structure forbids this. This insight reshapes speculation about superintelligence. No intelligence, biological or artificial, can exceed the constraints of the system it inhabits. This does not diminish intelligence. It defines it. Intelligence is about navigation, prediction, and control within constraints, not transcendence of them. Advanced civilizations may also develop different intuitions about reality. Their conceptual frameworks might differ radically from ours. They may abandon human categories like object, time, and causality in favor of deeper abstractions. Yet abstraction does not dissolve structure. It merely reframes it. Their questions about the edge of reality may be more precise than ours. They may not ask what is beyond in a spatial sense. They may ask what structures are invariant across regimes. They may focus on meta-laws rather than laws. Yet even these refined questions may encounter boundaries. Meta-laws may exist, or they may bottom out. If they bottom out, explanation ends. This end is not ignorance. It is finality of description. Another possibility is that advanced civilizations might recognize that some questions are ill-posed. Questions like why existence exists or what lies outside, all structure may be recognized as category errors. Not unanswered questions, but unaskable ones. This recognition itself is a form of progress. Knowing which questions cannot be answered is as important as answering those that can. This is a subtle but profound form of understanding. It suggests that wisdom involves restraint. Advanced civilizations may be wiser not because they know everything, but because they know what cannot be known. This idea aligns with philosophical traditions that emphasize limits of reason. It also aligns with modern physics. Progress often comes from recognizing limits. This does not mean resignation. It means efficient inquiry. Another aspect of advanced knowledge is existential orientation. Advanced civilizations may have made peace with the absence of ultimate answers. They may not seek cosmic purpose. They may focus on local meaning, continuity, and sustainability. This would be a rational response to an unbounded or partially unknowable reality. This again mirrors human experience. Science has removed many sources of cosmic purpose. Humanity has adapted. Advanced civilizations may adapt further. They may see the universe not as a problem to be solved, but as a structure to be inhabited. This attitude does not diminish curiosity. It channels it. Curiosity becomes exploration within known limits, not pursuit of absolutes. This is not stagnation. It is alignment. Another possibility is that advanced civilizations might discover deeper layers of reality that we currently cannot imagine. This is likely. History suggests that reality is deeper than current theories suggest. Quantum mechanics and relativity revealed layers previously inconceivable. Future theories may reveal further layers. Yet even these discoveries may introduce new limits. Each layer solved introduces new horizons. This recursive structure suggests that no final theory will eliminate mystery. It may unify descriptions, but not exhaust existence. Advanced civilizations may therefore experience endless progress without closure. This may be the natural state of inquiry in a rich universe. Progress without completion. This idea conflicts with the human desire for final answers, yet it may be the most realistic picture. The universe may be such that complete understanding is impossible, but continual deepening is possible. This is not a flaw, it is an invitation. Another important consideration is communication. Even if advanced civilizations know more, they may not be able to communicate that knowledge to less advanced ones in full. Conceptual frameworks may be incompatible. Human history already shows this on smaller scales. Advanced ideas require conceptual scaffolding. Without it, information cannot be transferred. This suggests that even if answers exist, they may not be accessible to us. This is another form of epistemic horizon. Knowledge is not just about facts, it is about frameworks. Frameworks evolve. This evolution takes time. Advanced civilizations may have frameworks we cannot yet inhabit. This does not mean they possess mystical knowledge. It means they have internalized abstractions beyond current human cognition. This again underscores that the edge of reality is intertwined with cognition. What can be known depends on what can be thought. Cognition is constrained by biology, technology, and culture. Advanced civilizations may expand these constraints. They may not eliminate them. Another question arises. Could advanced civilizations alter the structure of reality itself? Could they remove horizons, reverse entropy, or access hidden layers? Some speculative ideas suggest that sufficiently advanced technology could manipulate space-time in extreme ways. Yet even here, structure imposes limits. Removing a horizon locally may create another elsewhere. Reversing entropy locally requires exporting entropy elsewhere. Nothing escapes conservation. Advanced civilizations may shift boundaries. They may not erase them. This suggests that the edge of reality is not a target to be reached. It is a feature to be managed. Management, not conquest, may be the ultimate technological posture. This perspective contrasts with science fiction narratives of transcendence. Fiction often imagines civilizations breaking free of reality. Physics suggests that reality does not allow escape. There is no outside to escape into. Transcendence, if it exists, is conceptual rather than physical. It is understanding, not departure. Advanced civilizations may therefore focus on internal enrichment rather than external escape. They may explore deeper structures, not outer edges. This is a sobering but coherent conclusion. It suggests that intelligence does not culminate in omniscience or godhood. It culminates in alignment with structure. This alignment includes acceptance of limits. This acceptance is not defeat. It is clarity. The idea that advanced civilizations would encounter the same edges does not diminish the value of progress. It enhances it. Progress becomes about refinement, not closure. This is consistent with the scientific enterprise as it already exists. Science has never promised final answers. It has delivered ever better models. Advanced civilizations may do the same. This view also has implications for humanity. It suggests that chasing ultimate answers may be misguided. Instead, the goal should be deep, coherent understanding within reachable domains. This understanding can still be profound. Human science has already achieved insights unimaginable to earlier civilizations. There is no reason to think this trajectory will stop. Yet there is also no reason to think it will terminate in final truth. This balanced view avoids both arrogance and despair. It recognizes progress without illusion. This brings us back to the central theme. The edge of reality is not something to be breached. It is something to be approached. Approach reveals structure. Breach is not possible. Advanced civilizations may approach further than we can. They may see more clearly. Yet the horizon remains. This horizon is not a failure. It is a defining feature of existence. The universe may be constructed such that parts of it are always beyond the grasp of any part within it. This self-limitation may be fundamental. It preserves coherence. It preserves mystery. It preserves the possibility of discovery. If everything were accessible, discovery would end. A universe without discovery would be static. This suggests that limits are essential for a dynamic reality. Advanced civilizations may understand this deeply. They may stop seeking the end of reality. They may instead seek harmony within it. This reframing of ambition is itself an advanced insight. It suggests that the deepest knowledge may not be about what lies beyond the edge of reality. It may be about why edges exist at all. That question leads us naturally to the final phase of this inquiry. If edges are structural and permanent, what do they imply for meaning, purpose, and the future of inquiry? The next outlines will address this directly, not by offering comfort, but by offering clarity. Because clarity, not consolation, is the proper outcome of honest inquiry. The idea that technology might one day cross the boundary of reality is a recurring theme in human imagination. From myths of ascension to modern visions of hyper-advanced machines, there is a persistent belief that sufficient technological power could overcome any limitation. Yet when examined carefully, this belief collides with the same structural constraints that govern all physical systems. Technology operates within reality. It rearranges matter, energy, and information according to existing laws. It does not stand outside those laws. This distinction is crucial. No matter how advanced the technology becomes, it remains subject to conservation, causality, and geometry. To cross the boundary of reality would require stepping outside the system that makes technology possible. This is not a question of capability. It is a question of category. Technology can extend reach. It can amplify perception. It can compress timescales and expand spatial influence. It can even alter local structure of space-time. What it cannot do is negate the conditions of its own operation. Cosmic horizons provide a clear example. No propulsion system, regardless of efficiency, can retrieve information from beyond a horizon enforced by space-time expansion. This is not because engines are weak. It is because geometry forbids connection. Technology cannot change global space-time structure without affecting itself. Black hole horizons impose similar constraints. Technology may approach arbitrarily close. It may extract energy from rotation. It may observe subtle quantum effects. Yet the interior remains inaccessible. Crossing the horizon severs causal contact. No probe can transmit data back once inside. This is not an engineering problem. It is a causal one. Quantum mechanics introduces even deeper limits. No device can measure all properties of a system simultaneously. No computer can predict outcomes beyond what quantum uncertainty allows. Technology cannot bypass uncertainty without violating the framework that allows prediction at all. Information theory reinforces this. Information cannot be created from nothing. It cannot be extracted beyond available channels. Bandwidth, noise, and entropy impose absolute limits. These limits are not contingent. They are fundamental. This suggests that technology cannot cross the edge of reality because the edge is defined by the same laws that enable technology. Crossing it would require suspending the laws locally, which would undermine the operation of any device attempting the crossing. Another way to phrase this is that technology cannot escape the substrate it runs on. Even if reality is informational, technology is an information process within that structure. An algorithm cannot step outside the computation it is part of. This analogy is not perfect, but it captures the essence of the constraint. This realization has implications for speculative ideas about transcendence. Concepts like uploading consciousness to another reality, escaping the universe, or breaking out of a simulation all assume an external interface that technology could access. Physics offers no evidence that such interfaces exist. If they do exist, they are, by definition, inaccessible to processes confined to this reality. This does not mean that deeper layers of reality do not exist. It means that access to them may not be possible through internal manipulation. This again emphasizes that the edge of reality is not a door waiting to be opened. It is a structural boundary. Technology may reveal deeper structure within reality. It may unify theories, detect subtle effects, and manipulate extreme regimes. Yet every revelation comes with new boundaries. Each expansion of capability exposes new limits. This pattern has held throughout scientific history. The telescope revealed galaxies and cosmic expansion, but also revealed horizons. The particle accelerator revealed fundamental particles, but also revealed quantum limits. Computers revealed computational power, but also revealed complexity and irreducibility. Technology amplifies understanding. but it also clarifies what cannot be overcome. This dual role is often overlooked. Technology does not just empower, it instructs. It teaches us where structure resists manipulation. This resistance is not adversarial, it is descriptive. Another aspect of technological limitation is energy. Crossing certain boundaries would require infinite energy. Infinite energy is not physically meaningful. It signals impossibility. No amount of optimization can overcome a requirement for infinity. This applies to accelerating objects to light speed, accessing certain singular regimes, or compressing information beyond entropy bounds. Technology operates in the finite. Reality enforces finitude. This again suggests that some boundaries are absolute. This does not mean technology stagnates. It means that ambition must align with structure. Technology may reshape civilization profoundly without ever crossing reality's edge. It may create artificial worlds, virtual environments, and complex simulations. It may create new layers of experience. Yet these layers remain within reality. They do not constitute exit. This distinction is subtle but important. Creating new experiences is not the same as accessing new ontological levels. Another important consideration is that technology is an extension of intelligence. Intelligence itself is subject to the same constraints discussed earlier. No intelligence can be omniscient. No intelligence can compute everything. No intelligence can access all information. Technology magnifies intelligence. It does not change its fundamental status. This undermines narratives of technological singularity as transcendence. A singularity may occur in terms of rapid change. It does not imply escape from structure. Change can be extreme without being absolute. This realism tempers speculative optimism without denying progress. It suggests that the future of technology lies not in breaking reality, but in navigating it with increasing subtlety. This navigation may include manipulating space-time locally, engineering quantum states, and exploring extreme environments. These are extraordinary achievements. They do not require crossing reality's edge. They require understanding it deeply. This also reframes ethical questions. If technology cannot escape reality, then responsibility remains internal. There is no external refuge from consequences. Actions ripple through the same structure that enables them. This reinforces the importance of foresight. Another implication concerns artificial intelligence. Advanced artificial systems may surpass human cognitive limits. They may reason about reality with greater abstraction and precision. Yet they remain bound by the same epistemic horizons. They may reach limits faster and recognize them more clearly. This recognition may guide better decision-making. It may also challenge human expectations. Humans often imagine that intelligence leads to ultimate answers. Intelligence may instead lead to acceptance of limits. This acceptance is not failure. It is maturity. This theme recurs across disciplines. Wisdom is not omniscience. It is alignment. Technology may facilitate alignment by revealing structure. In this sense, technology brings us closer to the edge of reality, not to cross it, but to see it clearly. Seeing the edge is itself an achievement. Many cultures mythologize edges as thresholds to be crossed. Science reframes them as boundaries to be understood. This reframing reduces drama but increases clarity. It replaces hero narratives with structural insight. This is a hallmark of scientific progress. The belief that technology could cross the edge of reality often stems from misunderstanding what edges are. Edges are not obstacles. They are definitions. The speed of light is not a barrier in space. It is a feature of space-time. Quantum uncertainty is not a flaw. It is a feature of reality. Cosmic horizons are not walls. They are relationships between expansion and causality. Understanding these features dissolves the desire to cross them. Instead, it motivates understanding their consequences. This shift in motivation is profound. It transforms inquiry from conquest to comprehension. This transformation is likely what advanced civilizations undergo. They stop trying to escape reality. They start trying to live coherently within it. This coherence may involve sustainability, stability, and long-term continuity. It may involve embracing uncertainty rather than eliminating it. This is not resignation, it is adaptation. Adaptation has always been the key to survival. On cosmic scales, adaptation may be intellectual rather than biological. Humans are beginning this adaptation. We are learning that reality does not bend to desire. It reveals itself through structure. Technology is the lens. Limits are the image. The edge of reality, seen through technology, becomes clearer, not closer. This clarity may be the true destination of inquiry, not beyond, but understanding. This understanding brings us to the next and final set of questions. If technology cannot cross the edge, if intelligence cannot eliminate limits, then how should humans interpret the existence of edges? What do they mean for meaning, purpose, and narrative? This leads us to the philosophical conclusion of the entire exploration. The next outline will examine how humans have historically interpreted edges of reality, from ancient cosmologies to modern science, and how those interpretations shape worldview. That final turn completes the journey. Throughout history, humans have interpreted the edges of reality not merely as physical boundaries, but as philosophical signals. When knowledge reached a limit, meaning rushed in to fill the gap. Gods, myths, cosmic orders, and metaphysical frameworks emerged where explanation failed. These interpretations were not irrational. They were adaptive responses to uncertainty. Early cosmologies imagined the universe as layered, the sky above, the earth below, and an underworld beneath. Beyond the visible horizon lay realms of gods or chaos. The edge of the known world was the edge of order. These models reflected lived experience. The world felt bounded. Beyond the village lay danger. Beyond the sea lay monsters. Translating this structure to the cosmos was natural. As knowledge expanded, edges moved. The horizon retreated. The earth became a sphere. The heavens became space. Gods were pushed outward, then upward, then inward. Each retreat of an edge forced reinterpretation. The critical pattern is this. Whenever an edge collapsed, meaning did not vanish, it transformed. The loss of a literal edge did not produce nihilism. It produced deeper abstraction. When Earth lost its central position, meaning did not end, it relocated to human agency. Ethics, reason, and progress replaced divine geography. Modern cosmology continues this pattern. The universe no longer has a center. It may not have an edge. Time may not have a beginning in the traditional sense. Reality may not have a final boundary. Each of these revelations removes a comforting structure, yet meaning persists. This persistence suggests that meaning is not supplied by cosmic architecture. It is constructed locally. Humans often assume that purpose must come from outside, from a creator, a boundary, or a final answer. Science offers no such external guarantees. This absence feels threatening only if one assumes meaning must be imposed from above. Another interpretation is possible. Meaning emerges from participation. This shift mirrors the transition from mythic to scientific worldview. In mythic systems, meaning is given. In scientific systems, meaning is built. Edges play a crucial role in this transition. When edges are imagined as walls, they invite authority. Something beyond controls what is within. When edges are understood as limits of knowledge, they invite responsibility. Meaning must be generated internally. This is not a downgrade, it is an upgrade in agency. Humans become authors rather than characters. This perspective also reframes the fear of infinite or edgeless reality. Fear arises from loss of narrative closure. Stories end. Infinity does not. Yet life does not require cosmic closure. It requires local coherence. A novel does not lose meaning because the library is large. A life does not lose meaning because the universe is vast. Meaning arises from relationships, goals, memory, and choice. None of these require a cosmic edge. In fact, fixed cosmic narratives often limit meaning by dictating purpose. An open reality allows plural meanings. This plurality is unsettling but liberating. The edge of reality, interpreted philosophically, becomes a mirror. It reflects our need for certainty. When certainty fails, character is revealed. Some respond by retreating into dogma, others by embracing inquiry. History shows that societies flourish when they choose the latter. Another philosophical implication of edge-less reality is humility. Humility here does not mean self-diminishment. It means proportionality. Humans are not central, but they are not irrelevant. They are participants in a structure larger than themselves. This participation confers responsibility. If meaning is local, then it must be maintained. There is no cosmic safeguard. This realization underlies modern ethical thinking. Without divine enforcement, ethics becomes a human project. This does not weaken ethics. It strengthens accountability. Similarly, without cosmic purpose, purpose becomes chosen. Chosen purpose is fragile but authentic. It must be renewed continuously. This fragility is often mistaken for weakness. In reality, it is what makes purpose meaningful. Something imposed cannot be meaningful in the same way as something chosen. The absence of a final edge, therefore, deepens meaning rather than erasing it. It removes the illusion of completion and replaces it with continuity. This continuity mirrors the structure of reality itself. Reality does not end. Understanding does not end. Meaning does not end. They evolve. Another important philosophical shift concerns explanation. Humans often seek ultimate explanations, a final reason. Edges promise finality. Edge-less reality denies it. This denial is often interpreted as failure. Yet explanation does not require ultimacy. It requires sufficiency. A bridge stands because of engineering principles. It does not require a cosmic explanation of gravity. Likewise, a life can be meaningful without a cosmic purpose. The demand for ultimate explanation is a psychological preference, not a logical necessity. Recognizing this reduces existential anxiety. It aligns expectations with structure. The universe does not owe answers to every why. It offers answers to how. Humans can build meaning from how. This pragmatic shift is at the heart of modern worldview. It does not eliminate metaphysics. It places it at the boundary, not the center. Metaphysical questions remain valuable as reflections on limits, not as sources of authority. Another implication concerns death. Cosmic endings often serve as metaphors for personal endings. Fear of the universe ending often mirrors fear of individual mortality. Edge-less reality does not promise immortality. It does remove the idea that death is a cosmic failure. Death becomes a local event in an ongoing structure. This does not trivialize loss. It contextualizes it. Loss matters because of relationships, not because of cosmic finality. This is a profound reframing. It grounds grief and value in lived experience rather than metaphysical stakes. Another philosophical consequence is patience. If reality has no final edge, then there is no rush toward completion. Progress becomes iterative rather than terminal. This encourages long-term thinking. Civilizations that understand this may prioritize sustainability over conquest. They may value continuity over climax. This aligns with the earlier discussion of advanced civilizations. Wisdom may lie in enduring rather than escaping. The edge of reality, understood philosophically, becomes a guide rather than a barrier. It marks where certainty ends and responsibility begins. This reframing also affects how humans relate to mystery. Mystery is often treated as a problem to be eliminated. In an edge-less reality, mystery is permanent. This permanence does not paralyze inquiry. It frames it. Science becomes exploration without expectation of finality. This expectation shift is subtle but crucial. It removes disappointment. It replaces it with curiosity. Curiosity thrives on open-endedness. This may explain why humans continue to explore even when answers raise more questions. Open systems sustain motivation. Closed systems exhaust it. An edge-less reality is an open system. This openness may be the condition for conscious inquiry itself. If reality were closed and fully knowable, inquiry would end. Consciousness might stagnate. The persistence of edges may therefore be necessary for minds to exist meaningfully. This is speculative, but suggestive. The universe may be structured in a way that sustains inquiry, not intentionally, but structurally. This structural openness allows for growth, adaptation, and learning. Edges are not failures. They are features that maintain dynamism. This perspective dissolves the fear that not knowing everything is a flaw. It reframes it as a requirement. Another implication concerns narrative. Humans crave stories with beginnings, middles, and ends. Edge-less reality resists this structure, yet humans continue to tell stories. This is not delusion. It is local organization. Stories operate at human scales. They do not need to mirror cosmic structure. Expecting cosmic reality to follow narrative conventions is anthropocentric. Recognizing this frees both science and storytelling. Science can describe structure without narrative. Humans can create narrative without cosmic endorsement. Both can coexist. This coexistence is healthy. It prevents confusion between explanation and meaning. Explanation describes what is. Meaning describes what matters. Edges of reality clarify this distinction. Where explanation stops, meaning does not. Meaning begins. This insight may be the most important philosophical outcome of exploring the edge of reality. It suggests that humans should not seek meaning in the structure of the universe. They should seek it in their relationship to that structure. This relationship includes curiosity, care, creativity, and responsibility. None of these require a cosmic edge. They require participation. Participation in an ongoing, unbounded reality. This participation is finite for individuals and civilizations. That finitude gives urgency. Urgency gives value. Value gives meaning. This chain does not depend on cosmic finality. It depends on engagement. The edge of reality, therefore, is not a threat to meaning. It is an invitation to redefine it, to move from imposed narratives to constructed ones, to accept limits without despair, to embrace openness without losing direction. This philosophical transition is still ongoing. Many humans still seek final answers. Others accept open-endedness. The tension between these attitudes shapes culture, politics, and science. Understanding the edge of reality helps clarify this tension. It reveals that the discomfort is not about physics. It is about expectations. Adjusting expectations resolves much of the anxiety. Reality may not provide closure. It provides structure. Meaning is our contribution. This contribution is not arbitrary. It is constrained by reality, but not dictated by it. This balance between constraint and freedom is where human significance lies. The edge of reality defines constraint. Within it, freedom operates. This is not an accident. It may be the only way complex, reflective systems can exist. As this exploration moves toward its conclusion, one final question remains. If meaning is local and reality is unbounded, how should humanity orient its future? What does an honest understanding of the edge of reality imply for long-term human goals? That question forms the basis of the final outline. It is not speculative fiction. It is a practical, philosophical conclusion, and it brings the entire inquiry to completion. When reality is understood as unbounded, layered, and partially unknowable, the question of humanity's future takes on a different character. The future is no longer a march toward a final answer or a cosmic destination. It becomes an ongoing negotiation between understanding, limitation, and choice. This reframing has practical consequences. If there is no final edge to reach, then progress cannot be defined as completion. It must be defined as depth, deeper understanding, deeper coordination, deeper responsibility. Human history has often been driven by edge-seeking behavior. New lands, new frontiers, new territories. These pursuits were framed as expansion toward an end. Once the end was reached, conquest stopped or transformed. Cosmic reality offers no such end. Space may be unbounded. Knowledge may be endless. Mystery may be permanent. This requires a shift from frontier thinking to stewardship thinking. Instead of asking how far we can go, the more relevant question becomes how well we can exist where we are and how carefully we expand into what we can reach. This is not a call for stagnation. It is a call for precision. Precision in exploration. Precision in technology. Precision in ethics. An unbounded reality magnifies consequences. Actions ripple forward indefinitely. Mistakes do not vanish at an edge. They propagate. This makes foresight more important, not less. Technology amplifies this effect. As capabilities grow, the cost of error increases. Without a cosmic reset or final boundary, there is no external correction. Responsibility becomes internal. This is a profound shift from earlier worldviews where ultimate judgment or cosmic closure provided external limits. In an edge-less reality, limits are structural, not moral. Morality must therefore be self-imposed. This does not weaken moral systems. It grounds them. Ethics becomes a survival strategy in an open system. Civilizations that fail to align behavior with structure collapse. Those that succeed persist. This alignment may be the defining challenge of advanced civilizations, understanding reality deeply enough to avoid self-destruction. This perspective also reshapes how humanity should view expansion into space. Space is not an escape from limits. It is an extension of them. Colonizing other planets does not remove ethical responsibility. It multiplies it. Each new environment introduces fragility. Each expansion increases complexity. This complexity requires governance, coordination, and restraint. Science fiction often imagines expansion as liberation. Physics suggests it is obligation. Obligation to maintain coherence across larger scales. Obligation to manage resources sustainably. Obligation to preserve knowledge across long time horizons. This long horizon thinking is difficult for humans. Our psychology evolved for short-term survival. An edgeless universe demands long-term cognition. This mismatch is one of the central risks facing technological civilizations. The universe will not correct short-sightedness. It will simply continue. Those who fail to adapt disappear from the story. This is not punishment, it is selection. This brings us to another implication. If reality does not end, then extinction is not a cosmic tragedy. It is a local event. This does not trivialize extinction. It contextualizes it. Species and civilizations arise and fall within an ongoing structure. This perspective can feel cold, yet it removes the illusion that survival is guaranteed or externally protected. It emphasizes agency. Nothing ensures humanity's continuation except humanity's choices. This realization is sobering, but it is also empowering. The future is not written, it is constructed. Another implication concerns curiosity. If reality is unbounded, curiosity never exhausts itself. There will always be new questions. This is a gift. It means science will never become obsolete. There will always be deeper layers, new regimes, unexplored relationships. This open-endedness sustains intellectual life. It prevents stagnation. It also means that no single generation will see completion. Progress becomes intergenerational. This requires institutions capable of transmitting knowledge across centuries. Libraries, education systems, scientific norms, and cultural values become as important as technology. In an unbounded reality, continuity matters more than speed. Rushing toward imagined ends can be destructive. This reframes ambition. Ambition should focus on durability, not dominance. Durability of knowledge, durability of ecosystems, durability of civilizations. This durability is fragile. It requires humility. It requires recognition of limits. Hubris has always been civilization's enemy. Edge-less reality magnifies hubris's cost, because there is no final victory, only ongoing participation. Another implication concerns identity. Humans often define themselves against cosmic narratives, chosen species, central observers, destined civilizations. Science has systematically dismantled these narratives. Edge-less reality completes the process. Humanity is not central, it is contextual. This does not remove dignity, it grounds it. Dignity arises from capacity to understand, care, and choose responsibly. These capacities are not diminished by scale, they are made more urgent. A small being in a vast reality must be careful. This care is a form of wisdom. Wisdom is not knowing everything. It is knowing how to act given limited knowledge. This may be the ultimate lesson of exploring the edge of reality. Knowledge will always be incomplete. Action cannot wait for completeness. Choices must be made under uncertainty. This is the human condition. An edge-less universe does not change it. It clarifies it. Another implication concerns hope. Hope is often tied to endpoints, salvation, completion, final harmony. An open reality offers no guaranteed endpoint. This can feel hopeless. Yet hope need not be about final states. It can be about trajectories, improvement without perfection, understanding without closure, continuity without certainty. This kind of hope is quieter but more resilient. It does not depend on cosmic promises. It depends on human effort. This effort is meaningful precisely because nothing guarantees success. Guaranteed outcomes are not meaningful. Earned outcomes are. This reframes the human project, not as a quest to reach the end of reality, but as a commitment to navigate it well. This navigation includes science, art, ethics, and cooperation. Each addresses different aspects of existence. Science describes structure. Art interprets experience. Ethics guides action. Cooperation enables scale. None of these require a cosmic edge. They require a shared world. This shared world exists whether or not it has an end. Another consequence of unbounded reality is patience with mystery. Mystery is not a temporary enemy. It is a permanent companion. This does not diminish inquiry. It enriches it. Mystery provides direction without destination. This is similar to exploration in an open ocean. There is no final shore. Yet exploration remains meaningful. Routes are mapped. Patterns are understood. Skills are refined. This analogy captures the appropriate attitude. The universe is an ocean, not a maze. There is no exit. There is understanding. This attitude changes how success is measured. Success is not reaching an end. It is increasing coherence. Coherence in models. Coherence in societies. Coherence in action. Coherence allows survival in complex environments. This emphasis on coherence aligns with everything learned about reality's structure. Laws are consistent. Patterns repeat. Relationships matter. Chaos emerges when coherence fails. Human systems are no exception. Edge-less reality does not forgive incoherence. It amplifies it. Another implication is humility in prediction. Long-term futures cannot be forecast precisely. Complex systems defy long-range prediction. This is not failure. It is inherent. Planning must therefore be adaptive rather than deterministic. Flexibility becomes a virtue. Resilience becomes a goal. This approach is already used in engineering and ecology. It must extend to civilization-level planning. An unbounded future demands adaptability. Fixed endpoints invite collapse. Open trajectories invite survival. This also applies to identity narratives. Humanity must resist rigid self-definitions. Rigidity fails in open systems. Adaptable identities endure. This may require cultural evolution. Old myths of destiny and final purpose may need replacement. Not with nihilism, but with open-ended narratives. Narratives of stewardship, learning, and care. These narratives align with reality's structure. They do not fight it. This alignment may be the deepest form of wisdom available. Not mastery over reality, but harmony with it. Harmony does not imply passivity. It implies responsiveness. listening to structure, adapting behavior. This is not submission, it is intelligence. This perspective also reframes fear of insignificance. Insignificance arises when value is measured by scale. Reality teaches that scale is irrelevant to meaning. Meaning arises from relationships and continuity. A single thought matters to the thinker. A single act matters to those affected. These truths do not vanish in a vast universe. They become more important because there is no external guarantee of care. Care must be internal. This internalization of value is the mature response to edgeless reality. It is not despair. It is responsibility. Responsibility is heavy. It is also empowering. It gives humanity agency without illusion. This agency is fragile. It can be lost. Recognizing this fragility is essential. Edge-less reality does not provide second chances by design. It simply continues. Those who adapt persist. Those who do not fade. This is not moral judgment. It is structural outcome. Understanding this removes bitterness. It clarifies stakes. The future of humanity in an unbounded reality is not about escaping limits, it is about living well within them. This includes expanding knowledge, managing power, preserving life, and fostering cooperation. None of these are guaranteed. All are possible. This possibility is enough. The final insight of exploring the edge of reality is therefore not about what lies beyond. It is about how to live within what is. The universe may have no edge. Human responsibility does. That responsibility defines our future. And that future is not written in the structure of the cosmos. It is written in choice. As inquiry approaches its deepest limits, a new kind of question emerges. Not what exists beyond the edge of reality, but how inquiry itself evolves when edges are recognized as permanent features rather than temporary obstacles. This marks a transition from exploration driven by conquest to exploration guided by reflection. The future of cosmology and fundamental inquiry will likely be shaped less by dramatic discoveries of new objects and more by conceptual refinement. This does not mean discovery ends. It means discovery changes character. Early science expanded by finding new domains, new continents, new planets, new particles. Each expansion pushed the edge outward. Today, the most important questions lie not at new locations, but at interfaces between frameworks. How does quantum mechanics relate to space-time? How does information relate to geometry? How does emergence arise from fundamental law? How does time arise from timeless descriptions? These questions do not point outward, they point inward. They ask how reality organizes itself. This shift reflects maturity in a field. When a domain is young, progress comes from mapping territory. When it matures, progress comes from understanding structure. Cosmology is entering this mature phase. Future breakthroughs may not look like new worlds. They may look like unifications, simplifications, reinterpretations. This does not make them less profound, it makes them deeper. A single conceptual unification can reshape understanding more than 1,000 new observations. History supports this. Relativity did not add objects. It redefined space and time. Quantum mechanics did not add entities. It redefined existence at small scales. Future theories may similarly redefine what is meant by reality, causality, or even existence. This raises an important question. Will inquiry ever reach a final theory? A final theory would be a framework from which no deeper explanation is possible, a description that does not point beyond itself. Many physicists have hoped for such a theory. Yet, the exploration of edges suggests caution. Even if a mathematically consistent framework unifies all known interactions, it may still raise questions it cannot answer. Why that framework? Why those axioms? Why that structure? These questions may be unanswerable within the framework itself. This does not invalidate the framework. It defines its scope. A final theory in the sense of no further refinement may be unattainable. A final theory in the sense of maximal explanatory coherence may be possible. The difference matters. Maximal coherence does not eliminate mystery. It organizes it. Future inquiry may therefore aim not at closure, but at stability. A stable framework that integrates observation, mathematics, and interpretation without contradiction. Within that framework, many questions may remain open, but they will be well defined. This is already how mature sciences operate. Biology has no final theory of life, yet it is extraordinarily powerful. Geology has no final theory of Earth, yet it explains planetary processes effectively. Cosmology may follow a similar path. Another important development concerns the role of computation. As models become more complex, simulation becomes as important as analytic solution. This introduces a new kind of limit. Some systems cannot be predicted without simulating them in detail. This means that understanding may sometimes mean running the universe rather than solving equations. This computational turn changes how explanation works. Explanation becomes generative rather than deductive. We understand by seeing what emerges. This approach is already common in climate science, biology, and economics. It is likely to become central in cosmology and fundamental physics as well. This does not reduce rigor, it changes its form. Rigor becomes consistency across simulation, observation, and theory. This also reinforces earlier insights about irreducibility. Some truths may not be compressible into simple laws. They may require full instantiation. This, again, suggests that edges of explanation are not failures. They are features of complex systems. Another direction of future inquiry concerns observational limits. Even as technology improves, certain horizons remain fixed. This shifts emphasis from extension to optimization. Rather than seeking ever more distant signals, inquiry may focus on extracting maximal information from accessible regions. This includes subtle correlations, background fluctuations, and indirect signatures. Future discoveries may come from precision rather than reach. This is already evident in gravitational wave astronomy and cosmic background analysis. Small deviations carry enormous information. This precision-driven approach aligns with a reality where edges cannot be crossed. It respects limits while deepening insight. Another major development will be interdisciplinary convergence. Questions about the edge of reality cannot be answered by physics alone. They intersect with mathematics, computer science, philosophy, and cognitive science. Future progress may depend on integrating these perspectives. This integration will not dilute physics. It will clarify its assumptions. Many debates about reality arise from unexamined assumptions. Making these explicit is itself progress. This convergence also helps distinguish between scientific and metaphysical questions. Not to dismiss metaphysics, but to place it appropriately. Metaphysics explores conceptual space. Physics explores empirical structure. Confusing the two leads to frustration. Integrating them leads to clarity. Future inquiry will likely be more explicit about where physics ends and philosophy begins. This transparency will help prevent false expectations of final answers. Another aspect of the future concerns public understanding. Ideas about edges of reality often provoke misunderstanding and anxiety. This is partly because they challenge intuitive narratives. Communicating these ideas responsibly is crucial. Science communication must emphasize that limits do not imply meaninglessness. They imply structure. This requires careful language. Terms like beyond, nothingness, and end are emotionally charged and often misleading. Future communication may need to develop new metaphors that better capture unbounded and layered reality. Metaphors shape understanding. Bad metaphors create confusion. Good metaphors enable insight. This is not a superficial concern. Public understanding influences policy, funding, and education. Misunderstanding the nature of limits can lead to either nihilism or unrealistic optimism. Both are harmful. A realistic understanding fosters humility and resilience. Another important implication concerns education. If reality is unbounded and inquiry open-ended, education should emphasize thinking skills rather than final facts. Students should learn how to reason under uncertainty, evaluate models, and adapt frameworks. This is more valuable than memorizing conclusions that may change. Education becomes preparation for ongoing inquiry, not transmission of completed knowledge. This aligns with the structure of reality itself. Another frontier lies in the relationship between physics and consciousness. While physics may not explain subjective experience fully, future theories may clarify the conditions under which consciousness arises. This would not solve the hard problem. It would contextualize it. Understanding limits of explanation here is as important as progress. Another direction concerns ethics of knowledge. Some knowledge may be dangerous. Power without wisdom can be catastrophic. An edge, less reality, amplifies this risk. There is no external containment. Knowledge propagates consequences indefinitely. This raises questions about restraint. Not all that can be known should necessarily be used without consideration. This is not censorship. It is responsibility. Future inquiry must integrate ethical reflection. This integration does not hinder progress. It ensures survival. Another implication is long-term continuity of inquiry. If there is no final answer, inquiry must be sustained across generations. This requires institutions, cultures, and values that prioritize continuity. Short-term incentives must be balanced with long-term goals. This is a societal challenge, not a technical one. Cosmic understanding demands civilizational maturity. Another area of future exploration is the possibility that current categories will dissolve. Space, time, matter, and causality may not survive intact in deeper theories. Future frameworks may use entirely different primitives. This has happened before. Classical notions of absolute time were replaced. Particle notions were replaced by fields. Future replacements may be even more radical. This requires openness. Clinging to familiar categories limits progress. This openness is difficult because categories shape identity. Humans think of themselves as beings in time, in space. Deep theories may challenge these intuitions. Accepting this challenge is part of inquiry. Another possible development is recognition that some questions are not merely unanswered, but unanswerable. Future inquiry may formalize this, not as defeat, but as classification. Knowing that a question cannot be answered prevents wasted effort. It redirects inquiry toward productive domains. This again reflects maturity. Mature sciences know their limits. This knowledge strengthens them. The future of inquiry into the edge of reality is therefore not bleak. It is rich. It promises deeper coherence, clearer limits, and refined questions. It does not promise finality. This lack of finality is not a loss. It is a condition for continued discovery. Discovery requires unknowns. An edge less reality guarantees them. This perspective also offers comfort of a different kind, not the comfort of closure. The comfort of participation. Humans are part of an ongoing process of understanding. This process has no endpoint. It has direction toward coherence, clarity, and responsibility. This is enough. As inquiry continues, it will likely abandon dramatic language about edges and beyond. It will speak instead of regimes, transitions, and limits. This language is less poetic, but more precise. Precision matters. Precision prevents confusion between existence and description. This distinction underlies the entire exploration. Existence may be unbounded. Description is not. The edge of reality is therefore not a thing to be found. It is a relationship between what exists and what can be known. This relationship evolves. Future inquiry will continue to refine it. This refinement may be the true legacy of exploring the edge of reality, not a map of beyond, but a clearer understanding of where and how understanding itself operates. This brings the inquiry close to completion. Only one final step remains: to articulate clearly, without metaphor or speculation, what the phrase "beyond the edge of reality" ultimately means, given everything explored. That articulation forms the final outline. It will not introduce new concepts. It will integrate all of them into a single, clear conclusion. That conclusion follows next. After tracing the idea of the edge of reality through physics, cosmology, philosophy, and human meaning, a clear conclusion emerges. The phrase, "beyond the edge of reality," does not point to a place, an object, or a hidden realm waiting to be discovered. It points to a misunderstanding rooted in human intuition. Reality, as far as evidence and theories suggest, does not end in the way stories end. It does not have a wall, a border, or an outside. What it has are limits of access, limits of description, and limits of explanation. These limits are often mistaken for edges of existence. In truth, they are edges of perspective. The observable universe has an edge because light travels at a finite speed and space expands. Beyond that edge lie more galaxies, not nothing. The edge marks what can be seen, not what exists. Black holes have edges because causality is one-directional. Beyond the event horizon lies space-time we cannot access, not avoid. The edge marks what can be influenced, not what is real. Quantum mechanics has edges because certain properties cannot be simultaneously defined. Beyond those edges lie states that cannot be fully described, not states that do not exist. The edge marks definability, not existence. Infinity feels like an edge because human cognition cannot complete it. Beyond any number lies another. The discomfort is mental, not ontological. Even questions about why existence exists encounter an edge. Not because existence stops, but because explanation stops. This distinction matters. Existence does not require explanation in order to be real. It simply is. The cumulative lesson of modern understanding is therefore simple and radical. There is no evidence that reality has an outer boundary where it ends. There is overwhelming evidence that human knowledge has boundaries where it must stop or change form. When humans ask what exists beyond the edge of reality, they are often asking one of three different questions without realizing it. They may be asking, what lies beyond observation? The answer is more reality, governed by the same or related laws, but inaccessible. They may be asking what lies beyond current theory. The answer is deeper structure that future frameworks may partially describe. Or they may be asking what lies beyond all possible explanation. The answer there is silence. Not because nothing exists, but because explanation cannot go further. None of these answers involve nothingness. Nothingness appears nowhere in serious physical description. Even the vacuum is structured. Even emptiness fluctuates. Even silence exists within a framework. This strongly suggests that absolute nothing is not a physical state. It may be a linguistic artifact. The universe does not seem to allow absolute absence. Forms change. Structures dissolve. Patterns fade. But existence persists. This persistence undermines the idea of a final edge. Instead of an edge, reality appears to have layers and transitions. Each layer introduces new rules. Each transition challenges intuition. Yet continuity remains. This continuity is the defining feature of reality. Edges are local. They appear when descriptions change scale or regime. They do not mark termination. This conclusion reframes the original question entirely. What exists beyond the edge of reality is not something beyond reality. It is reality viewed from a perspective that human cognition cannot occupy. It is reality without reference to human categories. This may include regions beyond causal contact, states beyond measurement, structures beyond comprehension, or explanations beyond reason. These are not separate worlds. They are parts of the same total structure. The inability to access them does not diminish their existence. It defines our position. This position is neither central nor trivial. Humans are embedded observers within reality. We perceive a slice. We model a fraction. We infer more. We never grasp the whole. This is not a failure. It is the condition of being a part of something larger. The edge of reality, therefore, is the edge of human reach. Reach in perception, reach in interaction, reach in explanation. Beyond that reach lies more of what has always been there. Existence without relation, existence without relevance to us. This does not make it meaningless. Meaning is not a property of the universe at large. It is a property of systems capable of valuing. Humans are such systems. Meaning arises locally. This local meaning is not threatened by an unbounded universe. It is enabled by it. Finite beings require an open environment to act meaningfully. Closed systems stagnate. Open systems sustain agency. The absence of a final edge is therefore not a loss. It is the condition that makes exploration possible. The universe does not end, so that inquiry does not end. This may be the deepest structural insight. Reality is not arranged to deliver closure. It is arranged to allow participation. Participation through observation, through understanding, through choice. The question of what exists beyond the edge of reality ultimately reveals more about the questioner than about the universe. It reveals a desire for finality, for an outside, for a place where uncertainty stops. The universe offers no such place. Instead, it offers continuity. This continuity is not chaotic. It is lawful, structured, and coherent. Yet it is never complete from any internal viewpoint. This incompleteness is not a flaw. It is inevitable, and it is what keeps reality open to discovery. The most honest answer to the question is therefore also the simplest. There is no beyond the edge of reality. There are only edges of understanding, and beyond those edges lies more reality, unchanged by whether it is known, unchanged by whether it is named, existing in full while being seen in part. This is not a poetic conclusion. It is a precise one. Reality does not end. Our descriptions do. Recognizing this does not diminish curiosity. It purifies it. It directs inquiry toward coherence rather than fantasy, toward understanding rather than escape, toward humility rather than certainty. The edge of reality is not a destination. It is a reminder that we are inside something larger than ourselves, and that understanding it, even partially, is already an extraordinary achievement.